Our goal is to kind of give you this structure and this taxonomy that allows you to look at this, archive digest or the new papers that are coming out of on this topic, and to be able to kind of use the structure that we provide in order to situate where this work lies in this huge set of literature. There's also, a lot of confusing terminology, right? Implicit representations, implicit neural representations, and so on and so forth. So we try to kind of provide a comprehensive overview of neural fields, sampling a diverse set of papers in this topic, and also provide terminology that's going to help us understand what's out there. So our goal really is, one of the things that we did a few months ago was to read 300 plus papers in neural networks. And this was, by the way, work that was primarily led by Zhong and Kawaki. And what they did was they went through all of these papers, plowed through all of these papers, and wrote a Eurographics state-of-the-art report, which was published a couple of months ago. And this tutorial kind of follows the structure of this state-of-the-art report that was published at Eurographics. And this tutorial is also accompanied by a website, a community website that is a searchable database of neural field papers, as well as hopefully the structure that we're going to provide you today is going to help you kind of wade through this immense amount of literature. So I'm going to play this video that that's computer vision humor for you. Anyway, hopefully that gave you a very quick overview of what we are trying to do here. All right, so the tutorial journey today is going to be split into 5 parts. We are right now in the introduction, running a little bit late, but hopefully we can catch up on time. We're also going to talk about a little bit about the companion website and the features that this website has. And we're also really excited to announce a community effort to kind of keep on top of all the papers that are being published in the neural fields community. So that's going to be something that we're going to do right after the introduction. So after that, we are going to be diving through some of the techniques that we use in neural fields. So we're going to, the tutorial is going to be primarily split into AM and PM. And in the AM, we are primarily going to focus on neural field techniques. So what are some of the technical methods? What are some of the techniques that people use when they try to build neural field methods? So that's going to be the focus of the morning session. And this is going to have 5 lectures by my co-organizers. And the PM section is going to have 2 parts. The first part is application. So we're going to take all the techniques that we've described in the morning and kind of demonstrate how these techniques are used in various kinds of applications. Which spans things from 3D reconstruction all the way to robotics and compression. And finally, I'm really excited that we are going to have 3 invited speakers who are all experts in neural fields and computer vision, but also broadly beyond computer vision in science and physics, so content creation as well. So we're going to have 3 exciting invited speakers who are going to be talking about applications of neural fields beyond computer vision. So you can go to our the tutorial website at this link over there if you want to take a quick look at the schedule. We're also going to have this, the slide that I just showed in the previous slide that's going to come periodically during the day today, and hopefully that's going to situate all of you to where you are in the tutorial journey. I'd also like to take this opportunity to point out that June 19th and 20th marks Juneteenth, which is a US holiday commemorating the end of slavery in the United States. This is of special significance here in New Orleans. In fact, I was just looking through the Wikipedia page and I found that this sculpture here was installed recently, not very far from here in Lafayette Square. So I would encourage all of you to kind of go check it out. I think this is very important. Just some quick logistics. As I'm sure all of you are aware, masks are required. Speakers are, for my fellow speakers, it's okay for you to remove your masks when you're speaking. We're going to have a Q&A session Unfortunately, I'm not sure if the microphones there work. We might ask you to come over here to the podium to ask your questions. And for the speakers, please repeat the question just so that the virtual audience on Zoom can understand what the question is. This session is being recorded, and hopefully we'll be able to post the video of this online after a few weeks. And then finally, if you have your laptops here and you're trying to log into the Zoom room, if you could please avoid that, that'd be great. There's limited bandwidth in this space, and we want to make sure that the virtual attendees have the best experience. I'd also acknowledge the thousands of authors who publish papers in this neural field. This has been really exciting for me to kind of read these papers and kind of build this tutorial and the review paper. We'd also like to thank mini-conf authors, Jaden Yi, Sunny Lee, who helped with various parts of preparing this tutorial, as well as our funding agencies, the NSF and Google Research. I'd also like to acknowledge the broader set of co-authors that we have in preparing the state-of-the-art report at Eurographics, some of whom are actually here in the audience, so looking forward to catching up with you. All right, so with that, I'm going to hand it over now to Tawaki, who's going to give us the definition of neural fields, a formal definition of neural fields, and try to scope out the rest of the tutorial later.
Hi everyone, I'm Tawaki from NVIDIA and University of Toronto, and I'm super excited to be here to help teach this tutorial on neural fields and computer vision. I'm also excited that so many people are interested in this topic because I'm super interested in this topic. So I'm really excited to share some of the insights that we gained from basically reading all these papers. So I'm going to start off with giving some definitions of neural fields and some motivations as to why we might want to use something like neural fields. I'll start with some definitions. So a field is a quantity defined for all spatial and or temporal coordinates. And this basically means that you have some coordinate in some kind of space, and you might have some quantity defined there, like maybe RGB color or density or whatever you want to be there. A neural field is a field that is parameterized fully or in part by a neural network. And we realize that this is actually not necessarily a super complete definition in the sense that not necessarily all neural fields might actually be defined by spatial and or temporal coordinates. But we think that this is like a good starting point to start to think about classifying what neural fields are and why we might be interested in these kind of things. So I'll give some examples of fields to give you an idea of more intuitive idea of what fields are. Fields can be things like vector fields, in this case defined on like a spherical coordinate space. It can also be images, which is the 2D function that gives you RGB. They could also be explicit surfaces, for example, like a 3D parabola, which is a function of x and y and gives you the height of the surface. They might be also things like implicit surfaces, where you basically have some volumetric function and you basically take the level set of that function to get a surface. And they might also be things like 1D functions like audio as well. And all sorts of basically things in the world can be represented as fields, which is super exciting. So I'll also discuss some related terminology and potential misnomers. So the term that we see a lot in the community is implicit neural representations. And in a lot of cases, this is actually not necessarily a misnomer if you are talking about implicit surfaces, which is basically like a level set to represent a surface. Oftentimes, people use this expression to not describe only implicit surfaces, but just neural fields in general. And in many of these cases, we think that this is a little bit misleading of the terminology, so we prefer not to use it. Another example of terminology is coordinate-based neural networks. Coordinate-based neural networks are actually like a pretty good terminology to use, and it's accurate, but we think that it's a little bit of a mouthful, so we don't really prefer it. Another example that I see a lot, and I kind of like sometimes see myself using this term a lot myself, is just simply referring to neural fields as NERFs. But if you think about what NERF stands for, it's actually neural radiance fields. So in a lot of cases, you're not actually representing radiance with your neural field. So we also think that this is a bit of a misnomer in many cases. So we basically propose to use the term neural fields as an alternative that is both concise and also gets the point. So you might ask yourself, why would you want to use these neural fields representation in the first place? To think about this, it's helpful to look at the many different types of signals that already exist in the world. So many signals that you encounter in the natural world are usually continuous signals. And typically to represent them on a computer or something like that, you have to sample this signal in some kind of way and convert that into a discrete representation. A neural network is very similar in the sense that you're trying to also represent the signal, but instead of representing it with these discrete samples and interpolating between them to make it continuous, you basically have this parametric function that is continuous to try to regress your continuous function. And given this, we basically came up with maybe 3 properties of these neural fields that make them interesting with respect to traditional discrete signal representations, which is compactness, regularization, and domain agnostic. We'll go into much more details on what we mean by these terms much later in these slides. So to consider why neural fields are interesting, it's first helpful to look at discrete signal representations. Discrete signal representations are basically uniform samples of your continuous signal. And basically, these are equally spaced in many cases. And since they are discrete samples, you can basically represent this as a vector. In this case, an 8-dimensional vector. These discrete representations are nice because you can use the rich theory of frequency-based signal processing to reason about these signals in a principled way. And being vectors, you can also use them. You can also use them alongside the rich sets of tools that you get from linear algebra. And you can use for example, a matrix multiplier on these vectors to do operations like PCA and whatnot. So, but the difficulties with these discrete representations come along when you start to reason about these discrete representations in a higher dimensional space. So one example of this is a 2D image. Instead of just having a 1D vector, now you have to store a whole 2D vector to store your image. And for example, with this relatively small image of 1024 by 1024, if you were to have, for example, 3 color channels RGB and represent them in an 8-bit color space, then just to store this image, you need to store 3 megabytes of raw uncompressed data if you want to store this image. If you want to represent something like a movie or something like that, say a 2-hour movie or something like that at 30 FPS, all of a sudden you're working with 0.68 terabytes of data that you have to store in order to represent this video. This is obviously not super feasible in many different applications. So people have developed technologies to basically compress this type of data. If you look at this video, for example, you can see that across temporal frames, there's a whole lot of redundancy that you can capture. And basically, if you, for example, just simply take the diff between each of these images, you're left with a lot less information and much more sparse information, which you can store much more efficiently. And people have put in lots and lots of engineering effort to basically design codecs and video codecs, image codecs and whatnot to try to compress this type of data. But instead of having videos, what if we extended it not in the temporal direction, but in the spatial direction? So this is something we're kind of seeing the evolution from 2D media into 3D media where we have volumetric data. We have 3D data we want to work with in graphics. You might also have 4D data like temporal volumetric videos and stuff like that. And in these cases, unlike in videos, there's not a specific axis where you can easily take advantage of the redundancies that exist across a certain axis. So to design, codecs and compression algorithms for stuff like this, you need to design very specialized algorithms and stuff like that. And this extends beyond just 3D voxels to, very high dimensional data or just very unique data where you might not have a lot of resources to actually try to design and engineer codecs for them. So this kind of motivates our neural fields as a compact data representation, which I'll discuss more just now. So as a motivating example to try to understand why neural fields are nice and compact and why the compactness is even useful, I'm going to quickly introduce 3D reconstruction. So basically, this is a very typical setup that you see in many computer vision papers, where basically the signal of interest is 3D geometry and appearance. So what you want is a signal where given some coordinate, you want to know the geometry and appearance at that location. And basically the signal that you have available to you might be something like multi-view images, where basically these are just like, random camera positions that may or may not be calibrated, that take images of that, 3D geometry and appearance that you want to reconstruct. And basically you can solve this as an inverse problem. So an inverse problem is the form of the math equation there. But basically the things to look at here is y is the ground truth. So that's like the multi-view images that you have available. And x is the signal that you want to reconstruct. So in this case, it's like some kind of 3D volumetric information of geometry and appearance. And we also use this notion of a forward map, the function f, which is basically responsible for lifting your signal that you want to reconstruct up into the space of signals that you have available to supervise. So in this like multi-view rendering setup, this forward map function could be something like a differentiable render that maps your 3D volumetric function into multi-view images. And you basically just supervise it and optimize this problem end to end. In this sort of problem, like the important thing here is how you represent that signal x, because whatever algorithm that you design for, the variable that you are optimizing for is the variable x, which is the signal that you want to reconstruct. So whatever choice of mechanism you choose there affects the entire computational system design. So one super cool paper at CVPR 2022, these are actually two papers that do very similar things, Planoxels and Direct Fox Go. Basically, their idea is that we should represent that signal x with a sparse grid, like a discrete signal representation that encodes geometry information through density and also appearance through a spherical harmonics. And basically, they show in their paper that this works really well. And basically, they're able to, just by designing this system of like doing rendering on this like discrete signal representation, doing volumetric rendering and supervising with multi-view signals and stuff like that, they're basically able to reconstruct very high fidelity reconstructions of that 3D scene very fast also. However, the problem here is that because you're using these discrete representations that which scale, you have the curse of dimensionality and you add one axis and it becomes all of a sudden really big in memory. So these types of approaches can be very expensive in memory. And also once you want to store this information that you reconstructed, it's also expensive to store. Anyways, so what we basically see is that like, this class of like traditional discrete signal representation methods can get the same quality as something like, neural radiance fields, which just uses a single neural network to reconstruct the scene. But what we basically see is that, these class of methods are much more expensive. And we basically see in the purple curve kind of like represents like the different class of methods that exist within neural fields. And we basically see, so basically the y-axis here is quality and the x-axis here is the size. And you're basically examining the trade-off between size and quality for neural fields here. And like just like a signal representation. And what we basically see is that we tend to see that these neural field-based methods actually scale a little bit better in terms of quality with respect to size in comparison to these traditional discrete signal representation methods. So moving on from compactness, another motivation we have for these neural fields is regularization. And to kind of like understand what I mean by regularization, I'm just going to use the same problem from the 3D construction again. Basically, the idea is that you want to do 3D construction from these multi-view images, and each of these cameras have a bunch of pixels, and from each of those pixels, you can basically draw rays that go into your object. And maybe you have like this like blue bunny that you want to reconstruct, and you have 3 different camera rays that tell you that you should reconstruct a blue pixel according to that camera ray. And an ideal optimization method will get you this blue bunny exactly, but you could also equally get, for example, this blue sphere that you reconstruct, which will give you exactly the same loss. It's not even a local minimum or anything, just like a globally minimum optimizer could give you this same result, just because your problem is not very well constrained. Meaning that if you have 3 camera rays going in, that's telling you is blue. There's infinite solutions here that you can actually have to reconstruct this issue, this problem. And basically, this is typically known as an under-constrained problem, where you don't have enough constraints to actually, bound your problem such that you have actually a solution that you can solve for. And basically the typical, not typical, but one solution to this kind of like under constrained problem setup is that you can just add a lot more constraints and a lot more ground truth so that you can constrain your seed such that there's only one solution, or maybe there's no solutions, that you like regress for a solution that seems to work for all of them. But doing this kind of thing for, especially for like a 3D reconstruction setup, can be very expensive, because if you have like a 3D scanner or something like that, you basically have to go into every single possible configuration, look at every single corner, deal with occlusion and stuff like that. This can be quite difficult. So the typical way, I guess, like this type of setup is known as compressed sensing and computer vision. And the typical way of solving this type of problem, under constrained problem, is you can add some kind of regularization. And so this is on the left-hand side here is the usual inverse problem setup that you have. On the right-hand side is basically some regularization function P, which regularizes your signal X in some kind of way. And basically the idea here is that, if you have some like prior knowledge about your scene, for example, if you just know that your scene that you're reconstructing is a blue bunny, maybe you can inject some kind of prior knowledge, basically saying, reconstruct me a blue bunny. And maybe you can like, even if it's under constraint, you can actually still solve that system exactly. So this is kind of like basically like, so what we see here is that with discrete signal representations, you kind of need all these like regularization design to actually reconstruct the signal of your choice, because these problems are under constrained. And one example you see in a lot of these like traditional discrete signal based reconstruction methods is that they require a lot of like regularization tuning in order to get a good reconstruction. In comparison, something like neural radiance fields, which is just a single global neural network that you use to reconstruct your scene, you don't really need to have any like explicit. I'm not saying that it's not helpful to have them, but even without any regularizations, you're actually able to get pretty good reconstructions from these like relatively sparse multi-view images. And this basically points to the fact that basically the neural network architecture itself kind of functions as an inductive bias that constrains the smoothness of the signal in such a way that you can actually reconstruct the signal even without handcrafted priors and stuff like that. And there's a bunch of different papers that kind of like show this like same phenomenon happening for different applications. But one that I think is really interesting is this paper on trained networks for compressive lenses photography. They actually use a neural network-based representation in a compressed sensing application, I think specifically diffuser cam. And they basically show that, having this like neural network representation without any regularizations or anything like that, and reconstructing this like inverse problem in this compressed sensing setup, they seem to be actually able to get even better results than like hand-tuned like TV regularization based priors to reconstruct this signal. And yeah, this regularization thing I think has like implications beyond just like being able to reconstruct signals better, which is that, what we see is that these neural networks have these nice priors that make it easier to reconstruct signals. And I think this is actually a really important thing that is driving research forward also, which is that it's easy to really prototype, different kinds of applications using these neural fields because they have nice priors that make it easier to learn. And I think that even you could think of, you can even think about these neural fields as like a tool of prototyping even before, basically you prototype with neural fields before you actually, you might go and like design your like big like traditional signal based system. So I think that there's like room for exploration even to like explore neural fields as like a tool for like prototyping in the future as well. The last feature I want to focus on is that the neural fields are also domain agnostic, and I'll explain what that means. So we kind of see in the vision community a shift towards like 2D vision to 3D vision, where we want to reason about geometric stuff. So we want to reason about things like volumetric objects and meshes and all that kind of stuff. But if you think about appearance of these 3D information, it's actually like not necessarily even a 3D function, but also a 5D function. Where basically, if you think about something like a mirror that you look at, the appearance of the mirror actually changes based on your location and the relative view direction that you have with the mirror, which basically means that to model appearance accurately, you can't just only model the 3D function, but you also have to model this 5D function. And this becomes, we just like talked about previously how, having like a 3D information or like 4D videos and stuff like that is already getting into like, unfeasible territory for these discrete traditional representations. But now we have to work with 5D functions and maybe even 6D functions if you want to add temporal information to that. Basically, in computer graphics, people have had to deal with this kind of thing because, in computer graphics, we deal with things like view direction all the time. And basically, the typical solution in the 3D graphics context is that, you kind of like separate your problem. So you might have like a 3D grid that contains 2D basis functions or something like that. So you can separately model the 3D component and the 2D component that holds, like additional view direction and view dependent information. And for example, like stuff like, DDGI, for example, uses kind of like grids of like spherical harmonics functions, which are basically 2D basis functions. On the other hand, though, with neural fields, you talk about neural fields and it sounds like, this fancy stuff with like AI and stuff like that. But the neural networks that we actually deal with in neural fields are actually very simple mathematical objects. They're usually just multi-layer perceptrons, which basically consist of matrix multiplications with nonlinearity. And basically, with these neural networks, if you want to, for example, add another dimension, another input dimension into your input coordinate space, it's actually a very simple operation where, for like a 2D input space, you might have like, for example, if you want to map it to like a 4D space, you have like 8 parameters. And if you want to add another dimension, another input dimension, all you need to do is insert another column into this matrix multiplication that you have. So the cost of adding another input coordinates dimension for these neural fields is actually very cheap. And I think this is an important point that kind of like drives across like really creative research that happens in the field, where it's really easy to add these like additional input coordinate spaces, unlike with like traditional discrete signal representations, which kind of lets us prototype, things that we've never been able to do before. For example, this is one of my favorite neural field papers, which is NerfText. Basically, in this paper, they show that you can do kind of this like filtering, like level of detail filtering of your discrete of your signal by basically including as one of your parameters in the input space of your neural network, basically the level of detail or like the radius you want to filter your signal at. And they basically show that, just like this simple inclusion of like, like the level of detail into your the input space of your neural network, they're basically able to get pretty much equivalent results as something like integrated positional encoding, which has like a much more explicit control over the frequency spectrum of your signal in comparison to just like, just putting in this as like a input and just like forgetting about it. Yeah, that was like a super high level overview of like some of the properties that make neural fields interesting. But we talked a lot about the the interesting and like good parts of neural fields, but we also want to acknowledge that and also acknowledge that there's a lot of open problems in neural fields, which we'll actually talk about a lot in our upcoming sections and kind of like talk about solutions to some of these problems that exist for neural fields currently. Yeah, I don't know if you have time for any questions, but I'm happy to take any questions that might come up.
Yeah, we probably have time for a quick question while we are setting up the next presentation. I'm not sure if the microphones there work. So if you have a question, please just, they do? Okay, perfect. Yeah, we have a question here.
That's okay. Yeah, one question. You were using Pronouncers as a how, because actually Pronouncers does not use any neural network. So what does the definition of neural field extend to just the utilization of a certain set of parameters?
Yeah, so we use Plenastos as an example of, maybe I didn't make this super clear, but we use Plenastos as an example of something that solves a very similar problem to stuff that is solved with neural fields, but not with neural fields, but with discrete signal representations. So we would probably consider them to be non-neural fields, but they are also very interesting baselines to compare neural fields against too, because that's more of like that. Even though it came after neural fields, it's actually more of a traditional approach to it. So it's kind of like a nice baseline to compare against.
All right, thank you, Tawaki. All right, yeah, thanks, Tawaki, for that introduction. what we're going to do next, we're running a little bit behind. So we're going to quickly do a review or a review of features of the companion website to this tutorial, as well as the state-of-the-art report. We're going to do a quick review. We're also going to announce a community effort to kind of keep on top of all the new papers that are being published in this area. And we'd like to, we're really excited about involving all of you in this effort as well. So we're going to very quickly talk about that. So Or and me will do that in a moment. And after that, we get into the technical bit of the tutorial, where we're going to dive really deep into some of the neural field techniques that are being really popular these days. All right, so with that, I'd like to kind of point all of you to this website, which is a companion website for this tutorial, as well as for the review report that we've written. The URL for that is neuralfields.cs.brown.edu. Feel free to just log into that website, search for your favorite paper. It's likely that if you've written a paper in this area, it's in the website. But if not, we're looking for volunteers to kind of keep the website up to date. I'm just going to very quickly go over some of the features of this website and how you can use this for your research. So there's a couple of different features. There's simple search, advanced search, filtering, how to add a paper, and keyword-based search. So simple search, as the name implies, allows you to, so the website is kind of organized like a search engine. So you're presented with a search engine as soon as you log into the website. You can search for your favorite paper, your own paper, and so on. So you can kind of find this on the website. For each paper, you also see details on the abstract, video if the paper comes with the video, a link to the author's project pages, as well as a PDF of the paper on archive. The second is advanced search. So let's say you would like to do search based on a timeline view. So you'd like to kind of look at the timeline of when papers were published, and kind of situate papers depending on when they were published and so on. So you can do that as well. So here's an example of using our advanced features to kind of click on papers and see what are the details of some of these papers in kind of a timeline view. So I think this is really useful when you're working on the related work section of your future paper. So you can kind of get a bird's eye view of all the different papers that exist in this space. You can also filter by various different parameters. So you can filter by authors, institution, perhaps venue where it was published, date range where it was published, and so on. And again, for this, you can just click on the advanced search button, and then that kind of gives you different filtering options for how you might want to use the website. And then finally, adding paper to the website is really easy. It takes about 1 minute. So there's a Google form. You enter in some details such as your email address, a link to the PDF of your paper, a link to the abstract, perhaps. Sorry, not even the abstract. Just select your title, link to the PDF, and our system kind of automatically adds this to the website. As you can see, there's some stuff that happens in the background to kind of add these papers to the website. All right, you can also do keyword-based organization. So let's say you're interested in hybrid representations or manipulating neural fields, then you can enter this keyword onto the website, and you get papers that are filtered based on this keyword. And this is something that you might want to explore throughout the day in the tutorial as we go through the different techniques in neural fields as well as applications. You might just want to enter the keyword corresponding to that, and you'll find papers that are most relevant to the topic. All right, so with that, I'm going to hand it over to Or, who's going to talk a little bit about our neural fielder community that we are announcing today. And Or, take it away.
Thanks, Renath. So wonderful to see all those neural fielder potential members. So just really quickly, because we're behind on time, we're a small group of people. We put some initial effort into setting up the star review and setting up the website. Try to digest and organize, just digest and organize a lot of content that's out there, making it more accessible, probably easier to navigate. But now we're at a point where we're looking for, more hands on deck, and we'd like to make this into like a community. What that means, well, first of all, if you're in this room and you find yourself excited about the field, just use that QR code, just join the Slack channel. That's you already feel like you fulfilled like your first job as a fielder member. And then following up from there, we'll just, we'll announce on the Slack channel what are our future plans. Already, I can tell you we need some hands on deck to help us sort through these papers, remove duplicates, make the website, if you see any mistake, take responsibility and fix it. Yeah, that's mostly it. And going on from there, it's up to you guys. It's your opportunity to contribute, propose reading group sessions, whatnot. It's excited to see where this takes us. Thank you.
All right, thanks, Rod. Looking forward to seeing all of you on this Slack channel and where this community can kind of take us and how we can kind of stay connected to each other. With that, I'm going to hand it over to Yiheng, who's presenting his lecture remotely. All right, so Yiheng is the person who kind of led this work and the tutorial. He kind of waded through all these different papers. He's currently at Brown presenting remotely, but hopefully you'll find this interesting. And this also marks the beginning of part 3 of this tutorial, where we are going to start diving into some of the technical details on techniques for neural fields. And we start off with network architecture. So Yiheng, whenever you're ready, take it away, please.
Thank you. You can hear me and see my screen, okay?
It's perfect, thank you.
Great. Good morning, welcome. Let's start with a discussion on network architecture of neural fields. Traditionally, deep neural networks approximate functions with high-dimensional input domain, such as images or natural languages. However, neural fields operate over low-dimensional domain, such as R2 for images or R3 for 3D representations. They map low-dimensional coordinate values to outputs. As such, neural fields are a different class of function approximators, and they require different architectural choices. In this session, we'll touch on just a few of those choices. We'll first talk about neural network input encoding. This is also commonly referred to as positional encoding, since the input domain are coordinate values. Then we will discuss network activation functions and their implications on differentiability and the spectral bias. And finally, we'll briefly talk about network architectures that are invariant to rotational transformation. I'll start with input encodings. One of the problems with neural networks is that they are biased to fit lower frequency signals. This is also known as a spectral bias. For much of machine learning, this is actually something that can help with generalization. But for graphics and vision, however, this can be a problem. There are many high-frequency signals we would like to model in the real world, and our goal is to fit complex functions, often with as small of a neural network as possible. A number of different mechanisms have been proposed to address this problem. One class of these mechanisms are input encodings, namely positional encodings. Positional encodings embed coordinates into higher dimensional features. And often, the embeddings are axis-aligned sinusoidal functions at multiple frequencies. This is also referred to as Fourier features. They were originally used to embed positional data or sequential data, like natural languages, but they were adopted in neural fields as an input embedding, which can help alleviate the spectral bias. It's worth noting that here that one of our invited speakers today, Ellen, was one of the first researchers to introduce positional encodings to reconstruction tasks using neural fields. So be sure to tune in later this afternoon. Other input embeddings also exist. Random Fourier encodings are similar to positional encodings, but not axis aligned. Some other encodings use non-sinusoidal functions, but rather encode positions as Gaussians. And all of those promise different kinds of benefits. But right now, the community still doesn't really seem to have a good understanding of why these different properties emerge. There are also works which try to learn an optimal learning scheduling algorithm for positional encodings. SAPE, for example, learns positional encodings progressively in a coarse-to-fine manner, which then encourages the network to fit signal in a coarse-to-fine manner as well. Not all input encodings are meant for addressing the spectral bias. In integrated positional encoding, the sinusoidal embeddings are adjusted according to the cone size of rendering. This allows them to learn a multi-scale signal, which can be filtered and anti-aliased, similar to nerve text. This can be really useful for learning level of detail representations for computer graphics. So this wraps up positional encodings. And in short, using axis-aligned sinusoidal embeddings brought a breakthrough in the quality of reconstructed signals, while more sophisticated positional embedding schemes have been proposed since. And now let's talk about neural network activation functions. There are attempts to solve the spectral bias problem by using different activation functions. Activation functions are key components of a neural network. They refer to the nonlinearities placed in between neural network layers, and they are a key component of the universal approximation theorem of neural networks. Standard and popular activation functions include the sigmoid function and the ReLU function, which is essentially a gating mechanism. Many papers propose to replace these standard activation functions for neural field activation applications. For example, Siren replaces the ReLU function with sinusoids. Along with a careful network initialization method, sinusoidal activations allow neural networks to fit higher frequency functions better than ReLU activations. And importantly, sinusoidal activation functions also provide meaningful higher order derivatives. In comparison, ReLU activations produce piecewise constant or zero high order derivatives, making these networks poorly suited for solving problems with constraints involving derivatives. And in addition to Siren, Ramasingh et al. Studied a family of activation functions which can also fit higher gradients well, while also being robust to the neural network initialization scheme. Several works attempt to explain the behavior of these activation functions through both theory and empirical analysis. For example, we can see that Siren can successfully learn a high effective rank representation compared to conventional activation functions. In general, there's still not a lot of research being done in really understanding these activation and positional encoding functions. Most of the research done is empirical and somewhat ad hoc, and hence we think this is a really exciting opportunity for future work. There are also works which try to fundamentally change the structure of the neural network to learn representations, which are useful for various tasks like scene editing. For example, multiplicative filter networks is a frequency-space representation of signals. This allows for applications such as explicit frequency filtering of signals, as in Bacon. And finally, let's briefly talk about symmetric and transformation invariant networks. Here we'll focus on SO3 rotation transformation solving. Objects in 3D are naturally found in different orientations of poses. However, many neural networks assume the canonical pose for their respective tasks. Finding neural networks that can represent, segment, classify, or reconstruct 3D objects, irrespective of their orientation, is an important step to building general intelligence. In this example, we want the point cloud network to be able to recognize planes, whether they are pointing upwards or down. We want the network to be able to segment regardless of orientation. And we want the network to reconstruct the shape regardless of poses. Data augmentation is one popular approach, but what if we can build rotational invariance into the network architecture itself so that the representation is compact and scalable? A recent work, Vector Neurons, proposes a SO3 rotation invariant neural network. Vector neurons extend the dimensionality of neural network weights. Scalar weights are now vectors, and with vector dimension equal to the spatial coordinate dimension. And consider the vectorized neural network layer as a linear operator, as shown in the first equation here. And now consider a transformation on the input via rotation matrix R. And we can clearly see that the neural network layer is equivariant to the rotation in the input. The second equation shows that a rotational transformation on the input feature results in the same transformation on the output feature. So the vector neuron layer is rotationally equivariant. And building on equivariance, we can make the output invariant by multiplying together the input with the equivariant output. In other words, we can use the equivariant property to build completely rotationally invariant layer. This is just a bit more of linear algebra. Vector neurons multiplies together the input with the transpose of the equivariant output. The rotation is cancelled out via the transpose of the rotation matrix. And the final matrix product is invariant to rotation. Here are some results of the reconstruction task, where the rotational invariance property allows for meaningful reconstruction, even when the input point cloud is rotated. So this wraps up our discussion on network architecture. This is a very broad subject, and we've only touched on these 3 topics in this section. But please tune in later today for related topics such as hybrid parameterization and generalization. And finally, for more discussions on positional encoding, activation functions, and other interesting architectural choices, please search in our web database. And with that, I welcome some questions.
Thank you, Yihan. We have plenty of time for questions. We have a question here.
Thank you so much. So I was real curious about the structure bias. Can you talk a bit more about why this happens?
So just to repeat the question for our virtual audience, the question is, the questioner is interested in spectral bias, and Yihan, if you could elaborate a little bit more on spectral bias.
Okay, so for spectral bias, I'm not 100% the expert, but it's a well-known phenomenon that neural networks, in our case, multilayer perceptrons, are biased to fit low frequency signals. So in application, you'll see if you use a multilayer perceptron to fit an image, the image will turn out blurry. So that's the higher frequency content lost in the representation. And that's obviously a problem for vision graphics where we want high fidelity signals. So that's one of the core problems that people aim to solve when designing 3D representations. And 2 ways that have been proposed to solve that problem have been activation functions and positional encodings. And interestingly, both of them initially at least involve sinusoidal functions to help recover that high frequency content.
Just to add on to what Yiheng said, like a part of it is also just the optimization of these neural networks. It's not going to be perfect because you're going to be in these local minimums. And basically, like, you know, you need to separately think about the actual capacity of the neural network. What it's capable of is different from what the neural networks tends to achieve. So with basically a perfect optimizer, you can probably squeeze out a little bit more frequency content out of these neural networks. But with the current optimizers that we have available today, we're not really able to do that, especially if you want to do it like, you know, fast and stuff like that.
So I understand the spectral biases that has to do with the aspect of spectral. So I'm wondering, like you're saying, does that mean that the loss landscape?
Yeah, I think so. And I'm sure that these like different like positional encodings and stuff like that just change the loss landscape in a way where it's like more suitable for fitting these higher frequencies.
I see.
And I think some of the work we showed on like some of like the effective rank representations and stuff like that, kind of like do like a similar analysis on like the eigenvalues essentially.
We have time for a couple of more questions.
Just curious if people have done work on modeling the variations within the same class, such as you can model a book in closed position, and like when you open it, like, can you model the variation of the shape?
So to repeat the question for our Zoom audience, the question is if you can model objects in different shapes, is that, or different states? Yeah. Different articulations, perhaps, right? Yes, is that what you mean? Yeah. Okay, thank you. Did you get the question here?
Was it a question on using the same neural fields to model objects in different articulations?
That's right, yes.
Yes, there's actually at least one paper that investigates that. I think it's called articulated SDF that does exactly that. And later on this morning, we'll talk about ways to generalize neural fields. And one of the ways we can generalize without spoiling too much of the content is to condition the neural field on some explicit or implicit parameter. And you can imagine you can condition the neural field on, for example, the angle of articulation. And then you can create shapes that's articulated with the same neural network. But more on this later.
And maybe just to add to that, human bodies are, of course, a great example of articulated shapes. And of course, there's been extensive work in trying to use neural fields to model human bodies. And in fact, Shunsuke is going to talk quite a bit about that this afternoon. So if you're interested, you should definitely join the afternoon session.
Thank you.
Thank you. I think the last question, we are probably going to take it from Zoom. So let me just quickly check. All right, so we do have one question on Zoom. Prashant Raina asks, do you need major architecture changes depending on whether you're looking outwards or inwards at an object? Ihan, do you want to take that?
Sure, yeah. Again, I think a few papers have looked into this. One of the ways to solve this problem is to reparameterize the input coordinate space. So, if we think about ways we can manipulate neural fields, again, not to spoil too much of the content later on this morning, we can edit the network architecture and parameters itself, or we can edit its inputs, and inputs are the coordinates. So when we're looking outward, the coordinate can be infinity. When we're looking inward, it's bounded. Obviously, there are clever reparameterizations to help us better recover the network capacity. So to what Tawaki has said earlier, with a perfect optimization network, we wouldn't have to do this. But currently, with non-perfect optimizers, we have to think about ways we can reparameterize the input coordinates so that we can better utilize the capacity of the neural networks. So yes.
All right, thank you, Ihan. So with that, we are actually back on track in terms of time. So we do have 15 minutes for a coffee break. So see you all back in this room at 10:30. All right, so welcome back, everyone. So we're going to continue our tutorial journey. We started off with techniques in neural fields. Ihan gave a pretty nice presentation about network architectures used in neural fields. We're going to continue the technical bit with hybrid representations next, and Tawaki is going to talk about hybrid representation. So Tawaki, take it away.
Hi everyone, it's Tawaki again, and I'll be talking about hybrid representations. So in the previous section, Yiheng gave a really nice overview about network architecture. But a lot of these tricks that you learn about network architecture, like these positional encodings and activation functions, are kind of in the context of using a global neural network to parameterize your scene. And oftentimes, this neural network that you're using to parameterize your scene can be very big. And this can be problematic, especially if you're concerned about performance and stuff like that. Because if you, for example, look at how you render these volumetric representations, usually it looks kind of like this, where it's like you have like a eye that you want to render it into, and you have like a ray shooting out of it, and you want to render like a bulldozer or something like that. You have to basically take a bunch of these samples along that ray, execute the neural network at every point along that sample, and aggregate it. So this basically means that for every pixel of your image that you have, and your image might be high resolution, this could be millions of pixels and stuff like that. Basically, for every ray, for every pixel, you have to do this like rendering function, which takes a lot of samples. And yeah, basically, you might imagine, if you have these millions and millions and millions of neural network, maybe I should move this somewhere else. If you have millions and millions and millions of these neural network queries, it might get infeasible at some point. Let me just move this also. Yeah, so we don't want these huge neural networks. So basically our mission is basically how do we get away with using a much smaller neural network? Because if you just make the neural network smaller just naively, you're just gonna basically get, you know, much worse results essentially, because you're not gonna be able to fit as complex functions. We do this with something called hybrid representations, where basically you want to replace all the parameters of your neural network out of the neural network into this something called the feature grid, where you basically like put a bunch of parameters inside there. I'm gonna explain that a little bit more. So this is called hybrid representations. It's kind of a little bit akin to something like positional encoding, where in the goal of positional encoding is to take your 3-dimensional or 2-dimensional or whatever the dimensional, relatively low dimensional input coordinate space and lift it up into a higher dimensional space. The feature grid does also exactly that, where basically, you know, you might take like your 2D coordinate in this case, and you basically find the grid points that correspond for the specific coordinate, and then basically interpolate feature vectors that exist on each of those corners and get your higher dimensional feature vector out of it. And basically, after you get this feature vector, which is embedded into this higher dimensional space, you can feed this into a neural network. And we basically find that, you know, with a lot of these feature grid-based methods, you can actually get away with using very small neural networks to do this kind of to represent really high frequency functions. And this is a lot more efficient than, for example, executing an entire neural network, because even though you move a lot of parameters out of the neural network into this really big grid structure, at any point, you're only looking at maybe like a very localized window of features. So you're not going to have to do a lot of compute actually in most cases. This of course depends a lot on the grid structure and stuff like that, which I'll also talk about. And the another important bit here is that you want to basically condition your tiny neural network with this feature somehow. I'm going to leave this part purposely vague for now, because basically, like, you know, in the later section, Vincent will talk about generalization, and this actually has to do a lot with, you know, how you take these features, these latent vectors, and condition your neural network using it. And in some special cases, you might actually have no conditioning, and you might actually be interpolating entire neural networks directly from your grid structure, which is also pretty cool. Just an interesting historical tidbit is that, you know, the history of hybrid representation is actually pretty long. It's even longer than the, you know, like the current modern history of the neural fields. Basically in 2013 at SIGGRAPH, like there was this paper called Global Illumination of Radiance Regression Functions. And they basically said that if we take this, like, you know, grid of like neural networks, so basically, you know, you have like a big grid of like, you know, neural networks for each spatial region. They basically said that this is a pretty good way of like, you know, fitting radiance functions and like compressing them and stuff like that. So this is actually like an area that has a lot of history, and like this is like a very cool paper that was very ahead of its time. This came out in 2013. So anyways, there's a bunch of different, so like we basically have this like feature grid where you want to basically store these like different parameters on top of some data structure. And so the important thing with these like feature grids is the actual choice of your data structure that you want to use. So one simple example of a data structure that you can use is uniform grids. Basically, this is something like, you know, like an image or like something like a 3D dense voxel grid or something. And this is nice because doing access into these like data structures is super fast. If you basically know what your indices are, you can just like directly query these like data structures. And it's super easy to implement. You know, there's stuff in like PyTorch that's already built in to do this kind of stuff. And there's also established operations you can do on this stuff like convolutions, and like it has a very simple topology, so it's easy to generate. But the big drawback of these kind of uniform grids, similar to like the traditional discrete signal representations we talked about earlier, is that they can be very expensive in memory and bandwidth. And basically the other thing here to note is that these uniform grids are oftentimes uniformly spaced, which means that you're basically also limited by the Nyquist frequency. Nonetheless, these uniform grids are super useful. And this is one example of a CVPR 2022 paper that uses these uniform grids for a hybrid representation. This is BlockNerf. And they basically show that by having this like grid of neural networks that fit specific parts of the scene spatially, they're able to represent, for example, an entire block of San Francisco using these grids of nerfs, essentially. So you should definitely go check this paper out. The results are really, really nice. Another example of a data structure that you can use is a sparse grid, which is very similar to a uniform grid. But instead of having, you know, features allocated densely everywhere, you only allocate it where you want the features to be. So this can be a lot more memory efficient because you can basically prune out your grid and basically remove any areas that you don't really care about. And even though, it's a little bit more complicated data structure, but, people have designed algorithmically efficient access methods for these, usually they're like kind of like tree-based data structure. So it's relatively easy to access. And then people have also like proposed a bunch of like GPU compatible optimized data structure for this kind of stuff. But the con here is that, obviously just by adding this like tree structure onto your data, it all of a sudden, becomes really hard to, manage this complex data structure. And especially in like real-time graphics applications, this can be a pretty difficult issue to manage. And the other thing that's important is that because you have this like, discrete tree hierarchy that you have to deal with now, if you want to, for example, generate these sparse grids from like another neural network or something like that, that's actually really hard to do because the topology is somewhat dynamic and data dependent. So it doesn't have like a, like a regular structure to it. So it's a little bit hard to generate. And that's like an open question right now still. You're still limited by the Nyquist frequency just because these sparse grids are oftentimes uniformly spaced. And another thing is that, it has a sparse support region. So by support region, what I mean is that not every point in space actually has enough value associated with that. So we saw that you like neural fields and stuff like that. Basically, you see that for any point in space, you can query a neural network. But with a sparse grid, with any point in space, you cannot necessarily have a value in the sparse grid because it's just undefined. And this can be actually a big problem in like stuff like rendering and stuff like that, where you might want to do like shadow computations from like places that are open space, but still space is space, so it's still defined. One example of a paper at CVPR that uses this is a nerve fusion. In this nerve fusion paper, they basically show that using this like sparse feature grid, they're able to do like online real-time reconstruction with these like neural fields, and the results also are in this paper are also really nice. So you should definitely go check it out. Another option you can use, people don't really think about these things as grids, but you can also use point clouds of features to condition your neural field. And basically the idea here is that, you might have like a point cloud, which can be a floating point coordinate. So it's not necessarily integer aligned, but you can be anywhere in space basically. And for any point that you want to query from this data structure, you basically, for example, execute some kind of kernel function. For example, in this case, it might be like a simple radial Gaussian function to basically aggregate, features that are nearby, or it might not even be nearby. It might be all features or something like that to basically compute every point in space. There's a lot of differences you can have in like the choices kernel function you have and stuff like that. But basically, like the nice thing here is that you're not limited by the Nyquist frequency because these grid points are not uniformly sampled. So you can basically put it close together if you have higher frequency, farther together if you have low frequencies. This can be densely supported in space because you can like define it as if you always like have like a kernel function, then you can just like have output 0 or something like that if there's no points nearby. And it's very expressive. But the con here is that the actual design of this kind of data structure oftentimes depends a lot on your kernel function. So oftentimes you're going to make the assumption that your kernel is localized, so you only care about the points nearby you. But to get those points that are nearby you, you're going to have to design complex data structures for fast access and interpolation, or otherwise you're going to have to do like an ON operation and look at all the points that exist every time you want to query this. Yeah, it's just heavily affected by the choice of kernel, so it's hard to generalize the properties of this specific grid structure. One paper that showcases really the effectiveness of this kind of approach is DCC-DIF, also at CVPR 2022. So you should definitely go check it out. Basically, the idea here is that instead of doing like basically like a one way of doing it is like interpolation from a latent grid that might be sparse or dense or whatever. And basically, in their case, they have these like grid points where you can move them around in floating point coordinate space, and you're basically interpolating these continuous point clouds of features. And they basically show that in comparison to something like Englod, which basically uses a sparse grid-based approach, they basically show that with using 3 times less parameters, they're actually able to get equal or better quality in terms of like geometry reconstruction with these neural fields, which is pretty cool. So you should definitely also go check this paper out. Another example of a data structure that you can use is a mesh. This is very much like the point cloud, except you also have connectivity information. And basically this makes a little bit of some of the data structure access a little bit simpler and the interpolation simpler and stuff like that, because you can just use like, barycentric triangle interpolation and whatever. Similar to the point clouds, this is also not limited by Nyquist, so you can get away probably with less features, just like they showed in the previous paper. And the nice thing here is that you can use the rich sets of tools that are available to you in mesh processing. So this is stuff like, like finite element analysis and like all this stuff for like animation and like simulation. And this is really nice because if you want to, for example, manipulate your neural theater or something like that, you can just basically manipulate your deformable grid or something like that and do a bunch of the cool stuff with it. The cons of using this kind of grid structure is that, it's a mesh. So basically every time you work with a polygon mesh, it comes with the difficulties of working with meshes. And yeah, it's also like, the data access can be non-trivial depending on your implementation, especially in 3D where you have to do like, for example, like a tetrahedral grid or something like that. A cool example of a paper, again, that from CVPR 2022 that uses this kind of like a setup is nerf editing. So strictly speaking, this is actually not a feature grid because I think their tetrahedral grid is actually holds displacement values. But nonetheless, they basically use this like a deformable grid of like tetrahedral meshes, volumetric meshes, to basically show that you can edit your nerfs and basically manipulate them, move them around and stuff like that. And this is also really cool work. So beyond the unstructured, point cloud type grids, you also have, a little bit more exotic stuff like multiplanar images. So multiplanar images, some people in graphics might call these like triplanar texture maps or multiplanar texture maps. Basically, the idea here is that for a given 3D point in space, you have these like planes of like images that, might be on some axis or something like that. And the idea here is that taking your 3D point in space, you project it onto these planes that exist in space. And once you project it onto the planes, you can then just do simple bilinear interpolation to obtain your features, which is really nice. And stuff like bilinear interpolation is well supported in hardware. So this is also, can be potentially very hardware accelerated also. So the nice thing about this kind of multiplanar image setup is that they are much more compact than 3D dense grids, even though they are still like a dense grid in some kind of sense. They're very compatible with 2D pipelines. So there's a bunch of different papers that kind of like use this to their advantage. But one con is that, there's kind of like this resolution bias that exists on each of these plane axes, just because, for example, if you think about like a plane on some kind of an axis and you have a, high resolution image there, if you only have like a single planar like image map for your 3D space, if you go to like any other direction, you're not going to have a much, spatial resolution available to you that you can use. So the orientation of the plane probably matters a lot. And maybe even the number of planes also matters a lot too. And all of a sudden, once you add a lot more planes, it becomes a lot more complex to manage. One paper that uses these like multiplanar images in a really unique way is EG3D. This is also a CVPR paper. The idea here is that they basically use StyleGAN's generator, which is a convolutional neural network that outputs these feature maps in 2D. And they basically, reshape them such that you can use them as these like multiplanar texture maps or feature maps for a neural render that uses that 3D volumetric information to then create a multi-view image. And then basically they use like a discriminator to like actually learn this like learn like a 3D compatible StyleGAN kind of thing. And the results are really good here also. So you should definitely also go check it out. There's also stuff like multi-resolution grids. Here I kind of use the word multi-resolution, kind of like flexibility. There's not like a concrete thing necessarily, but basically I mean anything where it's like, you might not be interpolating necessarily from like, a single set of features, but maybe like features at multiple different resolutions. So in this case, you can kind of see that like you might be interpolating from the box that you're in, but you might be also interpolating from the bigger box that you're in. And they also might be hierarchical, whereas like, you have multiple levels of these multi-resolution grids that you aggregate from. The nice thing about this is that this kind of pipeline is very compatible with stuff like streaming level of detail for like people who are interested in like, streaming graphics and stuff like that. And empirically, it kind of seems to also contribute to like stable training, where it's like, if you just increase the resolution of your grid, you might just think that your signals will get, nice and also like a high frequency and detailed and stuff like that. But we kind of see that like you also need like low frequency information embedded in your grid also, such that you can actually stably train these things. They're also kind of nice in comparison to something like sparse grids, because they usually come from a wider support region just by having like these lower frequency grids also that you work with. But because you have to store multiple resolutions of your grids, it's much more memory. And usually there's more complexity involved in actually managing these multi-resolution hierarchies. One example of a paper that utilizes this kind of thing is Engelad, where basically the idea is that with these multi-resolution grids, you can have basically like level of detail hierarchies of your object, and you can basically use this for like streaming level of detail or like compression and stuff like that. Another really cool work is hash grids. So hash grids are a little bit more involved in maybe a little bit harder to understand. But basically the idea here is that if you look at like your typical dense grid parameterizations, for each of your grid points, you actually explicitly store some kind of feature vector in each of those points. The idea of hash grids, on the other hand, is that you don't actually store any features on your grid. Instead, for each XYZ coordinate or XY or whatever dimensional space coordinate of your grid, you basically feed this through a hash function. This hash function will basically take your XYZ coordinates and output a random number between 0 and n, where n is like any number that you choose. And basically the idea here is that using these hash functions, which is basically like a random number generator essentially, you basically take from a finite size code book and you query a feature out of that code book and put it on your grid on the fly. So the benefit here is that you can just like, essentially you can like disaggregate your resolution from the memory cost, because you can have like a super high resolution grid, but because you have like a finite size code book that you can just like get your features from, you can basically like, completely like disaggregate it and just say like, I want a code book of size 16, but like maybe I want like a super high resolution grid or something like that. There's no complex data structures to manage here, just because, you don't have to have like an octave or anything. You can just like, all you need to do really is like know where your grid coordinates are basically. And the other really nice thing is that you can get really performant memory accesses if your code book is small enough. Just because you can like disaggregate your resolution from your code book size, you can basically design your code book around your hardware. So if you have like for example, like, the cache size of your GPU or something like that, you can design the code book size exactly such that it fits in cache or something like that. The con here is that, with these you might imagine that, if you just use a random number generator to get random features, you're going to get a lot of collisions. And there's no guarantee that, for example, some point in space that gives you the same hash as another point in space actually represents the same thing. So basically, to deal with these like hash collisions, you also need to have multi-resolution and oftentimes large code books to actually perform this like collision resolution expectation. Another thing is that features are not spatially local, meaning that different parts of the scene might be pointing to the same code book. So if you, for example, want to generate your code book or do operations on that code book, all those operations will propagate to the entire grid and not just like a single local part of it, which is what you get with like, for example, like a typical or usual grid. One work that uses this kind of like setup is HashNerf or Instant NGP. Instant NGP basically utilizes that fact that I mentioned, where it's like, you can disaggregate your code book size from your resolution size to encode really high resolution radiance fields, but something that also trains in real time and also renders in real time. It's very performant. So this is an example where the grid architecture really contributed to the actual system performance. Lastly, actually it's not the last one, but one more, the recent kind of idea that also exists is the codebook grid. So instead of so in HashNerf using the XYZ coordinates, you kind of query into this codebook. But the problem there is that because you have these like random assignments to your codebook, you're gonna have to get either super lucky or have these like multi-resolution hierarchies to deal with those collisions. Another idea you can have is that instead of like storing feature vectors at your grid coordinates, you can actually just store indices at your grid coordinates. So this is still a little bit more compact than storing feature vectors entirely. You're just storing like an integer or something like that. And similarly to like the hash stuff, you can just like decide that I'm only going to store integers from like 0 to 256 or something like that. So you can also disaggregate your codebook size from the resolution. And basically the idea here is that because you have explicit control over the indices that you store, you can basically say like, if this part of the image has like, in this index 0 and represents the same kind of content as a different part of the data, you can kind of like say that, I'm going to explicitly say that these are going to be both index 0. So this kind of like, explicit control over the indices basically means that you can get away with a much smaller code book. You also have explicit control over the spatial features, basically. But there's several cons with this approach also. You basically need a mechanism to differentiate through this indexing operation, which is this like discrete operation, which is hard to make differentiable. And if you make them differentiable, it can be computationally expensive and also memory expensive. And we use hashnerf to get rid of that data structure, but by reintroducing these indices into these grids, you actually have to reintroduce the data structure to actually manage the indices. So that's another problem with these kind of approaches. A paper that uses this kind of codebook grid is variable bitrate neural fields. Basically, the idea here is that you can learn these super compact NERF models by using this kind of index learning. And they basically show that like there's like a better trade-off that you can get by using this kind of like setup as opposed to using something like hashes, for example. Lastly, I'll just talk about bounding volume hierarchies. These are basically like, like a hierarchy of like, primitives that encode like a specific like feature vector or neural networks entirely. And this kind of thing is nice because, BVHs are like an object that is very popularly used in computer graphics. So there's a lot of specialized GPU compatible algorithms for BVH, not just traversal, but also for generation. But the con is that, differentiability with respect to these primitives might be non-trivial. But yeah, anyways, there's a bunch of papers that use this kind of stuff, but unfortunately, I couldn't find any CVPR papers that use this. So if anyone knows any, definitely let me know. Yeah, so I talked about a bunch of these different types of data structures, and you might be kind of overwhelmed by the number of data structures you can choose from. And you might ask yourself, how do I even choose like what the best data structure I should use is? And yeah, basically all of these different kinds of data structures, and maybe the choice of not even using any data structure at all, basically has all these different design trade-offs. So these design trade-offs might be something like, the quality of your reconstruction or the size of your actual representation, or maybe the speed of inference, which is the motivation that I talked about in the beginning. But it's really hard to like reason about this because like, there's, in addition to just like the three basic things you might think about, we also looked at a bunch of pros and cons about all these data structures. Stuff like, the spatial support or like the entropy of that representation or like compatibility with existing tools or ease of implementation and stuff like that you have to think about. And I think the big takeaway here is that like, there's not really like a single silver bullet that will solve every single problem that exists for neural fields. So you basically have to look at your application specifically and kind of like choose the tool that makes most sense to you. And hopefully some of these like pros and cons that I lined out for each of these data structures can help you guide that decision of like choosing like which data structure you want to use for your application. And yeah, I guess like in general, like with most feature grid methods though, what we see though is that, compared to like a basic like, global method, we basically see that we're both able to like, basically increase the quality and also make them fast with these like hybrid representations, which is super compelling, I think. But I think an open research question we have is like, we have this like kind of curve that we can draw by like, moving more and more of the parameters out of the NERF into your feature grid. But the result is that you also have to increase your total parameter size. So kind of like, the open research question is how do we fundamentally shift this like trade-off curve up to the top left so that we can have, much more compact, but also high quality and also fast neural field architectures and stuff like that. I'll share quickly share a few of open research questions that might exist with these hybrid representations. One thing is that, in the graphics world, people have been working on, voxel-based systems for a long time, and people have been trying to make voxel-based systems work for a long time, but they have a lot of issues, which I think neural fields could be a potential solution to. But nonetheless, there's a bunch of insight and research that has been done in voxel-based graphics engines that are not really utilized too much in the neural fields design space right now. So one example of this kind of work is gigavoxels, which basically use like, it's kind of like a sparse tree, but instead of like storing one feature per like node, you have like for example, like a n by n cubed grid of features. And the idea here is that you can amortize your memory accesses and you can do stuff like, encoding and transform coding to like compress it and stuff like that. And all this stuff is like, nicely laid out in all these papers, but they're not very used in like current papers. So I think this is like a really nice source of inspiration that we can look into. The other thing is that, we talked a lot about these like different complex data structures and tree structures that we had to manage. And these can be like quite difficult to like employ in like a generative setting. But papers have been trying. For example, one example of this kind of work is Shapeformer, which tries to like generate that sparse hierarchy or a sparse tree directly. But I think there's a lot of open research questions that still exist in this space of like, how do we generate like, a sparse tree that from like, for example, like an autoencoder or something like that. Yeah, just like just to conclude, there's like a bunch of like stuff we show. It's all about basically balancing different trade-offs that you have with different data structures. There's no single solution that will work for everything, so you kind of have to look at your application specifically. And I think this is also kind of like an open research question, but there's not really like a holistic comparison of all these different approaches that exist in the current literature. And this is partially an engineering effort because each of these data structures require, implementation and stuff like that. But I think it's really important and really valuable question if, people can start looking at, for example, what is the fundamental difference between like, using like an unstructured grid versus like a regular grid and stuff like that. And yeah, with that, I'll conclude and I'm happy to take any questions that might come up. Thank you.
We can take one or two quick questions while we set up for the next speaker. There are microphones here and here.
Can I ask some questions?
Yes, go for it.
I think the introduced structures are all for the static sets. And I think there is some more better structure for dynamic sets there. Can you introduce any proper structure for dynamic sets?
Yeah, so the question for the Zoom people was a lot of these things we talked about in the context of static scenes, but what about dynamic scenes? Do we have the nice data structure for dynamic scenes? And it's a really good question. And I think it's also an open question. There's actually like, maybe like 3 papers that came out in this last month that kind of tried to use like hybrid representations for like applications like dynamic and temporal nerves and stuff like that. And I think the takeaway from there is that, there's the same kind of difficulties that you see with these, like a lot of these pros and cons kind of show up there too. One example is like, if you have like a sparse tree, for example, doing that in like a temporal setting is very difficult because encoding that difference in topology that occurs from your temporal data is actually really difficult to express with these sparse trees. So oftentimes most people actually opt to use something like, very dense representations and stuff like that to actually encode these temporal nerves. So basically like what I see in the current literature is basically like, it's like a dense grid of like 40 dense grid where basically like for each frame you might have like a dense feature grid or something like that. But something that a lot of people are also working on is that, you might also have like this, like there's this whole idea in like the dynamic nerve world of like a canonical representation where it's like you have like one frame, one feature grid or one neural network that serves as a canonical frame. And what you're encoding from each of these different frames is the motion vectors into that canonical frame. And this is very similar in motivation to a lot of the video encoding stuff that exists, where basically the idea is that with a lot of video encoders that exist, you want to estimate motion vectors, you want to motion compensate your next frame based on the motion and then encode that diff. I think this kind of like intuition is already being used in a lot of these hybrid representations for temporal data. But I think there's a lot of existing works that you can look at, and especially I think you can get a lot of inspiration from like video codecs and stuff like that as to how do we design like really efficient, memory efficient and performant data structure for temporal data. And I think it can also be utilized with all these like different hash nerves and like all those different more exotic data structures as well for temporal data. So I think it's a really exciting research direction right now.
I would also have a question about the generalization that you mentioned in the first talk. What do you think about the
regularization that to be in these hybrid representations where we want to model how you hybrid representation.
Yeah, so for the Zoom people, the question was, we talked a lot about regularization for these global neural network methods. So what about these like hybrid representations? Are like regularizations useful in these contexts? I guess like the answer to this is that I think nobody has like a really good idea of whether or not the same kind of like inductive biases that you see with global neural networks actually carries over to these like hybrid representations, where it more and more looks like actually like traditional discrete representations, which probably does actually in fact mean that like you need like for example like you need, similarly to how you need regularizations for discrete representations, you'll probably need regularization for these hybrid representations. And I think one evidence that points towards like why this might be the case, or not why this might be the case, but the evidence that points towards this actually being the case currently is that if you look at something like, these multi-resolution hierarchies of features, those like having that like, kind of inductive bias of having like, multiple resolutions from your grid structure seems to actually make the training much more stable, which you can hypothesize that because, these like, if you were to have like a single discrete feature grid that's super high resolution and stuff like that, it's not gonna, you're gonna need to have like, really good regularization design and stuff like that to make that converge well. Whereas like, people have been kind of like ad hoc proposing stuff like multi-resolution hierarchies to kind of like try to deal with this. So I think, yeah, my actual answer to this is that I don't think there's any current works, or at least I haven't seen any current works that try to investigate this specifically. I think this is like super exciting, also another super exciting direction to look into for these hybrid representations, seeing what kind of inductive biases there are, and like how you can regularize it so you can learn better and stuff like that with these hybrid representations. Probably this last question.
I would like to ask if you know of any way that if using like non-hardened by pure neural representation to avoid this issue where when you're that updating your network by seeing one point in space, then the representation of the whole scene changes, and that's something you probably don't want. And that's something that is good from hybrid representation, but you know any work that tackles that problems within the pure neural representation.
So you mean like you're saying that basically you have these hybrid representations and you can kind of like spatially disaggregate it, by you asking whether similar kinds of work exists for like pure neural networks. Yeah, I'm not really aware of any works that do that kind of stuff, but there's actually a really interesting work in like some like alternative like positional encoding schemes and like activation functions. A lot of these are based on like Gaussian functions and stuff like that instead of having like sine waves. So this is kind of like the same as like the whole story with like, wavelets and stuff like that. Basically, instead of like encoding your signals with these like, sine waves, which has like global support, if you like, encode them with like wavelets that have like local support, for example, then basically you can like disaggregate your signal much easier. So I don't think there's any research or like existing work in this, but I imagine that with a lot of these like, alternative like Gaussian looking or like more spatially local activation style functions and stuff like that, which those papers also propose that these have like similar properties to these spectral embeddings. I think those works probably, this kind of like spatial aggregation is like spatial disaggregation is probably much more feasible with those kind of applications. But yeah, I don't think anyone has proved that this is an idea that actually works.
Thank you very much.
Yeah.
All right, thank you, Tawaki. So what we've seen so far in part 3 of this tutorial is we've talked about architectures and we've talked about hybrid representation. So we're going to continue this journey looking into 3 more techniques that are fundamental in neural fields. And the third one in this list is forward maps. And we have Zhong who's going to join us again to talk about forward maps next. So I'm going to stop sharing, and then Zhong, if you want to unmute yourself. And
Great. Can you see my slides and the audio okay?
Your audio is good, and we can see your slides. Take it away.
Great. So welcome back, everyone. In this section, we're going to talk about differentiable forward mapping functions. They are a key enabler of all applications of neural fields. They make things such as 3D reconstruction from 2D images possible. This is a perfect time for us to introduce the general framework for using neural fields to solve inverse problems. Here again, we will use 3D reconstruction as the motivating example. We first sample the coordinates, which are the inputs of the neural network. The neural network predicts the reconstructed signal, and the reconstruction is then rendered into what we can measure. And the things are what we can measure with real-world sensors, such as RGB images. In inverse problems, we're given sparse, noisy, and often dimension-constrained information from real-world sensors. However, we want to recover a rich underlying representation from these limited observations of the real world. For example, how can we reconstruct 3D geometry from sparse 2D images, which we can measure? Then we need a differentiable forward mapping function, mapping the reconstructed signal to the sensor signals. And this is the differentiable forward map. In visual computing, this becomes differentiable renderer. And with that, we can now supervise the learning of the reconstructed signal with limited sensor signals. And we'll refer to the idea of the reconstruction domain and the sensor domain often throughout this section. Let's take a look at specific examples. We can render an SDF, a sign distance field, via sphere tracing and obtain screen space, normal map, and depth map. We can volume render a radiance field into an image or depth. We can also perform meshing operation on SDF to obtain a mesh. And for medical imaging, we can transform CT or MRI images into raw sensor measurements via radon transform or Fourier transform. The middle column here is our forward mapping function. Now, this is the complete picture. A key insight here is that finding a new application in neural field research is equivalent to defining a new forward mapping function that connects the two domains that haven't been connected before. For each inverse problem here, finding a solution via gradient descent is possible only because a differentiable forward mapping function is defined and computationally efficient. One particular type of forward map is differentiable rendering. This enabled the reconstruction of 3D signals from 2D images only, which was no less of a breakthrough in the vision community. The topic is also often referred to as inverse graphics for that same reason. A 3D representation is differentially rendered into 2D images, where supervision is available as RGB images. Differentiable rendering itself is also an umbrella term. Some concrete examples include volume rendering, surface rendering, such as sphere tracing, and neural rendering. Each rendering method comes with its own trade-offs and assumptions for the underlying scene representation. Now let's look at it in more detail. In volume rendering, each point along the camera array can potentially contribute to the final color of the pixel. This is suitable for modeling translucent materials as well as smoke or fog. And importantly, it also makes the optimization landscape smooth. In comparison, in surface rendering, the scene is assumed to consist of hard surfaces only, and only one point along the array contributes to the final pixel color. One example of the surface renderer is differentiable sphere tracing. And both surface and volume rendering have their strengths and weaknesses. Volume renderers create spurious fog and inaccurate surface geometry, while the reconstruction with differentiable surface rendering is more difficult and often requires ground truth object mass. Several works have investigated into combining the two to combine their benefits and mitigate their weaknesses. And one final type of renderer is one that involves neural networks as part of the rendering pipeline. We call this a neural rendering. Some works use convolutional neural networks to render a screen space latent feature map into RGB images. Another example is scene representation networks, which uses an LSTM network as the ray marcher. Another differentiable forward mapping function in computer graphics is the rendering equation itself. The rendering equation is trivially differentiable since it only consists of the elementary mathematical operation. The sensor domain is the rendered image captured by cameras. The reconstruction domain is material properties such as normal, roughness, specular, and diffuse albedo. With the rendering equation as the differentiable forward map, we can now recover material properties from camera images. However, even though this is possible, the solution is still under constraint, which is a common issue in inverse problems. Data-driven learning approaches can therefore provide prior information to help this task, and we'll dive into that in more detail in later section today. And for more details on the various forms of differentiable rendering, it's a great review project with much more thorough treatment on this topic. They are state-of-the-art in neural rendering and advances in neural rendering. Now looking more broadly beyond traditional computer graphics, medical imaging is another application that is concerned with solving inverse problems where the sensor signal is very constrained. In CT and MRI scanning, only sparse signal is available, and we would like a full 3D reconstruction of the human body while minimizing the human body's exposure to radiation. The neural fields reconstruct the 3D representation we are interested in recovering, and here labeled as the image domain in the middle. While the sensors can only measure sparse signals in the projection domain for CT and in the frequency domain for MRI. The forward mapping function for CT is radon transform, and the forward map for MRI is Fourier transform. You can see that the framework is completely analogous to 3D reconstruction in computer graphics. The image domain is the reconstructed 3D representation, and the projection of frequency domains are the analogous to camera images, except in this case, the camera, quote unquote, is CT and MRI machines. And finally, another form of differentiable forward map is differentiation itself. The reconstruction or the solution to the inverse problem is mapped to its derivative via differentiation. As we've introduced in network architecture, neural networks that have well-defined high-order derivatives can be used to parameterize solutions that involve partial differential equations. One prominent example in computer vision graphics is the iconal equation, which is highly relevant to our community. And consider a sign distance function parameterized by a neural field. A valid sign distance function must satisfy the iconal equation, which means that the gradient of the neural field must be unity everywhere. The forward map is the derivative operator, and the reconstruction domain is a sign distance function, and the sensor signal is simply 1. We therefore enforce the gradient of the network to equal 1 via an auxiliary loss term, so that we can ensure the reconstruction we desire is a valid sign distance field. More generally, this supervision via derivatives belongs to a broad class of problems in which the solutions are constrained by its partial derivatives. In other words, neural fields allow us to find numerical solutions for partial differential equations in a data-driven manner. This is especially relevant to the computational physics community, since many real-world physics phenomena are governed by differential equations. Neural fields offer a new way to parameterize the solutions to physics-based problems. And one of our invited speakers this afternoon will dive into this topic in much more detail. And finally, there's one trivial class of forward mapping functions, which is simply the identity operator. And this is when the reconstruction and the sensor domains are one and the same. For example, if we're simply asking a neural field to memorize an image, an audio clip, then the reconstruction domain and the sensor domain are one and the same. In other words, the ground truth signal is given during training. There is no inverse or reconstruction problem here. The forward mapping function is simply identity. One final comment before we open up for questions. When we think about new applications for neural fields, the key question to answer instead is, is there a function that can map reconstruction to the available sensor signal? And is it differentiable and computationally efficient? If we have a good answer to that question, then we have discovered a new inverse problem which neural fields can solve. And with that, I'll open up the floor for questions.
We have plenty of time for questions. And there are microphones over here and here.
So I think in all the forward rendering functions that you mentioned, I didn't see anything that handles reflection specifically. So I'm wondering if nerves, when I look at them, it looks like they're able to reproduce some reflection features. I'm wondering how that happens.
So just to repeat Ariel's question for our audience. So the question was, how can nerves model reflectance properties, right? So things like specular reflection and so on. So how does, do forward maps help with any of that? So Yiheng, do you want to take that?
Absolutely, yeah. So neural fields are almost trivially compatible with that. All you need to do is simply in your rendering pipeline, instead of having the neural field to predict the radiance values, you can have it predict BRDF parameters instead, and then use your own shader, GGX shader, anything that's differentiable after that to render the BRDF materials along with your lighting conditions into your final rendering. So having an extra component in there. Now, the more important question to answer here is, how can we constrain the problem in a manner that we can recover meaningful material, right? Because 3D reconstruction is already a very trivial, already a very ill-posed problem with lots of degrees of freedom. Now we're adding even more degrees of freedom by introducing these material properties and lighting conditions. How can we constrain the problem and provide meaningful prior so we can find a meaningful solution to the problem? So differential forward map here is adding a shader module to that rendering pipeline. And that's quite easy to do. The question is, how can we constrain the solution?
We have time for a few more questions. I'm going to unplug the display here so that our next speaker can start to set up, but we are still taking questions. So please feel free to come forward and ask a question. Oh, I see.
Thank you for the presentation. I have one question about all the nerves or fields you have mentioned is trying to completely use the same backbone region. Are there any forward way, like using a neural network or something, to generate a neural field instead of the backbone regions? Because otherwise, you need the backbone actually for every thing. You need to the backbone
that is a fantastic question, which my next talk is going to be about. So good. The answer is yes, and there is work on that. And it's very exciting. Repeat the question. Oh, yeah. So the question was whether there is a way other than optimizing a neural field. Is it possible to generate a neural field in a single forward pass through a neural network? So basically, do amortized inference to get a neural network, to get a neural field.
All right, so we have one last question on Zoom, and I'm going to meanwhile ask Vincent to set up. The question is, would one be able to use forward maps for representation learning? That is, learn a representation which would be better suited to downstream tasks such as classification. Yiheng, do you want to take this one?
Sure, yeah. I think the answer is absolutely yes. If we think about differentiable forward mapping functions, it can be really anything that's differentiable within an end-to-end pipeline that allows you to do whatever you would like to do. For learn, whether it's predicting the scene appearance or scene geometry, or we're working with latent representation, what you're predicting doesn't matter as much. What sits in between, we call them forward mapping modules. So absolutely, we can think about we can use neural fields to learn representations to output, for example, latent features in a compact space for other downstream tasks. And the enabler that links thus this whole end-to-end pipeline together in a differentiable manner are the differentiable forward mapping functions. The specific type of function you will use obviously depend on your downstream task and the representation you're trying to learn. But yes, you will be able to use forward maps for representation learning.
All right, thank you, Hank, for that presentation and for the Q&A. So while Vincent is trying to set up Zoom, I just want to kind of recap where we are in the tutorial journey. So we've talked about techniques for neural fields. In particular, we've talked about architectures, hybrid representations, and forward maps. Vincent Sitzman is going to talk next about generalization and the use of prior-based reconstruction for neural fields. All right, so with that, I'm going to try to switch the display. Hopefully that works.
Oh, perfect. The question already introduces the next talk. My name is Vincent, and I'm going to talk about prior-based reconstruction of neural fields, which is exactly what the second to last question asked about. So let me first motivate why what this actually means and why this is interesting and why people are interested in working on this. So let me motivate it with novel view synthesis and 3D reconstruction, right? So imagine something like NERF or scene representation networks and stuff like that. So here, usually what we want to do is we have a set of images and their camera poses, and we want to somehow find a model, some kind of model that allows us to do novel view synthesis, which basically means for NERF, for instance, right, you sample like the 3D neural radiance field. Okay, so usually the pipeline looks something like this, right? You have like a set of images with the camera poses, then you first like fit the neural representation, the neural scene representation that gives you this little MLP, and then afterwards you can use the differentiable renderer, the forward map, to render out novel views of that thing. And let me introduce a word here, which is inference. So what does inference mean? So inference we generally call in this framework this process of given a set of observations, find the underlying parameters of the scene representation. So in this case, inference is optimization, right? So we have all of these images, and then we optimize the neural scene representation such that we can do afterwards novel view synthesis. So the case that we have been looking at so far was this case of overfitting or per scene optimization. So let's look at that in more detail. Let's say you have like lots of images and camera poses of like a little toy car or like some 3D scene. You have the scene representation, you have a differentiable renderer, and now you can optimize the scene representation through the forward map, through the differentiable renderer to find the 3D representation, right? And so you can like do the fitting. This is like the little optimization process, and then afterwards you can render novel views. So that's great. And this is basically this framework that we've been talking about so far. This is what NERF does. This is what deep voxels does. Planoxels, Siren is all of this idea that we have lots of observations of a single scene or some single neural field that we want to optimize, and then we just optimize it for that particular scene. Okay, but the case that we are now going to look at is this case where we have incomplete observations. So imagine, for instance, of this little toy car, we only had one image, right? So note that in a single image, there is no 3D information. There's no way of recovering the underlying 3D scene if I just give you a single image of a scene, right? So, but if we just try to do naively the same thing, like what we're going to get out at the end is trash. Like we're going to only get, on the top is ground truth, and on the bottom right is the novel views that we're rendering, and you can see that they're not meaningful at all. Okay, so what can we do to fix this? And this is what this talk is about. So what we have to do basically is we have to get a little bit smarter about how we do inference. So instead of just doing optimization and like optimizing for a single neural field, now we have to somehow learn a space of neural fields. We have to learn a prior distribution over neural fields in order to be able to solve this problem. And this will allow us two things. One, it will allow us to reconstruct scenes from partial observations or signals from partial observations, and it will allow us to also do things much quicker. So for instance, imagine you can do a single forward pass and then you immediately get your neural field instead of first having to do optimization. Okay, so the general framework looks something like this. Usually we have like our sensor domain, so that might be an image or it might be a point cloud. Then we're going to have an encoder, and that encoder is the thing that does inference in this case. And the encoder is going to give us a set of variables. So these are low dimensional latent codes or like features or whatever you want to call them. And then we basically have a decoder, which is basically our neural field and our forward map. So this is also the case of null view synthesis, but like this could also be the case for point clouds or for something else. Okay. So there's a few interesting questions that one could talk about. We don't have enough time to talk about all of them, but I'm going to highlight a few of them, and then we're going to talk about some of them. So the first interesting question you can ask is, what do these latent variables look like, and what do they do? Another interesting question is, how can we get them? So like, how can we learn these latent spaces? How can we find for a new set of observations the corresponding latent codes? How can we use these latent variables to like then decode them into something interesting, and so on and so forth. Okay, the first thing we're going to talk about, and Tawaki was great, already talked about a little of this, is what do these latent variables look like, and what kinds of forms and shapes can they take? And so generally, there's these two kinds of cases that are on a very high level interesting. So the first one is this question of locality. So we usually differentiate between this thing of like global conditioning and local conditioning. What does that mean? Global conditioning means that for a single 3D scene or for a single neural field, you represent the whole neural field in a single low-dimensional latent code. Just like in a classic convolutional autoencoder, right? You would have an encoder, then you have your little latent code, and then you have your decoder. And so a single latent code that is not dependent on where you are in space encodes the whole neural field. And then there's this other thing of local conditioning, which Tawaki already talked about a little bit, where instead you have some kind of 3D data structure that stores your latent codes. And depending on where you are in space, you're going to retrieve a different latent code to condition your neural network, your neural field. Let's talk a little bit about this global conditioning first. So the basic idea, like one of the questions you have to ask is, how can you condition your neural field on a given latent code? So imagine this was like a latent code from like some kind of autoencoder. So this would represent your 3D scene. Given that latent code, how can you get your neural field? And like one way of doing this is, for instance, via hypernetwork. So what that means is you take your latent code and then you stick it into a little neural network, and that neural network gives you all of the weights for your neural field. So that is what we did, for instance, in scene representation networks. Another thing that people often do is they take the latent code and they just concatenate it with the XYZ coordinates and give that to your neural field. And that's basically how you can condition your neural network on a given latent code. And this is this global conditioning is the method that many of these early neural field papers used, right? So for instance, DeepSDF, occupancy networks, IMNet, scene representation networks, differentiable volumetric rendering, all of these learned spaces of objects where each object was always represented by a single low-dimensional latent code. And that allowed you to do like reconstruction from a single image. So for instance, these objects here, these are all reconstructed from a single image. In DeepSDF, if you remember, you could also do reconstruction from a partial point cloud, and so on and so forth. So we figured out over the past few years that this has several key limitations. So the key limitation that is interesting is that this is very limited to very simple neural field signals. And it's actually really interesting to think about why that is the case. And the way you have to imagine it is, imagine you want to parameterize something that is composed of two objects, right? Like a space. Imagine you have like 3D scenes, and imagine you have 3D scenes with a single object. So what is the degrees of freedom of that space? It's the degrees of freedom of the object, like maybe the degrees of freedom of chairs, like some low-dimensional manifold, and then the chair can move around. But now if you add a second object, then the degrees of freedom, they don't grow linearly, they grow very quickly. You can now have a latent space where your first object can be at one location, and then the other object can be at any additional location. And then if you add one more object, that latent space grows and grows and grows. So basically, long story short, this global conditioning is very limited to these very simple non-compositional seeds. And then we quickly figured out that there has to be a better way of doing this, and this is what local conditioning is. And in the past few years, we have seen an increase in this kind of prior-based reconstruction. How does that work? So as mentioned here, the idea is you have some kind of discrete data structure, like a voxel grid maybe, and that discrete data structure stores features at each of the vertices. And now if you have a query coordinate X, you query your discrete data structure that gives you a latent code at that location, and then that's what you use to condition your neural field. So one paper that is really cool here is this paper, Convolutional Occupancy Networks, and it's a good example. So how does that look like in practice then? So convolutional occupancy networks use that to parameterize an occupancy field. And they did exactly this thing where you have a 3D feature volume which stores these features. And then if you want to decode a coordinate, you do trilinear interpolation, stick that into your little neural field, and then that gives you the occupancy probability. So now, where does the prior come in this case? The prior comes in that now you can reconstruct this feature volume, not for a single scene via optimization, that's what we have looked at so far, but instead by encoding it from some kind of signal. So imagine you have a point cloud. Now you can take a point cloud encoder like a point net or something else. You can take that point cloud encoder to generate the feature volume. And then you can maybe do completion on that feature volume with a UNet or something, but then you get that feature volume in a single forward pass, just as the question asked. And this led to really, really cool results. So here you can see these are point clouds, and this is from the convolutional occupancy networks paper. And in a single forward pass without any additional optimization, you can get the occupancy field for that, the geometry for that whole room as a neural implicit representation. So that was really cool. One big problem with this is that the memory that this requires grows cubically with the resolution of the voxel grid, right? Because voxel grids are expensive. So Towaki also already talked a little bit about this. Well, one idea that people have looked at, but convolutional occupancy networks in 2020 already looked at, is this notion of factorized representations in triplanes or ground planes or parameterizations like this. So for instance, imagine that instead of having a 3D voxel grid that stores your features, instead you just have a ground plan. Imagine on the ground plane of this room here, there would be like a grid, and in every voxel of the grid, you would store a feature. And now if you want to decode a coordinate, you drop it onto the ground plan, you just bilinearly interpolate the features that are there, and then you decode that into an occupancy. And again, you can do this in a single forward pass. Imagine you have a point cloud, you just have to use a different encoder. So you give me a point cloud, I will build some kind of encoder that gives me that ground plane, and then I can do that in a single forward pass and then decode that ground plane into my occupancy field. So, that is with just a single plane, and now there's this notion of triplane representations, right? So instead of just having a single plane, you can of course have more than one. You can have one ground plane, you can have an additional horizontal plane, like an XZ plane, an XY plane, and so on and so forth. And then the same thing is true again. Maybe you have a point cloud, you'll just infer these three planes, and then these three planes you can then decode into your voxel grid. And this requires much less memory, but still allows you to do reconstruction of these occupancy fields in a single forward pass without optimization. Okay, so this is a little bit of a special case that Yiheng also just talked about in his forward map case, because in this case that we looked at so far, the field that we wanted to reconstruct was in the same space as the sensor data that we had. We had a point cloud and we wanted to reconstruct 3D geometry. But that's of course not always the case. In this case of inverse graphics like NERF, we have images and we want to reconstruct a 3D neural field. And so then, as you might imagine, this gets a little bit more tricky. Like, what is your local data structure that you can condition on images such that you can condition your 3D local field? And here one idea is, for instance, pixel line features, proposed here by Shunsuke, if I'm not mistaken, in PyFu. This is a figure from PixelNerf, which also uses this. So here the idea is, imagine I give you an image, you're going to extract 2D convolutional neural networks features with a 2D convnet from that image. And now when you want to decode a 3D coordinate, like this one, you're going to project it onto that image plane. You're going to get the feature that is at that image location, and then that's what you're going to decode with your little neural network, with your neural field. And that's how you can condition your 3D neural field on your 2D observations, on your 2D images. And this allowed to decode more complicated scenes and generalize to scenes that are composed of several objects, just instead of just a single object. And also to some real world scenes, but we're still not there yet, of course, where we can just take a single image of this room and decode it into a neural field. That's going to take some more time, but you know, progress. So this generalized much better. It also has a few interesting limitations. Like one of them is that this doesn't actually have a persistent 3D representation. So you always have to keep the images around, because when you want to decode a 3D coordinate, you have to project it onto the images. So that's a little bit questionable. And then the second problem is that the prior that you're learning, the thing that does all the heavy lifting in this framework, is actually the 2D convolutional neural network. It's the thing that looks at the image and generates these deep learned features from the image. So that's where the priors come from, where the prior information comes from, all the machine learning, and that's happening in 2D, but you might want to do that in 3D. There's another class of conditional models, which are called object-centric representations. This is also interesting. So imagine you have a scene that is composed of a few objects, and you have this little image of the scene here. Now, there's a class of models often built around this slot attention module. How exactly it works is not that important, but what the slot attention module basically does is it tries to detect the objects in this scene and then give you a separate latent code for each of these objects. So this is basically an encoder that looks at this image and then gives you one latent code per object. And then you can use these latent codes to condition your neural fields on each of these latent codes separately, and then put that into some kind of forward map like a renderer. And in that case, that allows you to learn to disentangle 3D scenes into the objects just from images. So in this little example here, you can see a single image, you can reconstruct this 3D scene here, which is composed of 4 separate objects. And each of those is actually represented, in this case, by its own little light field, or it could also be done with neural radiance fields. And that's also another form of conditioning. The problem is that this is also work in progress. So like this is a little bit hard. So it actually doesn't work for scenes like this one yet, right? If I took a photo of all of you, it would be great if I could have a neural field that would give me a separate latent code for all of you. That doesn't work right now. So right now it's constrained to these kind of simple scenes, but there's a lot of progress in this domain. And this is very interesting to follow that line of work. We have been working on something interesting here as well, which is based on inferring these ground plans from images. So the idea is basically in many scenes that we interact with in the real world, the thing that is actually interesting is many interesting things happen on the ground plan. But like for instance, in this room, most of the variance can be explained by just looking at the variance on the ground plan. There's not that much happening in the height axes. And we built this model that basically takes an image and then from that image does inference to infer this 2D grid that is the ground plan of the underlying 3D scene. And that allows us to do things like this, where from a single input image, we can reconstruct a nerf. And then through some more trickery, we can then disentangle that nerf into single objects and do self-supervised object localization and disentanglement into different parts of the scene. And so this is slightly different than like the conditioning on image features, because here we are reconstructing like a persistent 3D representation in the form of this ground plan. Okay, so that was just an overview over this notion of local conditioning. The big things to remember is global conditioning is a thing that we did in the beginning a lot. It doesn't work for complex compositional scenes. Then when we switch to local conditioning, we can fix that. That's basically the key insight. Okay, so how do we get these latent codes? And I want to touch on this door just a little briefly. So our latent variables can be organized in like a voxel grid or in this ground plan or in all kinds of different organizations. How can we actually go from, for instance, an image to these latent variables, or from a point cloud, let's say, to a voxel grid? And of course, you can pick an encoder, right? So that's many of the things we just looked at. Do that, for instance, from an image, you can get to a 2D grid of features, or from a point cloud, you can go through a 3D voxel grid through an encoder. But yet another way of doing that is with so-called auto-decoding. And the key idea of auto-decoding is kind of interesting. The idea is that you don't actually have an encoder. So you still want to learn this latent space of features. So each of your neural fields is represented by some set of latent variables. But you don't want to get these latent variables through a forward pass through a neural network. But instead, you're going to, again, use optimization to get these latent codes. And this is actually what DeepSTF used as an inference. So just to give you an idea how that looks like, let's say we use this for learning a latent space of ShapeNet objects with differentiable rendering. So let's say we have a single little car. That car is represented by a particular latent code. So we're going to use that latent code to condition our neural field. Then we can render it, and we can get our little image of the car. And now, how do we solve for the latent code given an image? Instead of using an encoder, right, is what you could do is you could take this image, stick it into an encoder, and it would give you the latent code. Instead of doing that, we're going to just backpropagate through our model and optimize the latent code given the observation. And that's what we refer to as auto decoding. And this is, and in that way, we don't have to use an encoder. We can just use only the conditional neural field plus the forward map to learn this latent space. And you could ask, like, why is this interesting? Why should we ever do this? Sometimes this has interesting properties because sometimes the forward map is something that has a lot of structure. So for instance, if you think about neural rendering, right? In neural rendering, we built all of this inductive bias in the form of this differentiable renderer where you can place your camera and then you shoot these rays and it samples along the way and does all of these things. And if you think about what this neural renderer does, in a way, it gives you a 3D structured way of making your, it has a lot of 3D structure. So when you backpropagate through the neural renderer, instead of using a convolutional neural network to get this latent code, what you get is that you can use all of that 3D structure from the neural renderer, and you get a particular property for free, which is that if you use the CNN encoder, if you use the CNN encoder and you train that over a set of cars, and now you give it an object from a perspective it hasn't seen before. So for instance, imagine that at training time, you only saw these cars from a particular distance, but now at test time, you're going to zoom out. So you see a very small car, or you zoom in drastically, and you see the car really up close, then your CNN encoder is going to be lost. Because your CNN encoder has never seen this before. Right, like convolutional neural networks are not, cannot deal with 3D transformations. If like I take my hand and like I move it really close to the camera, that is very different than if it's far away from the camera. But because you're backpropagating through your forward map, which has all this 3D structure that you built into the forward map, if you use auto decoding instead, you do generalize to these out of distribution poses. So this concept is a little bit subtle, but I encourage you to think about this sometimes. If you put lots of effort into designing your forward map such that it has particular properties, sometimes using the forward map for inference by just backpropagating through the forward map can be very useful instead of trying to build an encoder. Okay, I want to briefly touch on another form of generalization as well, which is recently we've seen lots of work using transformers. For instance, right, imagine you have a point cloud. We could do the thing that we just discussed. So you could have like some encoder that gives you like a 3D voxel grid from this point cloud, and then you could condition on your voxel grid. But as Tawaki had already mentioned earlier, sometimes that's not ideal because you don't want to store this huge voxel grid in memory and stuff. So maybe it would be great if you could stay in this domain of points. Then the question is, how do you do that? And there's this paper, AirNets, for instance, that proposes a way of doing that, which is you can use point cloud transformers, which is just an encoder, right, that acts on this point cloud. And the point cloud transformer will give you a feature for each of these points. And then at the end, when you want to decode a 3D point, you take that 3D point and you just do attention over close by points to then decode that 3D point. So you can use attention and transformers to parameterize these neural fields. And this is like, there's not much work that uses this kind of transformer-based conditioning, but it's an emerging area. And then there's the scene representation transformer, which also uses transformers instead of MLPs to parameterize the neural field. And this is also quite exciting stuff. So we're going to skip this. So now the last thing I want to talk about briefly is, so far we've talked about generalization exclusively as a tool of reconstructing these neural fields quickly or reconstructing neural fields from partial observations. And that's great. But one can ask, is there anything else that generalization can give us? Is there anything else that this framework can give us? And the interesting thing is there is. In particular, sometimes our forward map is very complicated or very expensive. So here the example that I put down is neural rendering. And you all know this if you've worked with NERF before or neural renderers, is that the forward map is really expensive. You have your 3D neural field, and then if you want to render a single pixel, you have to sample it hundreds of times. And there's lots of effort in speeding that up. But it turns out that generalization might give us a way of overcoming this problem. And the key idea here is that if you think about what this forward map is doing, right, is it's basically translating between those two domains. The one domain is the 3D domain where your neural field is defined, and the other one is the image domain where you want to render out an image. And every pixel in the image is a ray, right? And for each ray, you have to sample all these points along the ray. Okay, so what you can do instead is you can maybe you can just skip all of that. If you think about what you want to do is you want to have a ray and then you want to just get the color of the ray. So you're not actually interested maybe in the 3D radiance field, you're just interested in the color of a ray. And if you have that insight, then you can ask, well, can we just skip the forward map? And can we just immediately learn the neural field that you can just sample with the ray and it gives you the color, right? So you basically get rid of the renderer altogether. So then the neural field is a different one because now the neural field takes as input a ray. It doesn't take as an input the 3D coordinate anymore. And usually, if you try to do this in the overfitting regime, it wouldn't work. So you couldn't run this in this regime of NeRF where you have lots of images of a single scene and then you're just going to overfit it. But because we can generalize across scenes, it turns out that what you can do by generalization is you can basically learn a prior over these neural fields instead of learning a prior over these 3D structured neural fields instead. So what you're effectively doing is when you run inference, you're immediately getting the rendered neural scene representation instead of first getting the 3D one and then doing rendering afterwards. So the inference problem gets much more complicated because now maybe this neural field is much more complicated, but but you have gained a lot because you can skip the forward map altogether. And we did this for like simple scenes, and there it provided you drastic speedups, and it totally works, right? So this is reconstructed from a single image, and then you can render this in real time without any volume rendering. But when we did it, it was constrained to simple scenes. Here at CVPR, there's a paper called the scene representation transformer, which uses a transformer to parameterize this light field instead. And as you can see, it's still not photorealistic like NeRF or something. But this is, I think, inferred from like 3 or 5 images. And from 3 or 5 images, you can basically infer this light field that you don't have to render anymore. Rendering is basically free. So that's really cool. Okay, there's lots of things I didn't get the time to talk about, but I just want to point them out to you. So I talked exclusively about 3D things, but of course, there's all of the things we talked about also apply to signals in 2D and 1D. So for instance, there's learning priors for super resolution. That's you can parameterize an image as a neural field, and then you can learn priors for super resolution. There's cool work on neural field to neural field translation, like image to image translation with neural fields. That's cool. There's generalization for robotics applications, like if you want to do grasping or something like that from incomplete observations. And then there's generalization for very structured data. Like if you think about human geometry, we have lots of prior knowledge about like what a human skeleton looks like, and we can exploit that prior knowledge for building priors over that data set as well. So all of these are interesting directions that I didn't talk about. And just for the outlook, so I think that this line of generalization is currently gaining a lot of traction because it turns out that single scene or like single signal optimization is somewhat limiting. Like collecting hundreds of images for doing reconstruction of a single scene is very limiting. And oftentimes many of the applications that we want to solve in artificial intelligence also don't work like that. Like I don't need 600 observations of this microphone to be able to pick it up. So this line of work is gaining traction, and it has these 2 key applications, which is it can make the inference faster. We don't have to do optimization anymore, and it might allow us to solve problems where we only have partial observations. Then it has this thing that I'm very excited about, which is it might allow you to skip some expensive forward maps like rendering altogether. This is very much research in its infancy still, but this is very exciting. There's lots of progress recently on how we can disentangle scenes into their object components. Like I take an image of the scene and I want to disentangle it into all of its separate chairs. This is something that we humans do all the time, and that is very important for our understanding of the world. But in neural fields, we would like to have the same thing, and this is something we definitely have to tackle with generalization and priors. There's an interesting question that is not solved yet, which is as long as you deal with voxel grids, everything is kind of easy because voxel grids are nice to deal with. But if you have point clouds or meshes or light fields or like some complicated spaces, then this question of how you do this local conditioning gets more difficult. And there's still lots of exciting work there to be done. And then lastly, transformers are interesting as a tool in this domain because they seem to do something like local conditioning, like this conditioning on local coordinates, but we don't quite know how that works yet. And there's lots of exciting work to be done there. Thank you. I think that was my talk. And any questions?
For coding, do we have to train several times for each part of this?
In auto, yes, that's a good question. So the question is, if we do auto decoding, do we have to train several times for different categories? And this is a very interesting question because it relates to, it's kind of a more nuanced issue, which I'm happy to talk about with anyone who's interested to understand the differences between auto decoding and auto encoding. Like what actually is the difference between using an encoder to do inference versus using auto decoding to do inference? It's not at all obvious. And in the question that you just raised is if you think about the latent space where you have lots of object classes, then each object class would basically ideally be in a different part of the latent space, like in an auto encoder, right? And what you have to think about then is what the optimization and auto decoding has to do is it basically has to start at some point in that latent space and then optimize your latent code to go into that part of the latent space where that object class is in. And it might turn out that on the way there, there's lots of local minima that you fall into, and you might fail at doing that. While an encoder might be much better at immediately taking to the right part of that latent space. And why that is a little bit subtle, but unfortunately, there's no general answer to the question, but generally it can happen absolutely that sometimes some problems are harder for autodecoders and some are harder for encoders.
So when doing global conditioning using gradient activation network, etc., usually an hypermethod is used. That's not possible for local conditioning because there are some approaches to apply local conditioning for science. Gradient activation function.
So the question was, is it possible to do so I think there's actually two questions. One question was, is there a notion of hypernetworks in local conditioning? So let me answer that one first. So you absolutely can do hypernetworks as well if you do local conditioning. And an example for this is kind of kilonerve. So if you know the kilonerve paper, it basically takes a voxel grid and in each voxel, it stores like a little MLP, right? So that is kind of what, and one extreme end of a hypernetwork where you just store all of the weights of your neural network in the voxel grid. And the other end, you might store little feature vectors in each of the voxels, and then you decode them with hypernetwork. But in principle, you can also build that. It might just be a little bit more expensive. And then the second question was for these other kinds of activation functions, like periodic activation functions. Can you still use these kinds of conditioning methods? And the answer is yes. What usually happens is that you have to be a little bit more careful in designing where the latent code starts off. So for ReLU nonlinearities, the latent code should be close to 0. Maybe for periodic activation functions, your latent code might be initialized at in a different kind of space, such that you have at initialization a good initialization. But other than that, it works basically identically.
I have some questions. As I know, there are some few different ways for conditioning, like simple combination or feature-wise layer modulation or hypermethod, like you said. So is there any insight for this conditioning design?
Yes, so it turns out at the end of the day, they all kind of do something similar, which is, what does conditioning mean? It's like a weird word, but conditioning actually just means that you're at the end somehow predicting some part of the parameters of your neural field. That's basically what it means, which intuitively makes sense. Like you have a feature vector, and somehow you want to inject the information of that feature vector into your neural field, at the end of the day, you can always write it as predicting some subset of the parameters of that neural field. So hypernetworks is like one extreme case where you just predict all of the parameters. Conditioning via concatenation is on the other extreme where it turns out just predict the biases of the first layer of the neural field. And then everything in between is like some, maybe you predict the scales of each neuron, or like the biases of each neuron on each layer. But long story short, you would probably just try it out. I think generally people find film conditioning works really well and seems to be a good compromise.
Another question is about autoencoder. So there's no encoder. So we might think that without encoder, the learned prior to autoencoder might have just low-level features for shape reconstruction. So it might have worse reconstruction performance, like it can't capture the high fidelity details for reconstruction.
So the question is whether autodecoders can capture the high frequency detail in the reconstruction.
Yes,
okay. I think generally the answer is yes. So like if the only difference is how you do inference, like with autodecoding or via an encoder, your model is exactly as expressive, but it might of course be that the optimization is harder. So some problems are harder for autodecoders, some are easier for encoders. Cool, I think we're out of time. Cool, thanks so much.
Is this better? All right, cool. All right, so I'm a research scientist at NVIDIA, and I guess I'm gonna close this session where I was hoping to talk to you a little bit about how we manipulate neural fields. So let me start with some of my philosophy on this, right? So I think let's talk about prime representations, and this is like my term. I mean, it's not anything official, but the way I want us to think about prime representations for the following 20-30 minutes is as representations that naturally emerge out of sensors, or that we can create by some content creation tool, right? We all know these examples. So images represented as pixel arrays are a very natural representation. I would call them a prime representation, right? And same goes for point clouds, meshes, even audio signals, right? We can record them in the raw form, in the prime form. And as neural fields are becoming more popular, what we know to do well, and what my fellow co-organizers have talked about so far, is that we know how to map those prime representations into neural field representations. But one property of prime representations is that over the years, we've developed a lot of ways to manipulate them and edit them. So, images, for example, we have tons of geometric transformations that we can very easily apply to, but not only geometric transformations. We can also do tone mapping and histogram equalization, right? Even that silly meme I put out there is a composition, or an ability to go to an image and modify locally a bunch of pixels in that image, right? Turning to white, writing things on the image. So this composition ability is not something that necessarily naturally emerges in neural fields. If you go to meshes, point clouds, again, we have techniques to manipulate them and edit them. So I'd like to raise this question of like, are neural fields ready to be treated as prime representations? And I'm going to start with telling you why I think, I'm going to give like a couple of examples where I think neural fields naturally emerge as prime representations, which one of them would be in generative models, right? Where there was no like originating image necessarily, or signal that from which we copied and tried to overfit our neural field to represent it. It just emerged out of some random noise that was mapped to the neural field. So I'd argue that this is an example of somewhere where we just start with a neural field in some sense. And now another example, again, as we've talked about, is when neural fields are acted as inverse solvers, right? So in the case of neural radiance field, it's not like most of the cases, it's not like someone gave us a neural radiance field and we try to overfit a neural network to learn this radiance field, right? We solved an inverse problem from a collection of images, and so a resulting representation, or resulting neural networks, is now our prime representation. So hopefully this is convincing enough to you to think, okay, so wait, they are ready to be prime representations. Well, if you agree with me that that's the case, then I'd argue that we need to devise methods and techniques to manipulate them the same way we are devising those to manipulate prime representations. So here's an example. Can we take primal manipulations, which are manipulations applied to prime representations like a point cloud, and map them to neural fields? For example, if I knew how to map this airplane represented as point cloud to a neural network, it's very easy for me to think of, just taking that airplane and rotate it. But now the question, where I put the question mark, is, will I be able to also learn that manipulated airplane, that rotated airplane into my neural network? Turns out this is not as trivial as one might think. But maybe even more interesting than that, what if I already mapped it, maybe, my collection of airplane shapes into a neural network, and I just wanted to rotate them without ever reconstructing them, without ever decoding them into their equivalent primal representation? I would just want to act on the neural field itself. So this sets the ground for, a collection of tools for manipulation. I want to take the rest of the talk to tell you a little bit of, how we think about those, how we split the methods by topics, and which methods are also out there. And I just also want to apologize for all of these, all of you out there that wrote papers that I did not include in this presentation. I chose mostly those that would be easier for me to talk about or demonstrate the general message. So it's going to be if you feel like your paper deserves to be here, email me or come yell at me afterwards. So the first axis I'm going to present is, look at this kind of abstraction of, the neural network or a neural field that starts with some, coordinate-based input, and then there's a bunch of parameters that are baked into into our neural network. So generally speaking, we have two ways to think about manipulation here, right? We can either manipulate the input coordinates, or we can edit the network parameters themselves. I think that's pretty straightforward. But there's another interesting axis, right? Our handle to control and manipulate the neural network can be either done via explicit geometry or via neural field again. So maybe this is a little bit more vague. And instead of trying to explain to you with hand waves, I'll just start giving you some examples. So I'm going to start with this quadrant, where I'm going to look at the intersection of manipulating a neural field using its input coordinate remapping through explicit geometry, right? So here's a very simple example, right? Let's say that I have this neural network where I'm feeding some coordinates, and maybe my output is a sign distance field, and I can turn this sign distance field into a reconstructed mesh, right? Something very easy that I could do if I wanted to, for example, take that reconstructed chair, move it around, rotate it, even scale it up. I can almost trivially write down the geometric transformation. And because the knowledge is in the network already, I can just remap my query coordinates and query those in the new location, reflecting the geometric transformation I'm interested in. So this is a trivial transformation. And what I want to point out here is that I didn't have to ever decode, right? I didn't ever have to convert my neural field representation to its equivalent mesh in order to do that. I could just naturally do that if I knew what transformation I was interested in. This brings up, the question, can we go beyond single objects? That's all fine, right? But if I gave, if it was an entire scene, that would have been maybe problematic. So, Towaki talked about hybrid representations, and this representation came up as basically as means to make sampling more efficient. But it also bears another interesting property, right? That once we've done pruning the unused voxels, we get a natural mask for each object. And this buys us the ability to now take those masks and, again, using explicit geometry, literally moving those masks around and remapping the input coordinates to compose a scene, right? And each object in the scene can be manipulated in its own local mask or frame, if you will. The only thing we need to be kind of careful with is that when we, in the case of radiance field, right, if you want to ray trace for this, we need to kind of we need to do bookkeeping of like which voxels array is going to intersect. Once we moved an object to a new location, it might occlude other objects. So we need to account for that. This work took this idea one step forward, and instead of reconstructing objects in isolation and then composing them to a scene, what they did here is basically given a reference video or reference scene, already making the reconstruction process aware of the scene graph was used to decouple the scene into its individual objects. So basically here, the reference input could be a video of a drive. The different moving objects, in this case cars, in the scene have been detected and were reconstructed individually. And then another neural field was used to represent the background separately. What this gives us is this nice handle now as, again, explicit geometry being now basically just bounding boxes, each serving as a frame, as a local frame where a neural field lives. And we can move around those neural frames, recreating the scene, reenacting the scene, adding more cars and making novel driving scenario. This one might think could be very useful for training on autonomous vehicle systems, for example. Right, but of course, this is not at all limited to spatial manipulations, right? Temporal manipulations, right? We know neural fields can get as input coordinates also a time coordinate. And again, if I wanted to speed things up, slow things down, offset my video, or even reverse it, like these are a bunch of transformations that I just listed here on the screen, I could have done that as well. The paper I'm kind of showing here also took this idea together with the explicit spatial transformation and basically decouple the scene into its scene graph, where local frames represent the objects in the scene. And now I can not just move around, manipulate, geometrically each of those local frames. I can also play around with time, right? So I can have two people, who are maybe, dancing together. I can now take one person, move it to a different location, but also take dance moves from, 2 seconds into the future and play them now. So really, this kind of mapping is very powerful and gives a lot of controllability and also a very intuitive one. Another way to manipulate, maybe kind of in like if I would take the equivalent of objects to a scene, can be kind of thought of as like parts to an object, right? So this work, NASA from 2 years ago was doing that for local frames in signed distance field in geometry, and basically again the same concept holds, right? By having local frames representing signed distance field, I can compose them, and because a human body has a very well understood skeleton, then performing a manipulation is also an easy operation. I could very easily do retargeting, right? So I know generally how a human skeleton might move, and I can recreate novel motion and render it. In the case of radiance field, this work was Nurit last year, took this to the radiance field, but I'm gonna keep the, we have a full talk about human modeling in the afternoon, so I'm gonna just mention this and just say that retargeting is also possible with neural rendering. What if we don't have the skeleton? And if you notice, I'm kind of removing priors as we go more and more, right? It's going to be much worse when we get rid of the input coordinate and try to work on the parameters themselves. But now what if we don't know we're manipulating a human? So this work basically says, okay, if we have enough observation, we can look at something move. We can watch things move. That's literally the name of the paper, and then try to infer the different parts from the video and localize them using some, in this case, like some spherical Gaussians, and then each Gaussian can represent local detailed geometry, but is also coupled with a rigid motion. So after watching a couple of compositions of motions of the different skeleton parts, I now can infer the different parts and reenact them, moving them, creating novel animations. Right, just to say that if we don't know, go and remove this prior again of skeleton even, some works used a mesh, which again is a geometric prior that we can use. For humans, we have meshes. For some animals, we have meshes. That's again something we can hang our coordinates on, and then by doing manipulation, we can control the input coordinates into our neural representation. This work from this CVPR that I recommend going and check it out. Towaki already talked about, again, does an explicit use of a tetrahedral mesh in this time in this case, where again, this builds on the ability to take a neural field, reconstruct a mesh from it. And because we have mesh editing tools, deformation to the mesh can be translated to deformation in the input coordinate, a remapping of the input coordinates to the neural field. All right, moving on to, again, controlling the input coordinate remapping, but this time, I want to pose this problem, right? What if we get rid of all the priors I said so far, right? We don't have a skeleton, we don't have even the articulation assumption. So in this case, we need a more flexible way to map around our neural, our input coordinate. And, you know, we need a flexible representation that could continuously map input coordinates to other neural, other input coordinates, right? Sort of like a flow. And what a better candidate we have than, again, a neural field to do that. So here's an example of such a case where we want to represent, we want to do this time scene manipulation. And scene manipulation, as you know, I just said, is not limited to those, you know, skeleton motion only, right? Scene flow can be somewhat arbitrary. In this case, we'd like to be able to take rays that we shoot from one direction. And if we want to generate novel view synthesis, and we believe that flow is the only explanation of, you know, dynamics in the scene, then to be able to do novel view synthesis from novel, you know, we need to be able to map flow to new rays. And in order to do that, sorry, I'm looking for my mouse here. So the idea here is that we'll learn another neural field, this Rij, that can map the location of a point in space where it was in time or in frame I to where it is in frame J. Now, of course, the network could easily degenerate here, right? There's no prior, without any priors, there's many wrong solutions that can be found here. So it's very important to start, and, you know, this invites a place to start and devise interesting priors. One of them is of course, photometric consistency. So looking at nearby images, we want to be able to map backward and forward between the images, basically guiding the flow. So there are two ways to explain my image: is either my current observation or my observation from, let's say, one frame into the future after it has been mapped correctly by my flow field represented as a neural field. And to add on top of that, it's very helpful to use data prior regularization, which I think also relates well to what Vincent just talked about in terms of generalization. When we don't have good generalization naturally emerge in the 3D nerve representation, we can borrow it from 2D. And we know that 2D flow networks are generalizable creatures. We can use that and basically take the 3D scene or the 3D inferred flow, project it to 2D and match it with a 2D flow estimation network, guarding to, again, get rid of garbage solutions. And what this allows us to do is basically take such an input and either, you know, fix the view, but still play time, or fix time and manipulate the view, or do some joint space-time interpolation. All right, moving on to, again, editing, again, using explicit geometry, but this time we're not going to touch we're not going to use that to remap the input coordinate. Instead, we're going to control the network parameters directly. So we said that the knowledge is in the network, right? So if we, you know, if we take a shape, like in this case, a point cloud, and we already, let's say, know what's the equivalent network that can represent the same point cloud, the question is, like, can we assume that the rotated airplane will also be mapped to that? So it turns out, again, this is not that trivial. And if you train your neural network, for example, using deep SDF on a collection of aligned shapes, which we often do, then if you try and show that network an oriented, like a differently oriented object, you'll get garbage as a result. So in this work, the vector neuron, there's a proposed solution in the form of an encoder, right? And the encoder basically is an equivariant encoder that takes care of taking that rotated input and mapping it to a latent code instead of the standard high dimensional latent code that's a single vector, this time the vector is going to be a vector. Sorry, the high dimensional vector is going to be in 3 space. So it's a vector list that lives in 3 space that can be mapped to basically, and using the queried input coordinate, it's mapped to an invariant input to the neural network, right? So now this time by using this collection of invariant creatures that are basically interactions between the input query coordinate and the latent vector neuron representation, we can rely that what we get, basically what we're asking the decoder, the neural field decoder to infer, it's the same thing exactly as it did in the rotated version of the airplane, only we know how to rotate it thanks to the equivariant network. Another form of, again, this, you know, like in this work, the optimization was done on the latent code condition neural field. This is again a latent code condition neural field, but this idea is a little bit different. In here, what the proposed idea was to take input geometries represented as geometric primitives, but also high resolution sign distance field. Both can be generated from the shared latent space. By mapping both the coarse geometry or the coarse / explicit, geometric primitives and the high resolution neural field geometries to the same latent space, manipulating the one should hopefully affect the other, right? And then decoding to the high resolution would allow us to take a manipulation that's very easy to do using geometric primitives like spheres and transfer them to a new latent code that then would be decoded into a high resolution version. Okay, this may be slightly more involved. I'm not sure if I have enough time to go into this, but super important work. This work basically tells us how to do shape editing on neural fields representing sign distance fields using a bunch of properties that sign distance fields have. And unfortunately, yeah, I think in the favor of time, I'll unfortunately have to skip this. But if you're interested, please come talk to me afterwards. Happy to go into details about this. Super exciting work. I just want to say that basically the idea here again is to say, can we borrow all those mesh editing techniques that were developed, that we're working on explicit geometry and immediately apply them to neural fields representing sign distance field? And the short answer is yes. What we need is, if already our shape is represented as a neural field, which is, we know how to do already. All we have to do is, again, optimize the network parameters. We initialize a new network with the same parameters as the old network. So we are kind of guaranteeing this. The first term guarantees that during optimization, we're not going to hurt the global shape structure. The iconic constraint is going to keep it a valid SDF. But what's interesting here is that now we can devise explicit ways to control properties like curvature, for example, which could be just due to the fact that neural fields are differential. We can take derivatives of neural field. The first derivative would give us the normal. The second would give us the curvature. We could actually optimize by controlling the curvature. So really important work. Yeah, another thing that I want to say, maybe this touches upon generalization, again, going into like what Vincent talked about earlier, is that, when we do a manipulation on our input, we want to somehow guard that manipulation would be respected by the neural network. One way to do this is not to do just a feed forward, but instead, so for example, if we feed this to like networks that were trained on boats and there were maybe never those benches in those boats that were trained on, maybe what we'll get is slightly more akin to retrieval than actual reconstruction. Whereas in this work that's going to be presented here in this CVPR on Friday, there is a local optimization problem that's actually being solved as part of the forward process. And this optimization problem respects the input points and make sure that whatever editing was done to the input would be taken into account in the reconstruction process, right? So it's basically it's solving this inverse problem on the fly. Right. Our last topic is, before moving on to non-geometric manipulations, is how do we edit a network, the network parameters via neural field? And I think a very kind of intuitive example is like, what if you had a generative model that was generating, you know, taking random noise, generating shapes, and then you wanted to interpolate it, right? No explicit geometry was guiding our interpolation. Still, there are valid results. It would lie somewhere in between, you know, one type of car and another type of car. And this is, you know, from a network that was trained on a collection of shapes. There's, you know, high chances that the latent space is well structured and we'll get reasonable reconstructions somewhere in the interpolated space. If we don't have a network that was trained on a collection, and we, for example, have a network trained only on one source and one target shapes, then again, this calls for like inventing new types of regularization. So this work from SIGGRAPH this year was proposing to jointly with the decoder also optimize for the Lifshitz constraint needed to guard that we don't get weird behavior in when interpolating between a source and a target. Shapes representing represented as neural SDFs. So a couple of words on you know, going beyond geometry. So I talked mostly about geometric transformations, but of course it's not, you know, that's not the only thing we need. We also need to be able to control color. So in this work, for example, the user is given you know, some input scribbles, maybe on the foreground mask and maybe on the background as well. And through decomposing the network into a shape code and a color code, we can control each of them separately depending on what manipulation we want to do, right? So for example, by training this on a collection of shapes, if I'm giving like a new color to my forward mask on the object, it seems that the network during optimization would learn to follow that input and also recolor the entire surface. Same goes for shape editing. If I wanted to take this chair and remove those two front legs, this time what I'm optimizing for is not the color consistency, but it's actually the density. I'm trying to penalize the density to become sparser and eventually eliminate those legs from the geometry. Stylization is a very important application in images, right? A big question is like, okay, we can clearly learn a nerf on this input set of images. We can render novel views and we can do stylization to each of those views. But what guarantees that those views would actually be consistent, right, is the main question. And the answer is like, we need to make sure that we're optimizing our neural representation, taking into account those stylized inputs, right? So in this work, again, not going into details, they devised like a slightly different way to, slightly different loss term to do stylization that's not propagating the VGG features, but actually taking nearest neighbor in feature matching. So it can capture high details during optimization. There's also cool techniques there on how to do proper you know, patch-based optimization that can work on the entire can propagate the gradients from the entire image at once and not compromise, you know, because we sample rays essentially. Lastly, I want to mention this very recent work that also kind of relates to one of the questions from the audience that we had earlier. Can we learn representations from networks? And in the context of generalization, again, we are borrowing the strength of highly generalizable 2D networks by lifting them to 3D. This time, instead of having our neural field predicting just you know, density and color, it also predicts a high-dimensional feature. We can make sure that this feature matches general representation, like clip, for example, from the input images. Given that, now we know that we can, you know, we have neural fields that can generate useful representations, and we can manipulate it after the fact. We don't have to optimize towards a specific target. We can query in OpenSet, for example, give me the features that match with the floor, right? And then, you know, get as a result a semantic mask of the floor or other objects in the scene. It also gives us very nice handles to do manipulation, right? Because, for example, I could retrieve all the patches that look like, you know, like this patch that I'm taking from one of the images, and suddenly I have those patches retrieved to me from all the input views, and I can delete them, right? So I can edit now scenes. I have a very intuitive handle, either via you know, image patches or via textual queries. Right. So my key takeaway message to you guys is like, first of all, adopting this mindset of neural fields as prime representations, I think opens up an interesting collection of questions to think about and tools that we need to invest research in. And then we covered a bunch of geometric and semantic manipulations through either coordinate or parameters. And I think going forward, I think there's a lot of importance to the way we structure our architectures to become modular so that they allow us this, one reason that we can so nicely control the input coordinates is because neural fields are naturally decoupled into input coordinates and network parameters. The more we decouple, the more we can control things and decouple them, control them individually, right? So think of like material, lighting, geometry, all that. And the other thing is that regularizations are really key here, right? So we saw that coming up whenever we want to become more general, being able to work on scenes in the wild, regularization pop up as like this super critical ingredient. And with that, I think if you want to skip lunch, stay and ask me questions.
We can take a couple of questions for those of you who want to stay, but just we're going to take a lunch break now, and we're going to reconvene at 1:30. So looking forward to seeing you all back again. But if you have any questions for Or, please feel free to ask them.
Go ahead. Yeah, speak up so you'll cover the noise. Yeah.
In case of the editing network parameters, it seems like they all uses the latent codes. But is there any works that directly edit the network weights instead of the latent code?
Let me try and think. Yeah, there's no real reason to only control the. First of all, a lot of the optimization, for example, the editing geometry work that I showed wasn't actually manipulating the latent codes condition. It was manipulating all of the network parameters. And what he was using a regularization to make sure that you don't. There was a shape preserving term that was making sure that you never deviate too much from your original set of weights. But it was the entire network parameters essentially, not just the input latent code. And same goes for like the editing in radiance field that I showed, right? So it was again trying to the user was giving a scribble, wanted to paint red a part of the forward map of the object mask, and then during optimization, there's a regularization term that keeps the network parameters close to their original values, but yeah, it was basically. Oh, sorry. In that case, you're right. In that case, it was also conditioned on the input codes. Yeah. Sorry, I take that back. But the previous example is controlling the entire network parameters. Yeah.
Thank you for the talk. I was wondering whether you believe that, I guess, neural fields will ultimately come to encompass sort of like the only representation of what we need in a streamlined evolution pipeline. Because, for example, you cited the unit work that proposes like these analytic ways of deriving like geometric features from neural fields. At the same time, though, I know something like computing curvature is highly sensitive to like sampling as well as like quality encoding in the neural field itself. So I was wondering whether you think like in the future we'll inevitably have to converge onto like hybrid pipelines where we're mixing and matching these different representations.
So your question is, just to repeat, is like are these going to replace
everything?
Primary representation? Everything is going to be that's a fantastic question. I think I'd be very surprised if that happens. I can give you my intuition on why that is the case. People have been asking, just maybe one way to look at it is people have been asking about unifying representations for 3D, for example, for a long time, right? Before the emergence of neural field. And it seems that, because each representation brings its own advantages and disadvantages, they coexist. Right, all these different representations coexist, not just because they are prime in the sense that they are the output of a sensor, but because they're, for example, they allow an easy API and easy usage for animators to do manipulations on them. If you think of like an animator working, an artist working and changing network weights directly to control the resulting shape, even the thing that needs to display the resulting shape to the animator is going to have to, maybe translate this first to a mesh and then present it. So I think we'll have to decode. In a way, one way to think about these representations maybe is to adopt this compression mindset in a way, right? So you have a compressed version, you can use it to send over, but when you want to view this, you have to decode, right? I can send you a video as a file, but if you want to watch the movie, you have to decode it on your TV and play it frame by frame, right?
Yeah, thank you.
Yeah.
Maybe if like fields take off, we won't need any meshes for.
But I will say one thing though, that it's very important to think of them. I was talking about manipulation, but you could also think about other downstream tasks, for example, classification and segmentation that run directly on the neural field representation. So if I took my whatever ImageNet collection and mapped it to a neural field, basically each image is now just a set of network weights. I need to be able to answer the question, okay, given a set of weights, is this set of weights a cat or a dog, right? So there's this really interesting work called your data is functa or something like that. Functa is the keyword to look for, and in this work they explored exactly these type of questions.
So in physics-based simulation, you use discretization of the surfaces with triangles or tetrahedron, right? And then all the energies that are based on these discretizations. So I was wondering if you know any work or any direction that tries to embed physics-based simulation into our neural field.
Yeah. There's a bunch of physics-based papers that relate to neural field, but I admittedly know very little about that. So
okay, I mean, my point was that to be a time representation, maybe you have to be able to have also some physics-based simulation. You need to be able to account for a physics-based simulation.
Simulation or constraints? Are you talking about the
in simulation, right? When you have a deformable model, and you want to simulate how it deforms based on forces, etc. Right? So maybe to be a time representation, you should also be able to maybe simulate using this representation.
I'm not sure. Yeah. So what is the question?
So the question is, with neural fields, you would be able to do physics-based simulation, which are mostly based on discretization of the surfaces, which basically measure energies of deforming triangles, etc. So with neural fields, I'm sure there's a way to do that.
Well, I mean, if the answer is like you could always make a simulation step and then map it back to a neural field, I think.
Yeah, exactly. So you would need to discretize, compute something under a discretization representation back to neural field.
Right.
I think it would be cool to,
fully agree. Directly. Yeah, that's where I was going. So I think like if you can imagine that process being done, explicitly and then mapped to a neural field, I think it's a very relevant question to ask, how can we do this directly on the neural field?
That's what I meant.
And completely agree. Much like we need to devise like classifiers in neural fields, we also need to learn physics-based update rules, right, on neural fields. Yeah, I don't know of a work that does that. Yeah.
Thank you.
Thank you.
All right, so welcome everybody. I hope you're fed and watered. The neural fields in computer vision tutorials so far has covered techniques this morning, including architectures, hybrid representations, forward maps, generalization, and manipulation techniques. And now in the second half, we're going to cover how applications across domains such as 3D reconstruction, digital humans, fit into these categorizations to help us all understand how to think about neural fields within this framing. So there's about 2 hours of us covering all these different interesting applications. And then we have our invited speakers after a short break that we're all very much looking forward to. In terms of timing, the invited speakers will start at about 3:30. And so we'll run now through these different applications until about 3:10, 3:15, when we'll take another break. Okay? All right, so with that, let's get on to the first of our applications, which is 3D reconstruction. Hello, I'm James Tonkin. I'm an assistant professor at Brown University, and I'm going to be joined by Vincent Sisman, who you already know from earlier. The general framework for which we might think about neural fields, just as a recap, looks something like this. I have some space of coordinates, typically space-time, x, y, z, t, that are going to be fed into the neural field. And then I have some kind of reconstruction domain. It could be an occupancy or radiance field. It could be a distance field. Then I have my forward map, such as volume rendering or sphere tracing for SDFs. And then I have the images that I have as supervision that I'm going to use to reconstruct my domain. Okay, so what we can measure are things like RGB images, sometimes even depth images, too, from active sensing. What we really want is the reconstruction domain of surfaces, of appearances, and then the forward map is the bridge that allows us to optimize through from the final images back to the weights of the neural network. Okay, so within that framing, what kinds of tasks do we want to perform within 3D reconstruction? So the classic one you might also call inverse graphics. And the work over the past few years has posed this problem as given images and camera poses, how can I estimate the geometry and appearance of some static scene? Of course, there's the dynamic version of this where I now try to estimate moving objects within the scene, a significantly harder problem. Then I have the problem of trying to estimate the camera poses in the first place. Typically, this is assumed through some classical structure from motion method, but now that we're finding new methods that can also simultaneously at least improve, if not optimize for those camera poses in the first place. Along the way, we have help from active sensing, for instance, depth cameras or time of flight cameras. And sometimes these produce what we might call a point cloud. And then there's this whole other area of 3D reconstruction with neural fields that you would consider as shape reconstruction or shape completion, where given those initial points, my goal is then to estimate what the full shape of an object might have been, including using priors for like class-specific objects, for instance. Now, there's a lot here, and we're only going to be able to cover some of it. But let's just cover some of the classic settings within 3D reconstruction. So we're all familiar with like outside-in, like array-based or stage-based representations using structured or light-filled captures, or even unstructured. And then we have inside-out settings, 360 camera style. Starts to get a bit more complicated there because the baselines are smaller, and so your estimates of what the surface geometry, where the surface geometry is going to be worse. Things get even worse when you think of single images capturing video. And then in the particularly worst case, sometimes our community even attempts single image 3D reconstruction, where I have to then rely significantly on learned priors for geometry and appearance. Okay, we've already talked about occupancy fields and sign distance fields as ways to represent different kinds of shape. Within our process of optimizing our final representation, we might also use points and meshes. These are typically samplings of fields. Another area that's becoming popular right now is considering not just surface meshes, but tetrahedrons for volumetric-based meshing. In terms of appearances, typically we're used to radiance in the classic radiance fields formulation in a view-dependent sense. We can also consider representations like surface light fields, where radiance is parameterized on a surface coming towards the camera. More complicated representations of appearance consider a physically based pipeline that is based upon a bidirectional reflections distribution function, or BDF, examples of which might be the Zhong model or the concurrence model, which is very popular in computer graphics. And along with that, then, I have to also have a complementary lighting representation, such as an environment map or a spherical harmonic frequency style spherical encoding of the lighting, or spherical Gaussians, many different kinds. There's very interesting upcoming work at CVPR that considers these. This is from Lundberg and colleagues from NVIDIA. Of course, the problem when you're trying to estimate material and lighting properties is that it's incredibly ill-posed. There's always a transformation between the two where I can scale the reflectance of the material and scale the reflectance of the lighting to come up with the space of problems. This is very ill-posed. The other problem is that any kind of estimation of explicit material and lighting needs very accurate normals. So you need good geometry. Okay, we're familiar with our MLP as a representation, as a parameterization, sorry, of either of these geometries or appearances. We're now starting to see neural fields based on transformers. And then Tawaki gave us this interesting space of hybrid discrete continuous neural fields that cover voxels, hash maps, point clouds, meshes. And then we also have newer representations in a hybrid sense that factorize these, such as tensor or these triplane or ground plane representations that Vincent was describing. Okay, and then finally, to recap the different ways that we can infer scene models. Most of the settings that we're going to pose have a per scene optimization, but sometimes we're going to integrate some of that knowledge from what materials look like, for instance, to use pre-trained BRDF embeddings. And then when we consider generalization, we're going to think about feature encodings either through CNNs or things like auto decoding, as Vincent talked about earlier. Okay, so using this recap, we're going to try and build some kind of taxonomy and show you where a set of methods, recent papers, fit in with this framework. Disclaimer, there are so many neat papers that we cannot possibly cover all of them. So we're just going to give you just a few points within the space. Sorry to everybody. We love your work too. We're going to completely also ignore this space of 3D shape completion, but thank you very much. We read your papers and they're great. All right, so with that, I'll turn up to Vincent, who's going to give us the first of our taxonomy.
Cool, awesome. So yeah, we thought about what is most useful. Instead of explaining each paper, you know, and like how it works and so on, we're only going to touch on them very briefly and very high level. And I think the key takeaway from this section should really be using the techniques that we discovered and discussed earlier in this workshop. Can we classify lines of work or trends that we're seeing into this framework, such that maybe afterwards you can both think about new ways of combining the things in this toolkit and understand, you know, with how these different parts fit together. And so we consider four dimensions of neural fields here. So one is the field parameterization, one is the geometry and appearance model, one is the forward map, and one is the inference model. So field parameterization could be like MLP, transformer, hybrid. Geometry and appearance could be density plus radiance fields. Forward map could be volume rendering, and inference model could be auto decoding, just to give you an idea. Okay, so as an example, let's take a look at NERF, right? So this is just to get you familiar with the framework. How does NERF work? NERF has this field parameterization and MLP, right? It's just a neural field. The geometry and appearance model is basically a density and radiance, so it's a radiance field. The forward map is volume rendering. And finally, the inference method is per scene optimization, right? And what that leads to is like this combination of like these four dimensions yields high quality, but also slow rendering. It's very expensive in the forward pass, but we don't need much storage for the because we don't have like a voxel grid or something that grows kubically with memory. It sometimes leads to noisy or cloudy geometry and requires many images. So this is just as an example of how we will look at papers in this framework. Okay, let's take a look at one trend that we've already discussed, but now we're going to specifically discuss it in this framework and then this framework of multi-view and 3D reconstruction. Oh. Hybrid conference is hard. There we go. Yeah, click. Nailed it. Okay, great. So
really extreme.
It's very hard. Okay, so we discussed a nerf, right? Okay, so here's a trend. One trend is, of course, we're going to speed up radiance fields with hybrid data structures. And so here's how this framework works, right? 3 parts remain identical, like still the same radiant appearance model, still the same forward map, still the same inference model. Now what we're going to swap out is basically the field parameterization, and then we're going to see what happens, right? So as an example, here's planoxels. What does planoxels do? The field parameterization is a voxel grid, and we do direct optimization of the voxel grid. Also, direct voxel grid optimization falls into the same bucket. So all that is, this is like a simplification, of course. There's many parts that make this work well, but the key idea is we're going to replace the MLP with a voxel grid. Then next is neural instant NGP or neural graphics primitives, right? Here the idea is we're going to replace the MLP with a voxel grid plus hash map plus tiny MLP. Point nerf and point-based approaches where we're going to replace the global monolithic fully connected neural network with a point cloud, and then we locally decode that point cloud into densities and radiances. And then there's this recent line of work of triplane representations and tensor factorized 3D representations. And that would, for instance, be EG3D or tensor. Okay, so all of these have in common that they are all towards faster fitting, faster rendering, lower memory footprint in the forward pass. They sometimes may achieve higher quality, sometimes they're slightly worse quality than NERF. The key trade-off that you're often striking is now you have to, as Tawaki discussed earlier, somehow deal with this complicated data structure, or you have. But that's just simply a straight trade-off. Okay, so that was one trend in like half a minute. Next, we're going to move to hybrid volumetric and level set representations. This is another interesting trend. So here, same framework again, everything stays the same, just this time the geometry and the appearance model and the forward map changes slightly. I see we actually didn't update the forward map, that's fine. So what is the key difference? So 3 examples of this are Unisurf, VolSDF, and Noise. All of them came out at the same time. The key idea here is that instead of having the radiance field just be parameterized by a density and then radiance and then just solving this volume rendering integral, we're now going to express the density as a function of one of these level set based geometry representations. So like a sign distance function or an occupancy function. And by coupling, by relating the volume density and the occupancy function, what you get is that you now actually have a well-defined surface. This is the key benefit of representations, that like you have a well-defined surface, like you can see here in the left for the surface rendering thing. But you still get the convergence properties of volume rendering and the high quality of volume rendering. So this is also really cool to see. Has well-defined surfaces. The geometry is significantly better that you can pull out of this. You can also render it slightly faster at the end. It's good for solid objects, but it's not that good for complex scene phenomena, right? If you have like glass or something like this, then sometimes this assumption of a well-defined surface bites you. Okay, next we're going to come to neural light fields. In this case, the 4 dimensions actually are all kind of busy, which is unfortunate, but the field parameterizations here are usually MLPs or transformers. The geometry what we discussed in the generalization section earlier, the geometry model in this case is kind of this a case of the trivial forward model. Like, what does it mean to have a light field? It's a function that maps the ray that you're observing directly to the color observed by that ray without doing volume rendering in between. So now you're directly parameterizing the light field instead of parameterizing the radiance field and doing rendering. So now the geometry and appearance model is just both this like this light field that maps like rays to colors. The forward map in that case is usually identity, but there's like a little catch where we still might want to do alpha compositing, and then inference is also all over the place. So let's talk about these. So light field networks basically is this idea that we parameterize the light field of a scene as an MLP, and we used auto decoding in that paper to do inference. So we generalize across scenes, and then you can reconstruct a scene by doing auto decoding. And then there's a scene representation transformer, which I mentioned earlier already, which both parameterizes the scene and does inference via a transformer. And then this is the little catch that I was discussing. So this is actually a good opportunity to clarify this. there's recently been a lot of papers that also have light fields in the name. What they do is that they still have they still do sampling in 3D. So similar to NERF, right, where you shoot array, you sample points along the array, and then you do volume rendering. These papers also raise and sample 3D points along the rays, but they take a particular perspective on the alpha compositing step, whereby each of the samples isn't just a pointwise radiance, but each of the samples per a little light field around the point where you're sampling. And so one example for this is this neural light fields paper. There's also another one from Amish at folks at Zhong. But this is a good thing to keep in mind. So this light fields term is a little bit overloaded. So sometimes it really means it's a function that maps ray to color, and sometimes it means you still have to do sampling in 3D. And so light fields, I'm very excited about them. They trivially achieve real-time rendering because there's the forward map is just the identity. They naturally, in principle, model multi-bounce lighting effects because it just amortizes the whole multi-bounce thing. But what happens is that this is very much an unsolved problem. They have very little inductive bias. There's no 3D inductive bias anymore. So single scene optimization, for instance, is difficult. And the results we've seen so far are far from photorealistic. Or for the pure light field models, they're not photorealistic. Cool. So that was that. Now James is going to talk about a few more things.
So when it comes to trying to go beyond radiance, I now want to factorize my appearance into lighting and material. So here is in the visualization there we see a BRDF, then we see a visibility term, and then finally the albedo appearance. And when I put all of these things together, I can render a final image. I can change the lighting conditions onto the image. So I have extreme flexibility into how to create this view. But 3 or 4 intersecting parts that all have to be estimated to produce the correct result. So how do I do this? Well, I'm going to introduce pre-training of some of my components. So here's the physically based model for how this is achieved. And you can see that it's split up into 5 different MLPs, each a neural field that are doing some. The blue BRDF MLP is this pre-trained embedding of material reflectance, okay? And then you also see that I have in green this light visibility MLP and the normal MLP, and these are built from a pre-training of the density of the space. They define the geometry via the normal for light interactions, and then they also represent by the light visibility MLP the light transport of the scene. And this approximation of the true light bouncing everywhere allows us to solve this problem in a compact way via the neural fields. So this is one of the first methods that's out that actually has like a component in its neural field representation for each of the parts of a classic computer graphics pipeline. Some approximations as stated. So BRDF embedding, we use this initial nerve density for doing things like normal and visibility estimation, and it produces us these plausible things for visualization. Forward, we're going to move towards trying to use these for measurement, as in trying to estimate the exact physical properties, rather than just their use for visualization. Okay, but what if I want to do some kind of lighting decomposition, but I don't want to go all the way? So an intermediate case that's going to be a SIGGRAPH this year is splitting the appearance into things like view independent or diffuse illumination and the effects from view dependent illumination. And this is easier to solve because I don't have to go and estimate all of my complex visibility and BRDFs, but it gives me less flexibility. I can't do things like relighting. I can't do editing in quite as easy way. But I'm able to do things like separate, in the video you'll see in a second, separate the diffuse illumination, which is just that, from just the reflection component, which is just that, which is the light that's being reflected off the ceiling onto the floor. Okay, so there's a lot of work in this space. We only just covered 2 points, the full decomposition and then this kind of hybrid decomposition to get you some of the flexibility while still maintaining some quality. All right, our whistle-stop tour continues with dynamics. When I have dynamics in my scene, typically my geometry and appearance model might introduce some kind of flow, this F in the top right-hand corner. Dynamics are so hard that the easiest first setting might be the multi-view video setting. So let's play the video. In this case, I'm going to set up, say, 12 cameras and have them simultaneously capture a dynamic scene. Then how do I encode this within my neural field? Well, I work at CVPR from folks at Facebook. This DyNerf model says that kind of latent auto-decoded representation for time. Time is a very complex effect that has all kinds of disocclusions, deformations, topology changes, and I'm just going to let the neural network learn an embedding for time via this latent code through an auto-decoding scheme. At CVPR last year, we had neural scene flow fields. This increases the complexity of the task. Now I just have a single moving video camera and to solve the same problem. This requires me to separate the scene into 2 parts, a static part and a dynamic part. And you can see that there are 2 MLPs there in the field parameterization, the results of which are put together to produce the output. And then I've also added, or the model has added, this additional term. Not only do I estimate the flow field explicitly, but I also estimate these disocclusion weights for representing what has and has not changed within the flow field through time. Now, because this is such an opposed problem, there's additional priors that are added, such as depth regularization, to help solve the task. Okay, the last paper that we'll look at is HyperNerf. HyperNerf says, when things are moving in space, such as my mouth that's opening and closing, actually the flow field becomes tricky because the topology of the geometry is changing. Okay? So HyperNerf says, I'm going to lift these dynamics into a higher dimensional space. This is like hyper. And I'm going to have an MLP that represents the deformation field in space, and then an MLP that represents a slicing surface that at any particular instance in time tells me what the deformation field can be. This slicing surface with the deformation field, and that allows it to more robustly capture things like a human being speaking. Okay, so 2 different ways. There's like a literal way, anyway, or a auto-decoded latent for representing time. And they've all been shown to work with various different trade-offs. We can represent topology changes to this hyperspace, but if we're going to do so, typically we have to add some additional priors to get the options in the field. Represent rigid motion, deformable motion, especially within complex real scenes. Just imagine going outdoors with trees and wind blowing everywhere. And then the second core question that still has to be solved is how to represent voxels increases, though I gain in speed. Marry that with long time scales while still being. Okay, let's go back to the very first problem or assumption that we made within the field, which is that I know the camera poses. we'll just highlight 3 works to show that it's possible to at least improve the initial camera poses that come from structure from motion. There's nerf minus minus, iNerf, which shows when I'm doing, I just intelligently sample scene points based on how interesting they are in the classic sense of interest points, or equivalently interest regions. Then I can significantly reduce the cost of optimizing the camera poses. Think that every time I want to whole image to be able to assess poses. And then at the end of last year, the creatively named bath was announced. This produces more accurate poses. It says that, this is an interesting twist, in the network's architecture that's caused by the position encoding actually harms optimization of camera poses because it more easily focuses on the high frequency information. And this leads to or like more local minima poses. And if you can just solve this problem in a cost-defined way, use a cost-defined positional encoding over the optimization, then you will do better. Great. A last comment on active this year is that if I have a depth camera, I can do construction significantly better. What I'm going to do is supervise the rendered ray termination depth within the volume by a Gaussian that sits over the depth value that comes from the depth sensor or comes from structure from motion. And then I'm going to scale the difference between those two, and it produces me significantly better results with very, very few samples. So you can see this would help in the single view setting. And at Neurox, we show work that does this for time of flight using continuous wave time of flight is common or being integrated these days. And with this, you can achieve more accurate, less noise, get around the limitations of the sensor through this interface. Okay, so this is all things we can do with multiple cameras, different priors, but what on earth can we do for single images?
Very dramatic. So we all much of this in the last sections. I'm going to go over this very quickly. I think the key takeaway here will be, again, to just think about it in this little framework here and think about that anything you can see, right? Paper you can see, and you also always swap out these things less independently. And this can be a very good way of like exploring new kinds of ideas. So this is based on prior-based reconstruction from single images. Let's go through it very quickly. So we already talked, for instance, about scene representation networks, which is like a single monolithic MLP representation, globally conditioned via auto-decoding. Then we talked about pixel nerf and these pixel-aligned radiance fields, where now this is a hybrid representation, right? Because you have your MLP, but then you also have your hybrid image grid that you're locally conditioning on. And the inference model here is encoder-based, but you could also do it auto-decoding based, maybe. I haven't tried that yet, would be interesting. And then there's like another one, which is code nerf, which basically just showed, look, you can think about disentangling geometry and appearance as well in a very similar framework to scene representation networks. And then I had already mentioned, like, ground plans are another thing that you can infer from single images, and you could do a single image 3D reconstruction by inferring a ground plan that parameterizes the radiance field. Cool. This is basically it. The key thing is here, we can't talk about everything. There's so many papers you have to categorize for yourself. We hope that the Eurographics star report that we wrote is helpful in that thing. So things that we're particularly excited about that we didn't get to talk about is 3D reconstruction from 3D observations. We completely left that out, right? That convolutional occupancy, deep SDF, like, there's lots of stuff on just 3D reconstruction from 3D observations, which also neatly can be put into a framework like this. Then there's the unconditional 3D generative models that we're going to hear about a little bit more about in the next section, like EG3D, PyGAN, that line of work, which is exciting. There's object-centric representation mentioned in the section, and then there's this intersection of nerfs and foundation, basically training, it's like clip nerf or training on dinos. Okay, and this is the outlook, but it doesn't. Any questions? Okay, so should we do the outlook? Cool. Any questions? The microphones might have to be switched on, but.
First of all, thank you because that was really nice. I ask two questions.
Sure.
Mostly, you said that for example, they need to have visibility to its target, like target shadow.
Shadow, yeah.
Yeah. Do you think that there's a way of doing easy to compute by having different illumination, use of from different illuminations?
Yeah, so it's quite hard to use this illumination like in the real world, but it's yes, to help us.
They use an embedding for the use of I think that they use different both things. And they use learnable embedding for the
That's right, yeah. So on the rest of the, just take the it comes about in exactly what the rest of the parameterization percent. Right? There's an interplay there between and what exactly your representation of form are. Significant analysis for here. And I think people are still trying to understand exactly what works and what doesn't, but is positive. Thanks. We don't know if anybody has any further questions, but we will then move on to the next application.
Quickly flash this here.
Sounds good. Oh, you screen share. Or you screen share.
Yeah.
Yeah, cool.
All right, thanks, James and Vincent, for that great talk about 3D reconstruction. Again, just to kind of situate ourselves where we are in this tutorial journey. So we are in the applications part. We just talked about or looked into 3D reconstruction. We're going to have Tawaki talk about generative models next. And we're also going to have Shunsuke go right after for neural fields and human reconstruction and so on. So Tawaki, take it away.
Thanks, Srinath. Let me share my screen. Hi, everyone. It's Tawaki again. I'll be talking about generative modeling. And I'll probably try to make this quick. And most of this presentation will be a feature of some of the generative modeling works at CVPR today. So Generative modeling basically involves some kind of latent distribution where you assume that whatever data that you want to generate kind of exists on. So in this case, it might be the distribution of human faces or something like that, which exists on some kind of latent distribution. The goal of, and I'm gonna give a not necessarily the most robust definition of generative modeling.
Can you switch to
monitor? A little
monitor?
bit, easy to understand. I'm not gonna go into any of the details, but basically, in a lot of these generative modeling applications with like GANs and everything, you have some kind of like generative network that basically maps your latent vectors that you sample from this latent distribution to your whatever your signal of choice is. So this generative network is a function that maps from your vector from the latent space to, in this case, an image. And for images, this is kind of like generative network thing works pretty well because you have these convolutional neural networks and the inference times are like reasonable for 2D cases. But if you want to do, for example, 3D generative models, this becomes all of a sudden super difficult because in 3D, first of all, if you want to generate something like meshes, you have to worry about topology, connectivity, all that kind of stuff, which is super difficult to reason about with these generative networks. And if you want volumetric data, that's going to be like this, huge 3D function. And we just talked about, how these traditional discrete representations and voxels and stuff like that are super memory expensive. And things that like 3D convolutional neural networks are super also expensive in memory and also in compute. So it's not super clear right now, like what the best representation to like generate this kind of 3D data is. So given this, something like neural fields seems like a pretty promising alternative to generate 3D data, where basically neural fields, whatever parameterization you choose, you might use like hybrid representations, or maybe you want like just like a pure neural network-based approach. Whatever you want to do, they basically provide like this compact parameter space that you can work on. So basically your pipeline might look like something like, you sample a latent vector from your latent distribution and you use your generative network to generate a neural field instead of generating 3D data directly. This is kind of like the idea kind of like shared by DuPont in their paper. In their paper, they basically propose that, instead of generating this data directly, you should be generating functions instead. And in their case, functions, basically they mean like generating neural fields directly. So they show that they can do this kind of like setup and they can get pretty good approaches, pretty good results on something like human face generation. But they also find that they're using the same exact architecture. They're able to also generate objects from like 3D and also like other data, like data that exists on like a 2D manifold or something like that. So this is kind of like a nice approach that unifies kind of a lot of different kind of generative models inside a single framework. And if we can kind of like, the idea is that if we can kind of like optimize for this and make this work really well, then we can make this generalized to a bunch of different kinds of data, which is really exciting. Nonetheless, though, generating all the neural network parameters can be expensive. So a lot of different works kind of like think about different ways of trying to do generative models with these 3D data. And basically one of the ones that we already talked about a little bit, and this is also a CVPR paper this year, is EG3D. Yeah, again, just to quickly say, if you use the StyleGAN feature maps as the feature grid for this like a generative model and uses all the StyleGAN components to get really nice 3D reconstruction, 3D generative model results. On the other end of the spectrum, so that was the previous one was kind of like the extreme StyleGAN, big model kind of approach. On the other end of the approach is this more autodecoder based approach, where you basically on the bottom, you basically have like a latent table of like, per observation latent vectors. And basically the idea here is that for each of your training images, if you're able to have like a pretty good idea of where the camera is looking towards your face, basically they find that by basically fitting this model, even though you're for each specific face, you're only fitting it from a single view, by training like this unified neural field model that takes in these latent vectors and maps it into faces, they're basically able to get pretty good results on human face generation, even with this very simple setup. So this is kind of like the opposite end approach to like the whole like EG3D type setup. There's other approaches that also do this kind of setup. This one's UNIST, which is also a CVPR 2022 paper. This one also similarly to like kind of like the EG3D stuff. They basically predict these like planar like feature grids. So in this case, it's like latent grid that they do bilinear interpolation on. And just beyond like simple like generative models that actually use a generative network to output stuff, there's also really cool stuff in like doing like, text embeddings and stuff like that, where in dream fields, basically what they're trying to do is that they're trying to optimize a neural field model that basically tries to follow some kind of text prompt. So in this case, on the right side, you see a bunch of like generated neural fields, neural radiance fields, which came from this prompt, teapot in the shape of like, for example, Pikachu on the top right. Yeah, so those are some of the works from CVPR 2022 that I highlighted, but I'm sure there's a bunch more that's missing. If you think that these should be highlighted, definitely let us know. And nonetheless, I think that there's a lot of exciting also open research questions that we can look at. One of them is kind of like generative models for non-local information. This is a little bit similar to the stuff we talked about, for example, like, someone asked a question where it's like these like global models are not really spatially disaggregated, which basically means that, if you change one parameter of your neural network, it's going to affect everywhere else. That kind of means that if you want to generate, models, this is kind of becomes a difficulty because when you want to generate these different models, it affects all different parts of the space. So you can't use like there's not really like an elegant way of using like a spatial reasoning to design like an autoencoder for this kind of data. And this is also true not just for global neural networks, but also for stuff like hash grid nerves and stuff like that, where you have like a code book of features where it's like randomly allocated space. And you have like a very clear separation of like space and feature. I also mentioned this one earlier as well, but I do think that this is a very important one, which is, generative model for complex data structures. We really don't really have any very many examples of this. Shapeformer is really the only one. And yeah, this kind of data, if we can generate, like these sparse grids and like complex data structures, even if you don't actually generate the neural fields part of this pipeline, if you can just optimize and generate the grid topologies, you can use this for a bunch of different applications down the line. So I feel like this would be super exciting area of research. And yeah, that was a super quick overview of all the cool generative modeling stuff going on at CVPR this year with generative models, neural fields. Thank you. Yeah, so I think the significance of that paper is that it kind of shows that, like, even if you have this like unified framework for doing like generative models on different types of data, basically using that same architecture, you're able to generate all kinds of different kinds of data, which is something that has never really been shown before in other types of generation methods. You might argue that this kind of thing is like, just like coming based off the fact that neural fields, can represent all sorts of data. And I think that's exactly what it is. And I think that there's also like a really interesting research direction in the sense like, if you want to generate, for example, like a distribution of cats in 3D and distribution of cats in 2D, there's probably a lot of like shared weights even that you can share between those two types of things. And there's not a lot of research that's going on in that kind of research right now. So I think it kind of inspires stuff like that, I think, which is, I think, the significance of that specific work.
All right, so let's start the human section. Hello, everyone. I'm Shinsuke Saito, a research scientist from Reality Labs Research. So in this presentation, I'm gonna walk you through recent advancement in digital human enabled by neural fields and discuss open questions. So let's get started. All right, so first let me motivate you that like why like neural field is important or the good representation for digital human applications. So first, we all live in a 3D world. And there are many applications in 3D space like AR and VR. And as earlier talk explains, like neural field is particularly suitable for 3D representation, 3D modeling due to its memory efficiency. Another thing is resolution. For human, we care about the quality. So enabling high resolution synthesis is also pretty important. And we wear clothing, and everybody has different like a hairstyle. So to handle the complex topology, we need a volumetric representation, and the neural field can naturally handle such a topological changes. And for human specifically, so we have joined and we are articulated, so we can change poses. And this also like poses like another challenges. And as Or mentioned in like neural field manipulation, neural field also naturally support coordinate transform, which really goes well with human articulation, which I will talk in the later slides. So first, just following up on Twaki's generative model session. I will briefly talk about how generative model can be used for digital human application in particular. So here's a schematic view. Given an input image, now we have a powerful generative model that can span realistic human face in a 3D space. So what we can do is we can find the mapping and the latent code Z that best explains the input image and the camera parameters because it's a 3D. And once we enable such a fitting, you can simply apply different camera parameters to produce a new, novel synthesis in a 3D consistent manner. Or you can optimize with regard to the latent code Z, such that you can optimize in a semantic space. So here in the style nav paper, for example, people use a clip loss to enable the editing of 3D human based on text prompt. So in the EG3D paper, they also demonstrate that their state-of-the-art inversion method for 2D style GAN can be directly applied to 3D GAN because we have a forward map of a differentiable rendering. So this allows us to generate the 3D version of linker just from a single image. So here, let me give you a couple of open problems. The first, I've never seen any complete 360 degrees, a rendering of human head from generative models. I believe this should be addressed by both a data perspective and the learning perspective. But this is definitely one open problem. Another thing is, so far there are many recent papers that demonstrate the learning of 3D face from image collections, but still extending it to a full body human is still challenging. This is partially because of articulation, and I will discuss a bit later about how to handle articulation. And another thing is, so far, most of manipulation techniques are just simply reusing the manipulation technique developed for 2D GANs. And since we have everything 3D now, it'd be great to have a more semantic, 3D aware semantic manipulation. That's another good open question. All right. And also, for human, we often leverage parametric models such as 3D multiple model or SMPR model, and they open up many research programs and in the computer vision community. And recently, many papers extend those parametric models to neural fields, including face, hair, body, and clothing. So the question would be, what's the benefit of using neural fields for parametric models? The one thing is a higher degrees of freedom. So as I mentioned, there's no kind of resolution limit for the neural field type of representation. And it's particularly suitable to represent person-specific details. And now the community is more and more interested in a human and scene interaction type of application. Dealing with the penetration and the collision is quite important. And the volumetric representation allows us to effectively resolve such a penetration and the collision. And in that case, over the mesh-based approach, we can quickly resolve those collisions. That's another advantage. And for closing, so if you use mesh-based representation, it's really difficult to represent different kind of clothing because they have a different topology. So by using our neural field, we can represent different topology of clothing using a single network. And traditionally, to enable this learning of parametric models, people often first fit the template model to 3D scan or images and so on. And this is called surface legislation. And many recent papers also ease the problem of surface legislation by solving a neural fields for surface legislation, including deformation fields or 3D dense correspondence field, multi-part occlusion occupancy fields, and piecewise transformation fields. I'm not going to go into too much detail on those paper, but if you're interested, please check them out. All right, so still the surface legislation is a very challenging task, especially for textureless region or changing the clothing and so on. So another great use of neural field is to completely sidestep the surface legislation process and learn a parametric model directly from raw data, such as point clouds or images. So they're kind of presented in a different context, but in principle, they share many methodologies in it. And the difference here is first input modalities. So either we use 3D scan or images, we use different types of word mapping, which we discussed in the earlier part of this tutorial. So if you have a point cloud or 3D scan, you can directly leverage the identity mapping and supervise in a 3D space using sign distance function or occupancy. And if you have images as an input, you can simply apply a differential rendering technique to map your 3D avatar into 2D space. So from now on, I'm going to focus on how we deal with articulation in our neural fields-based avatar modeling. So pioneered by NASA papers, one common approach is to leverage articulated compositional neural fields. So instead of modeling a single whole body shape under different poses using a single network, we can let small subnetwork to figure out local deformation of each body parts. And for human, we have a joint transformation already, so we can simply apply the transformation to each local body part and then compose them together. And if you have an occupancy field, for example, to compose, we can simply apply max pooling. So there's a closed form solution. And if you use SCA for reference field, where we care about the smoothness, another approach is to use the neural composition. So here, what I mean by neural composition is you can take intermediate features or output from each subnetwork and then feed them into another neural network to figure out the final composition value. So in summary, those articulated compositional neural fields are the advantage of articulated compositional neural field is its simplicity. So you can easily compute the inverse of transformation and use it for optimization tasks. Therefore, articulated compositional neural field is particularly suitable for downstream tasks that involve optimization, such as analysis. On the other hand, since it's completely localized, it's challenged to incorporate non-local deformations such as closing. So if your deformation spans across multiple body parts, such a local composition model might not produce a good result. And another approach to deal with articulation is applying a linear blend skinning. So if you're not familiar with linear blend skinning, so linear blend skinning is a common technique to enable character animation in computer graphics community. So to figure out the transformation of every surface in a canonical space, you represent the transformation by the linear combination of every single joint. Here denoted as a W theta. In a traditional computer graphics, those skinning weights are defined on the vertices of a template mesh, and the Scanimate and the lead paper extend this to the neural fields or the skinning fields. So you can define the skinning weights or the contribution of each joint everywhere in 3D space, and this allows us to transform human body or object in a unified way. So the difference from this articulated compositional model is now we have another network which predicts the skinning weights. So how we train them? So there are two main approaches for that. So one is we can define another neural network for the inverse direction from port space to the canonical space. Here you can see that there's a cycle consistency. So you can inject it as another regularization to jointly solve this forward skinning network and backward skinning network. However, the one drawback of this approach is the cycle consistency is only added as a soft constraint, meaning there's no guarantee that you can actually map in a one-to-one from port space to canonical space. And to address this, SNARF proposed to solve this only using a forward skinning weights W theta. So you can see that only here, we have a single network W theta, and what we want to solve is the position XC given the port space XP. And here's the equation down below, if you see my cursor here. So between the canonical space and port space, this equation should hold. And we can solve this equation with respect to XC using our iterative root finding algorithms. And this way, we can solve inverse skinning problem in a unified manner. And they show that this leads to better generalization. So in summary, skinning-based and like LBS-based articulation handling give us a smooth deformation space, and also it's compatible with a classical character animation tool, similar to SMPL model. Therefore, it's more suitable for closed avatars and animation purposes. On the other hand, LBS is notorious for its cantilever artifacts, and also as an iterative root finding algorithm is an optimization, it requires some time to compute the backward warping. Therefore, it's if you want to inject this for analysis type of application, this may be a bit slow. So there's a pros and cons for articulated composition model and the LBS-based approach. So another extreme is to, instead of using LBS, we can simply figure out all the articulation using another neural field or deformation fields. And a similar approach is also used for NAFIs for head modeling. Since we use neural field as a post-shape deformation, it's more expressive than LBS, and it can potentially address the limitation of LBS. However, the post space is typically represented as a latent space and difficult to comprehend. And also it requires a lot of data to generalize. So more recently, people start incorporating the multiple ideas together to overcome the limitations. SPMs, for example, combine the articulated composition and deformation field together. And neural GIF, human nerve, and self-recon paper combine LBS and deformation fields to overcome the limitation of LBS. Those underlying papers are CVPR paper this year, so if you are interested, definitely check them out. All right, so there are a couple of open problems. First, still the training of the neural body takes quite a lot of time, and fast training and inference is a quite important problem. So in this year's CGraph, we will present a paper about enabling real-time rendering of those volumetric avatars using articulated voxel primitives. However, still training takes a few days, and improving the training efficiency is another big problem. Also, for game characters, we can easily change clothing and props. Enabling such application for photorealistic avatar would be another interesting problem. Now here, I want to emphasize that dynamics and temporal modeling is very important, yet less explored area in this community. So in the aforementioned avatar modeling papers, usually shapes are parameterized as a function of pose. However, this is not exactly accurate. For human, the clothing on the human actually changes based on the history of motion, right? So those history dependency and their secondary motion dynamics needs to be incorporated to better represent the dynamics. So we present some preliminary work called the alt avatar. Oh, you probably cannot see. So we present the alt avatar, which is an autoregressive neural field, which takes the history of neural field in a network to predict the temporal dependency over human dynamics. So if you're interested, please check them out as well. All right, so let's switch the gear a bit, and we can quickly talk about the 3D reconstruction using neural field for digital human applications. So there are many methods that enable 3D reconstruction from point clouds or RGB colors. So now we focus on image-based 3D reconstruction approaches from a single view or sparse view inputs. So one approach is to do the test time fine-tuning using differentiable rendering. So we can take either fitted parametric mesh model or pre-learned geometric plier as an initialization, and then you can solve appearance and geometry with respect to latent pole or neural the network weights through differentiable rendering. So this allows us to generate plausible 3D geometry just from a single image or sparse view images. Another approach that doesn't require test time fine-tuning is the pixel-aligned neural fields. So given image, you can pass through image encoder to predict the pixel-aligned code, and then combine that with a spatial encoding to predict the final neural fields. This is working in a similar way as semantic segmentation and human pose estimation, and it works as a term for generalization. And there, like many axes, recent papers have been improving the quality and like as aspect of a neural pixel-aligned neural fields. The one axis is improving fidelity. So PyFuHD takes multi-level image features to overcome the limitation of resolution in a pixel-aligned neural fields and enabling the reconstruction at 1K resolution. And this year CVPR, the team at the Google present a forum which produced normal supervision, which improves the fidelity of digital avatar from normal supervision and differentiable rendering loss. We can also improve the robustness of our pixel and neural fields. The original PyFu doesn't take human shape as PyFu doesn't take a human shape as an explicit flyer. In Pamir, for example, they jointly fit their SMPL model from the input images and then take it as a 3D feature to predict the final neural fields. This way, neural field is conditioned by the parametrics naked body model, and this allows us to get their, like plausible 3D geometry even for unseen poses. However, this process requires a 3D CNN, which is not exactly a rotation equivariant. And in this year's CVPR, Icon proposed to take surface normal from input view and SDF from the parametric body model as a feature instead. And they're pose invariant. Therefore, we can produce highly detailed geometry for extreme poses like this. So if you're curious, please check it out as well. And once we get the reconstruction, you may want to also control and change different poses. And to do so, Arch, for example, warp pixel-aligned image feature into a canonical T-pose space using a fitted body model. And then your reconstruction is happening in a T-pose, and you can trivially animate them later on. Another approach is S3, for example, predict skeleton location and spinning wave as a pixel-aligned neural fields. This also allows us to build an animatable avatar without going through this canonicalization step. So lastly, recently people combined the pixel-aligned neural field with their differentiable rendering or nav type of training. And this enables learning such a pixel-aligned 3D reconstruction human without requiring 3D ground truths. Those work include PBA, Neural Human Performer, and Double Field, which is also a CVPR paper this year. And there are a couple of open programs. First, for human, as I mentioned, resolution and fidelity matters. Now, I haven't seen the work that enable training and inference at ultra high resolution, which is, for example, 4K. And of course, compute could partially address the problem. However, I believe the algorithm itself should be also improved. And another thing I'm particularly interested is to avoid having ad hoc system for face, hands, body, and so on. And instead, we want to build a unified framework that allows to get their high fidelity avatar. And one attempt I did is we take our 3D key points as a special, generic spatial encoding. And this way, we can achieve a high generalization for face and body without requiring those parametric body or face model in a unified manner. And lastly, maybe one big aspiration is enabling virtual teleportation in real time just from a single webcam or mobile phone you have. And to do so, we want to build this volumetric avatar in real time from just RGB images feed. In 2020, I and my colleagues did a real-time version of PyFu called Monopod, where we can achieve the real-time inference of a pixel-aligned implicit function. While it's very promising, the resolution and fidelity are still limited. So I would like to see, like how this can be further improved to enable truly realistic volumetric interpretation in the future. So that's all for my talk. And in conclusion, I provide an overview of digital human application, including 3D reconstruction, generative models, and avatar building, and so on. So I hope you are now convinced that the digital human is a very interesting problem to work on with many open questions. Thanks for listening, and I'd like to take any questions you have.
Could you clarify you mentioned on some of your slides about public family?
So this is actually our CVPR paper this year called COAB code. So like we have a basically compositional body models, the same similar construction as a NASA paper, so which represent the human body as a composition of local body model. And this, so we extended to multi-identity and better generalization to unseen poses. And so if you want to solve, for example, collision and penetration in a plot space, what you need is to query the value in a canonical space to resolve the penetration. This is particularly difficult for LBS type of representation, or it's a little more computationally involved. Whereas if it's a compositional model, you can simply compute the inverse transform by getting the inverse of a joint transformation, and then you can query a local coordinate space for each body parts. And then you can find if there's any penetration happening, so you have an overlap of the value, like two, like a local, like occupancy field or SDF function give you the collision, right? So what you need is you want to resolve this penetration, basically taking it as an objective function, and this can be resolved very quickly as a deforming as a gradient pass through from this shape space to the pose parameters and so on.
We have a question from our remote speakers. For volumetric teleportation, can we use two cameras, one in the front, one in the back, and somehow combine them? Can we integrate multi-camera systems into this problem?
Thanks for the question. So this is definitely possible, and there's already a couple of papers from Japan University Yevin Li's group, for example. And so if you're curious about that, this is definitely possible, and it's already published in a CVPR paper last year, for example. So please check it out.
I think the only paper that you mentioned, simplicity, that's the only one that separates the body from the clothing. So because most of the examples that we showed, this basically combined version of the body and clothing together.
Radar.
What is better model, clothing separately or put it as information of the body?
So it totally depends on application. So if your focus is on analyzing clothing itself, having a separated model will be preferable. However, if you're focusing on animation, then after all, what you see is only the outer surface of the body. In that case, you could merge, clothing and body together and then solve the joint problem. So this is like, if you're more focused on animation, you can ultimately what you are interested is on the outer surface, right? However, if you want to use this, like a parametric body model as a foundation of analysis, of a scene interaction and so on, then you probably want to separate them together as a different model.
Thank you.
Thanks for your great talks. I'd like to ask something about the closed human. I think there are some demands on the closed human body, and I think it is hard to track the closed dynamics with physics. And the problem is there are a lot of works on the closed physics are only on the mesh and principle. So how can I approach this problem on SDF level?
So so the question is how we represent dynamics for clothing using neural field.
With physics.
With physics. So it probably depends on what you mean by physics. So if you want to incorporate explicit notion physics like a material model and time integration, then you have to incorporate explicit material model and then solve a time integration. Another direction is you can take a bit neural approach, and at high level, what's happening in physics engine is you take a history or the previous state and velocity and acceleration so on, and then predict the next step. This can be also formed as a, in the form of neural fields. And the paper I mentioned, this old avatar paper, for example, takes the history of neural fields and then predict the next shape. So this is, in a sense, solving the physics implicitly. For closing, I would say the deformation mode by the dynamics is much more complex, and it might require like more trick to stably solve the problem. But I think this is a promising direction.
All right, thanks a lot, Shinsuke. We are running a little bit behind time, so let's try to catch up on that. So just to again kind of situate ourselves about where we are in this tutorial journey today. Shinsuke just talked about applications of neural fields in human reconstruction, pose estimation, and so on. And we're going to be switching gears a little bit. We're going to look at the applications of neural fields in robotics. And I'm going to talk a little bit about why this is an important area and why people are so excited about applications in robotics. And I'm going to be a bit brave here by trying to present through Zoom's screen share. Hopefully that works. Let's see. All right, so far so good. Okay, so maybe in the next 15 minutes or so, I'm going to talk a little bit about the application of neural fields in robotics. I know that this tutorial is primarily about the application of neural fields in computer vision, but there's a very good reason why I think it's really important for us to look at the robotics community and kind of think about what are the problems, what are the shared problems between these two communities. So, we've talked quite a bit about, neural fields in computer vision, applications in 3D reconstruction, in appearance modeling, as well as, applications in spatiotemporal appearance capture and so on and so forth. There are some features of neural fields that underlie all of these different applications that also make it exciting for robotics applications. So let's kind of think about what are some of these features that make it useful. So the first is that a common property of many of the neural fields that we've seen is that they're somehow grounded to 3D in some way, right? So they either focus on 3D reconstruction, or there is an underlying 3D feature representation that kind of helps with the reconstruction technique. Some methods, for instance, HyperNerve, they focus on capturing dynamics over a temporal dimension, right? So this is also something that neural fields have been applied, in order to capture the temporal dimension as well. Neural fields, of course, one of the interesting things about neural fields, especially neural radiance fields, is their ability to capture fine scale detail. And this is also something that we've seen in previous presentations. And finally, there's a bunch of work that looks into how to make neural fields interactive or perhaps even real time, both in terms of the training as well as in terms of the inference, right? And this is something that are useful. Now, the interesting bit here is that if we kind of replace neural fields in computer vision with robotics and kind of replace the kind of applications that we think about when we think about robotics, all of these features of neural fields are equally important to robotics applications as well. So we want to be able to operate in 3D. We want our robots to kind of move around in the 3D environment, interact with the 3D environment across space and time, capture fine scale detail potentially for manipulation tasks, as well as being interactive and real time so that the robot can operate at real time states. So these are some of the reasons why I think we should really think about neural fields in robotics as well. So the rest of the remaining 11 minutes or so, I'm going to focus on neural fields in robotics, broadly classified into two categories. The first category is going to focus on perception for robotics and kind of look at some of the work that's been done on using neural fields for perception in robotics. I'll then indicate a little bit about how neural fields have been used both in planning as well as in control. So there's a little bit of work that's been done here as well. The perception box is bigger here because there is obviously more work that's been done relative to planning and control as far as using neural fields in robotics is concerned. A couple of caveats, as James mentioned earlier, this review is not meant to be exhaustive. This presentation is not meant to be exhaustive. But what we hope to provide is a kind of a framework for thinking about neural fields in robotics. So this perception, planning, and control, I think that's a pretty good framework to kind of think about how neural fields are applied. Of course, we'd love to make it more comprehensive, so just to kind of plug in the community effort here again. Some of you mentioned that the QR code that we posted earlier did not work. We've just updated it, and hopefully this should work. And this is a link to join our Slack channel, our Slack community, where we have lots of interesting things planned, so that those of us working in neural fields, we can kind of be in touch with each other. I'd also like to point out that this is a very brief presentation. There's a really great set of presentations and workshops, for example, at ICRA, where the focus of this particular ICRA workshop was specifically on implicit representations in robotics and for motion planning. So I'd highly encourage you to take a look at their website. I believe they also have a follow-up workshop planned for RSS next week. I'd also encourage you to look at lots of community effort out there, GitHub repositories that try to compile a list of papers that apply neural fields to robotics applications. All right, so with that, I'm going to dive into and give you a kind of a whirlwind tour of how neural fields have been used in perception for robotics. So let's start with that. So one of the main goals of perception in robotics is for us to know where the robot is, or in other words, to localize the pose of the robot. And typically we assume that the robot has some kind of a sensor, a camera that is kind of looking at the environment. And we'd like to use this camera to figure out where the robot is relative to everything else in the world. So localization pose estimation is one of the first problems that people looked into when they started applying neural fields in perception. So, just to kind of recap what we see in NERF. So in NERF, we have some kind of the input, the XYZ coordinates, and the viewing direction that is passed to a neural network, the neural field, which then gives us the value of the density field, as well as the color associated with that particular point in the density field, right? And in order to figure out what the color of a particular pixel is, we do ray marching. So we kind of aggregate the color and the density across the ray and figure out what the color of that particular pixel should be in the image. So the first thing that you could try, and this is something that was tried, for example, in iNerf, is to see if we can jointly optimize both the network weights, the neural field that models the underlying radiance field, but also to figure out what the camera poses. So as James and Vincent talked about earlier, iNerves can be quite effective at you can use iNerves to figure out the camera poses. So let's try to optimize the camera coordinates, the position, as well as the orientation. So that's the first thing that we could potentially try. Now there's a bit of duality here between 6 degree of freedom pose estimation and localization. When we try to build a neural radiance field for a particular scene or a particular object, there is an underlying coordinate frame of reference. And when we try to estimate the pose of the camera with respect to this radiance field, we are estimating the pose of the camera in this coordinate frame of the scene that we've started off with. Now that if you treat the scene or the object as the object of interest, we could also think of this as 6D pose estimation of the object, assuming that the camera is static. So from the perspective of the robot, the egocentric perspective of the robot, the robot is static and everything else around it is moving. So this is kind of one way to think about 6 degree of freedom pose estimation versus localization. So what iNerf does is uses this idea of can we jointly optimize for the camera pose as well. And of course, this is certainly something that's possible as was demonstrated in their paper. iNerf starts with some kind of initialization, which is somewhat close to where the camera is, and then tries to optimize for the camera parameters as well. And by doing this optimization, you can figure out the precise coordinates of the camera. And the fact that we have to start with a good initialization is not a big issue here, because in robotics applications, the camera tends to kind of move continuously, and therefore we do have some kind of continuity that we can take into account. But there's a bit of a problem, by naively trying to optimize the camera pose. And the problem is that we know that many of these neural radiance fields methods are quite slow. So how do we, make sure that we can run this at interactive frame rates on mobile robots and so on? So that's one of the problems. So their solution to this problem is to sample a sparse number of rays. So in this case, n could be in the order of about 1024 rays, right? So instead of trying to evaluate the ray marching at every single pixel of the image, you subsample the image into a sparse set of rays, and then you do the pose estimation only for those particular rays. And this, of course, helps them operate in real time. So the pipeline that they use, which is shown on the top here, they have a scene for which we assume that we already have a radiance field that has been constructed, a neural radiance field that's been constructed. And by sampling only a sparse set of pixels and trying to optimize the camera pose, we can actually achieve camera pose estimation. And consequently, this can be used in mobile robotics localization. So here's one more example of iNerve being used for 6-degree of freedom object pose estimation. So here the camera is static, but the object for which we have the neural radiance field is kind of moving. So we use this method to figure out what the exact pose of that object is. And as I mentioned, there's a kind of duality between 6-degree of freedom object pose estimation and camera localization. Okay, so that's just one example of the many works that kind of try to optimize for the camera pose. A couple of other examples include bundle adjusting radiance fields that James and Vincent talked about earlier. And the idea here is, you want to use a coarse-to-fine optimization strategy by making use of the positional encoding, by starting off with the lower frequency components first, and then kind of trying to optimize for the higher frequency components. And this, they show results at better camera poses. And more recently, there was also these Gaussian activated radiance fields. And the idea here again is not to use a coarse-to-fine optimization strategy, but to kind of to use Gaussian activation kernels within the neural network, and they demonstrate that this can also be used for better pose estimation. Okay, so we're still in perception, and perception for robotics wouldn't be complete if we did not talk about SLAM, simultaneous localization and mapping. And of course, there's been a lot of work that's been done in the last year or two on using neural radiance fields in particular for reconstruction and SLAM. One example is IMAP, and the idea here is to build in real time or in interactive frame rate to build a 3D reconstruction of the scene, which is a neural radiance field. And this is something that we can use for robotics applications as well. In the interest of time, I'm not going to go into the details, but the problem with doing SLAM using neural fields is very similar to camera pose estimation. We want to be able to do the inference at interactive frame rates and real-time frame rates. So IMAP has a really nice optimization strategy where the tracking is separated from the mapping process, and they run at different frame rates essentially. So therefore, and there's a bunch of other tricks that they employ in order to make sure that this whole process can run interactively. Okay. Another paper that is going to be at CVPR this week is NiceSlam. And the idea here is they want to be able to do reconstruction, but also capture fine scale detail. And what they do for this is to kind of divide the capture space into lots of subvolumes where each of these subvolumes has a separate neural network that kind of is interested in reconstructing that part. And this is also something that you can check it out at CVPR this week. Okay, so in robotics, we are not only interested in figuring out where the robot is, how the scene looks like, we also want to do something interesting with the scene. And doing this requires us to have a sense of the semantics of the scene. So what are the objects that we are looking at? Is this an object that I can interact with? Is this an object that I should avoid? And so on and so forth, right? So incorporating semantics within neural fields is also a very important topic. And there's been some work done on this. Just one example of that is neural semantic fields. And the idea here is we pre-train lots of NERF models with ground truth supervision for semantic classes or semantic segmentation, 3D semantic segmentation. And then at inference time, even if we don't have the exact same scene that we are looking at, they demonstrate that this can actually be generalized to new scenes where the neural field is able to kind of figure out what the semantic class of the pixels in the image are. Again, in the interest of time, I'm not going to go into the details here, but the central idea here is to kind of use the density field that we get from neural radiance fields. And to not just use the density field for ray marching, but to use it for something more than just ray marching, right? So in this case, use it for modeling the semantics as well within the density field. Okay. So next, I'll kind of give a brief overview of some of the stuff that's been done in planning and control and how neural fields have been used for planning and control. Perhaps the earliest example of that, and this might actually precede the earliest neural field paper that we pointed out in the introduction, which is from 1998. So this particular work from Lemon in 1991 and 1992 uses neural fields for 2D path planning. Although they use neural fields in a slightly different sense to how we present it here. The neural field is essentially a 2D grid of neurons that covers the map that they want to do planning over. And what they show is that this grid of neurons can actually be used to solve the dynamic programming problem and therefore find path between 2 points within the map. Of course, neural radiance fields in particular have been demonstrated as being useful for navigation tasks. For instance, this work from Stanford shows how neural radiance fields can be used for navigation in a NERF world, or talked about these prime representations, whether neural radiance fields can actually be these prime representations. So this work is an example of doing navigation within this prime representation of neural radiance fields. So they again operate on the density field, which I think is an interesting trend that we see with many works that go beyond reconstruction, using the density field to do things beyond just reconstruction. And they kind of do an A-star search and gradient descent on this underlying field. They also have a NERF state estimator, which is kind of similar to iNERF in figuring out where the camera is relative to the rest of the environment. And then finally, they have a controller that makes use of the state estimated by the NERF state estimator to control a drone flying through the scene. All right, so hopefully that kind of gave you an overview of some of the work that's been done in trying to apply neural fields in robotics, in perception, as well as in planning and control. There is, of course, a ton of other work that's ongoing and upcoming, and I encourage you to look at our website to figure out connections between them. Now, I'd like to spend maybe a couple of minutes on future work. Most of the work that we've seen so far that applies neural fields in robotics is kind of limited to navigation applications, perhaps a little bit of dynamics, right? We don't see as much work in manipulation. So I think a really exciting direction for future work is to see how neural fields can be used for doing manipulation with robots and how they can be useful. And the second thing that I'd like to point out is the existence of data sets. We are starting to see data sets that are not just released in terms of meshes and point clouds and so on, but we are starting to see data sets that are neural fields themselves. For example, there is this data set called object folder, which is again a paper at CVPR, and I'm going to talk about this in a couple of seconds. Okay, so one of the challenges that we need to solve if we want to use neural fields in robotics is to solve the problem of equivariance. So what is equivariance? If we have let me play this video. Yeah, so let's say we have a coffee mug. How do we get the robot to sense that this coffee mug, no matter what orientation it is in, no matter where it is, that it's the same coffee mug? So in other words, how do we build neural networks that can extract features that are equivariant to the pose of the coffee mug, right? And there's certainly work that's been done, for example, neural descriptor fields that try to extract equivariant descriptors in an underlying neural field. I'd also like to point out to some work that we've done, which is also going to appear at CVPR on Thursday. And here the idea is to extend this notion of equivariance to canonicalization. And the notion of canonicalization is, as humans, when we look at chairs, we know that chairs are, we typically observe chairs in a certain orientation. And here the idea is to try to have a network learn these canonical orientations in a self-supervised way. And this is very closely related to the notion of equivariance and so on. So here you can see on the left an example of 3D point clouds, which are in arbitrary orientation. And on the right, you see the output of our method, which is able to canonicalize for the 3D orientation in a self-supervised way. I'm going to skip through the details, but very quickly, these networks use something called tensor field networks, which are neural network architectures that are equivariant to point permutation, orientation, as well as position. This work, of course, is limited to point clouds, but I think similar equivariant architectures can actually be used in the context of neural radiance fields and neural fields in general. And we saw an example of that with vector neurons, which is also an example of another work that tries to extract equivariant features. Okay, last minute, just to wrap up some of the future directions that I think are really exciting. For manipulation, contact-rich manipulation is really important in robotics. We've seen some work in the direction of modeling this contact-rich dynamics. One of the works that does this is grasping fields. And here the idea is to use two neural sign distance fields to kind of model the contact between the hand and the object. And I think works like this kind of push along the direction of modeling contact-rich interaction. And then finally, I mentioned object folder. This is work that is going to be presented at CVPR this week. And the idea here is, let's start to release data sets, not just as meshes, as point clouds, as images, but also as neural radiance fields. And that's exactly what object folder does. They created a data set with thousands, I believe it's over 1,000 different objects. And then with these objects, you also get the underlying neural radiance fields for both the appearance properties, but also for the audio and the tactile properties. And then finally, I taught a course at Brown this semester. And the idea here was to see if students could appreciate the need for neural fields in robotics. And one of the final course projects that some of my students did kind of flipped the table around a little bit. And here the question is, instead of trying to see how neural fields can be useful for robotics, can we think about how robotics can be useful for neural fields? And I'm going to play this video that kind of demonstrates what they tried to do. So their goal was to build a neural radiance field of the object that you see on the floor. But they wanted to do this using the spot robot. So the idea here is you find the optimal camera poses that gives the best possible reconstruction for the underlying object and scene that you're interested in. So they kind of built on top of instant NGP to realize this method. All right, so with that, I'd like to conclude this particular presentation, but I'd like to point out that we do have a great set of invited speakers who are going to talk about the application of neural fields beyond computer vision in science and engineering and content creation and so on. So I'd highly encourage you to come to these invited speakers' talks. And with that, I'm happy to take maybe one very quick question before we move on to the final part of the applications section.
I have features for the post estimation and either like that. As I know, the structural motion connect method can estimate the correct codes using the stuff. And what is it? The optimization base for the post estimation is always good compared to the structural motion based method. Is it right? Or if not, I want to know when it is effective or when it is effective.
So if I understand your question correctly, you're asking if some of these methods are as good as structure for motion, right? Yeah. So obviously, these methods are probably not going to be as good as structure for motion. Depends on what scene you're looking at. It depends on a few different factors. But in general, methods like iNerf and generally this notion of optimizing for the camera parameters is probably not going to be as good as structure for motion. But of course, there's follow-up work, for instance, bundle adjusting radiance fields and Gaussian activated radiance fields that kind of are kind of competing with structure for motion based methods. So I think the approaches are very different though. So structure for motion uses key points, whereas here we are kind of using all of the image pixels that we have available. So I think there's a few differences. But for the moment, I think structure for motion is still more widely used. All right, so in the interest of time, I think we should move on to the next section. We are running a little bit behind. We are probably not going to have time for a coffee break. We should? Okay, after the compression section. Okay, cool. All right, so we're going to hand it over to Towaki for a short overview of compression in neural fields, compression as an application, and then we'll probably take a very quick break right after that.
Yeah, thanks, Srinath. I'm going to give a super compressed version of the compression talk. We're going to compress the compression. I think the most difficult part of this will be switching over the Zoom. All right, so we basically have no time, so I'll make this super quick. But basically, compression is another application of neural fields. Basically, Shinsuke mentioned some of this kind of stuff, but volumetric teleportation and volumetric media is definitely the future of multimedia. There's projects like Project Starline and also older projects like Holoportation, where the goal is to basically have 3D content shipped to people. Beyond these existing projects, there's also a lot of really cool future applications with this kind of multimedia, where you see things like Travis Scott giving concerts in Fortnite and Lil Nas X giving concerts inside Roblox, and these virtual environments have a bunch of these concerts that have basically would benefit from like some sort of 3D volumetric compression and stuff like that. And as graphics workloads are also becoming increasingly distributed, which basically means that the big bottleneck of these graphics workloads is moving data around. And graphics workloads are also increasingly on the edge, which basically means that you need to also transfer data from these data centers to thin clients, like for example cars and phones and stuff like that. There are actually a few standards that already exist for volumetric media. Most of them come in the form of point cloud compression, which is actually another name for voxel compression. But if you look at the existing standards, they basically rely on these planar projections of depth and color onto these cubes. And these kind of standards have limited topology of the data you can represent. And it has no really notion of view dependence or anything like that. And it's not really discrete. But the good thing is that these things are pretty compressed, and the standards are standards because they work decently well. So the question we have kind of is, can compressed neural fields empower future multimedia? And we kind of think that these neural radiance fields and these view parameterizations can offer a much more elegant solution to multimedia in the future. So before we get into too much of that, I'm going to quickly ask maybe what is compression. Compression could mean two different things. Oftentimes we either mean parameter efficiency or information entropy. A lot of the stuff that we already talked about in the context of compression actually is all about parameter efficiency, which is basically you want to maximize quality, but not make your model too big. Another axis of that is information entropy, where you want to minimize the entropy of your representation and maximize the quality with respect to the entropy coded file. And yeah, this is some of the work that was already discussed in terms of parameter efficiency, so I'm not going to talk about it. But there's a bunch of works that basically try to do neural field compression more in the context of information entropy, where basically a lot of these work basically try to reparameterize neural field compression as neural network compression. And you can kind of see some cool results here, where it's JPEG is a very discrete kind of compression algorithm where you're compressing these image patches. But something like Coin, which basically is neural fields, even in the low bitrate regimes, you can kind of see that the usual artifacts of JPEG doesn't really show up that much in these neural field representations. And these kind of formats for neural fields actually seems to outperform standards like JPEG in a low bitrate regime, but not so much in the higher bitrate regimes. There's a bunch of other papers that show very similar results. They all show better performance, usually in a low bitrate regime. And they've been applied to things like scalar volume fields and also things like radiance fields. And there's also some recent, more interesting works that also try to do this kind of like entropy coding, entropy minimization type stuff for not just regular like global neural networks, but also for hybrid representations. So in this case, they're trying to fit like this like volumetric point cloud. But basically what they do is that they fit it with a neural field that also is parameterized by a hybrid representation of like a sparse grid, basically. And what they do here is that they basically use like a wavelet, 3D wavelet based transform coding to try to entropy code this like representation. And they also find that this works pretty well in comparison to the existing standards like RAT, which is basically based on the standard wavelet compression. So that's like a super quick overview of all the compression works that kind of exist in the world. And here are some open research questions that I think are interesting. What we see with most of these works is pretty much that in a low bitrate regime, which basically the small size, low quality regime, we see that these neural fields outperform existing codecs, but not so much in the high bitrate, high quality regime. So I think it's a very big open question of how we can, make these neural fields perform well in a super high quality zone where we want to, not have a lot of loss, but still have a compressed representation. Right now, most neural fields are extremely lossy. The other research question is, we talked about this like idea of like parameter efficiency and information entropy, but there's not really very many works that try to optimize for both. And I think this is a really important research direction where we want to be, looking at representations that are parameter efficient, but then think about ways of, compressing that, not just like compressing like regular like global neural networks and stuff like that. And another one that was alluded to in a question that somebody asked was basically how do we compress temporal volumetric videos? I think this is a really important problem and a very much unsolved one and also like a not very focused research question. And I think this is there's a lot of insights you can take from like volumetric video compression and also from things like video compression and like traditional multimedia that we ought to use here. Yeah, that was a super fast overview, and I'm happy to take any questions, or you can just go to break. Thank you. All right, I think we are ready now.
Does it work? A test?
Yes, awesome.
Oh, great. Thanks for fixing it up. Yeah, I'm going to get started. Right, so today I'm going to try to bring a connection between computer vision and scientific computing, especially we're going to solve for partial differential equations. It's going to be a 25 minutes talk. The first 10 minutes, I'm going to introduce the problem, what is partial differential equation, and what is physics-informed neural network, which is an analog of neural representations in scientific computing domains. The next 10 minutes, I'm going to introduce operator learning or operator representations. So one step further compared to neural representations. And in the last, if we have time, we can cover some examples and some extension beyond that. Okay, so what we're caring about, we want to solve for partial differential equations. There are all kinds of problems in science and engineering, from fluid mechanics, solid mechanics, electron mechanics, all kinds of problems. They're governed by physical equations, what we call partial differential equations, and we solve them using deep learning methods. Consider this very simple equation, the second order heat equations. So imagine I have a heat pan, and then I have a heat in the center. The heat will dissipate, diffuse into the environment, and I can ask the question how long my pan is going to cool down. In the computer vision language, we're going to represent a video. This video is a heat map of these objects. We're going to measure how long does the heat is going to diffuse into the environment. This equation is governed by some equations. In this case, it is right that the time derivative of U, which is the heat map, equals the Laplacian of u, which is second order derivative of the spatial dimensions. If you know the math language, that's great. If you don't familiar about that, it's just some constraint. We know that such a video, such a heat map, it satisfies some physical constraint. It turned out to be a physical problem. For example, we know in the initial state at time 0, we can ask what is going to happen at time 1, how long it's going to diffuse into 0. We're going to represent such a heat map or represent a video using neural networks. There are all kinds of other problems. For example, we have the second order elliptic equations. In this case, we don't have time. But we have a material properties. So imagine I have a pen, but they made up 2 different type of material, the blue parts and the purple parts. They may have different heat conductivity, and I can ask how long, or how the heat is going to diffuse in this alloy, how it's going to diffuse across different type of materials. And in this case, my given is a material property, is the input map A, and I want to still solve for the velocity or pressure or heat map solution U in this case. So in general, partial differential equations is we have a system. We have some known information, for example, the time 0 initial conditions, or we know the physical properties, and we want to solve for some variable like the heat map, velocity, or some physical property of the system. Traditionally, when we solve for partial differential equations, we're going to use some numerical solver. As unfortunately, most equations are too hard. We cannot write out the analytical solutions. So we have to discretize the domain, discretize into a grid, like a 10 by 10 grid or 100 by 100 grid, and so we solve the problem on a grid. When we have a grid, everything will be like relatively easier. It will reduce to a linear system. Basically, it's write out that AU equals F, where A is all the physical constraint, all the physical property we have. U is the 10 by 10 or 100 by 100 solution matrix we have, and F is the right-hand size. Usually, when we solve this kind of problem, it will reduce to a finite difference system, a linear system, and we solve it using solved by like LU decomposition, Cholesky decomposition, solve it as a linear system. The good part is it's kind of easy. For each point, each grid in the middle, we can approximate the derivative using its neighbor points. The most common method is the finite difference method, where we approximate each node, the right nodes, using all its neighbors. It can write out as this, but it's very similar to convolutional network. You can approximate the derivative at each point and write out this system, AU equals F, and solve it as a linear system. But the bad part is this approximation is certainly depend on the resolutions. If my grid is too coarse, it's going to be less accurate. If my grid is very fine, if it is 1,000 by 1,000 or million by million grid, it's very expensive. So it's a trade-off between the accuracy and the computation. So this is when deep learning methods called physics-informed neural network emerge. Basically, it's saying maybe we don't need to represent the solution using a matrix or using a grid. We can use continuous representation. It is exactly the neural fields idea. Indeed, this line of work, physics-informed neural network or deep Reis method, deep Garlinkin methods, they come out at 2017. I believe it's 1 or 2 years earlier than it happens in computer visions. The idea is very simple. We just represent this heat map or this video or this what we call function as a neural network. We know that neural networks, they are universal approximators, so we can always write it as a neural network. And the good part is we can compute the derivative, like the time derivative, spatial derivative, using chain rule, basis backpropagations. So we can write out this constraint and see if my solution satisfies the constraint. And then we can use it as an objective of my gradient descent. I can optimize my neural network, make sure it satisfies this constraint. So then we can solve this problem using gradient descent methods. It's basically the idea of pins. We're going to use neural fields, neural representation to represent the solution functions, and we optimize to make sure it satisfies these constraints. Okay. This is a framework or the flow map. It's very simple. Basically, we know the constraint which is given to us, and we initialize some neural network, U, which is represent the target functions. And for each iterations, we'll sample boundary points. They are the coordinates x and t, and we compute the derivative. We evaluate the function u at x and t and its derivative, and we plug in the equation, see if it satisfies the constraint, and we minimize the loss regarding these constraints. Right. So this physics-informed neural network is very flexible. Its biggest advantage is it's very simple and flexible compared to traditional methods, finite difference, finite elements. You need really apply math degree to write a solver. But the physics-informed neural network, they're very simple. You just need to call PyTorch TensorFlow library, and you can solve equations. Extremely simple. Usually, we don't need to worry about stability conditions. Some numerical analysis tricky parts. It's quite simple and straightforward. And it can be applied for complicated geometries, just like neural fields. We can represent, because neural networks are extremely flexible, we can represent high-dimensional complicated geometries, and we can do inverse problem, etc., etc. The challenge or the problem is usually the optimization is kind of tricky, because we are solving a constraint optimization problem. We don't have data, but we only have constraint, and we want to find out the solution by using gradient descent. It's very easy to stack on critical points, local minima, etc. And usually they're less accurate compared to existing solver. Existing solver, finite element, finite difference, we solve a linear system exactly, but now we are using gradient descent to approximate or trying to use optimization to solve it. There are usually less guarantee of these optimizations. Usually it's not that convex or it's not even smooth. Right, so if we want to compare neural fields or physics-informed neural networks, in the neural fields, we're trying to fit some computer vision objects. It can be a scene, an image, or videos. In pins, we're fitting functions. So basically, they're the same thing. A scene or image or video, they're all some function defined on different domains. So the target is the same. The difference is that in neural fields, usually we have the data, we have some observation, and we are fitting these observations. But in pins, most of the time we don't have observations. We may have some observation on the boundary case. If I have a pen, I know I can put a sensor at some points, but usually we don't have too much observations. We only know the constraint, we know the physical rule. So in general, it's a little bit harder than just fitting data sets. And to my understanding, the neural fields, the biggest concern or biggest target is representation, how to represent complicated objects using a small or simple network. The pins is more about solving a problem. We don't know the solutions, and we want to find out the solutions by optimization methods. Nevertheless, the architecture of this neural network can be quite similar. The input are coordinates and maybe codes or other things. Output are some physical variables or RGB values. Similarly, in pins, input are x, y, z, t is the coordinates in space and time. Outputs are velocity, pressure, vorticity. There are some physical value. So the objects are kind of similar. We have a network with similar input and outputs, but the problem setting is slightly different. In the pin settings, we're trying to solve an optimization problem, trying to find out solutions. So far it's clear. Okay, so the second part, I'm going to introduce operator learnings or operator representations, trying to go one step further than just pins methods. So most of the problem in partial differential equations, it can be viewed as an input-output map. It's not just the function that input coordinates, output the heat map or velocity fields at these coordinates, but we can create a data set of many images, many scenes, they have different pairs of input and outputs. For example, the heat equations, I may have different input image, different time zero, and I can try to estimate what is happen later in the video, later in the time one. So this is a forecast problem, like weather forecast, or I may have a different type of material, different type of pens with different structures, and I can predict what happened for different kind of structures. These settings is more like the traditional supervised learning settings, where we first gather data sets, like ImageNet settings. We can gather thousands or millions of image pairs. It's just my input and output are both functions, or say my input and outputs are both images, both fields, both things. I guess in the traditional image classification, output is usually simpler as a label. But now, we still want to output the functions, and we want to compute the physical laws on the functions. So we need to make sure we have a continuous representation of input and outputs, such as we can compute the physical properties of these continuous objects. So the operator learning is similar as the supervised learning, like image classification problem. We have a governing equations, we have a physical system, and we have multiple pairs of training instance, big data sets, and we can directly learn the mapping. In this case, we're not solving a problem, we're now trying to use optimization to find out solutions, but rather it's a generalization problem. We have a data set, we have a training point, I want to generalize what happened if we change the input a little bit. Right, so if we try to visualize it, on the left is a neural fields or physically informed neural networks. We have a domain, which can be a square or complicated physical objects. Input is X and output is UX, the solution UX. On the other hand, the operator representation or operator learning is we have a map between the input function space and the output function space. And given a new inputs, we want to ask what is the output now. Right? So it's more like an interpolation between input and output function space. Usually, like data-driven methods, like learning-based methods, is a lot easier compared to solving methods. And so on the left, no matter it is a numerical solver like finite element, finite difference, or pin-based methods, we need to find out the solutions. We don't know the knowledge. On the other hand, if we have a data set, we can like interpolate and extrapolate given these data sets. We have a distribution and then directly guess the solutions. So we turn the optimization problem to a like generalization problem. It suddenly becomes a lot easier. Especially regarding to the architecture search, architecture design. When we talk about operator learning, it's input and output are image, so it's corresponding to the UNets or fully convolutional neural network, or even ResNets. All these networks, they are very good for computer vision or like segmentations, but for physical problem, because we are caring about the physical properties and mathematical properties, we need to design the network considering its underlying physical mathematical properties. If we directly use the discretized vectors or like discretized grids, the network may only work for these specific grids. On the other hand, we want to have a continuous representations, kind of like neural fields representations, such as we can use these methods to evaluate for different grids, like for adaptive meshes, and we can evaluate off-grids computed derivative accurately. This is the starting point of neural operators, operator learnings. Just a little bit taste a little bit of visualization here. If we use a convolutional neural network, most of the time the filters have this kind of they're local filters. They're good to capture patterns in real-world image and computer visions. On the other hand, if we design a neural network using Fourier features, like Fourier basis, they will have more continuous representations. So if my function is smooth, then it's better to use Fourier representations. So later we're going to introduce the Fourier neural operators, where we're going to use the Fourier basis that support the continuous evaluations. Okay, so what exactly is the architecture of neural operators? first, we know the simple architecture of neural network. The basic idea is we compose linear functions and nonlinear functions. Simple linear is matrix rapidly multiplication, the green block, and the simple nonlinearity, which is ReLU or hyperbolic tangents or cosine functions. If we combine these simple linear functions and a simple nonlinear activation function, many layers, suddenly it has the representation ability to represent highly nonlinear, non-smooth functions. We compose simple structure, have a deep network that can represent highly nonlinear, complicated functions. We generate this idea to operator learnings. So now my input and output, there are fields, or there is some continuous image, continuous things. And I develop operators that represent the transformation from the input and the outputs. Still, the green block is the linear integral operators, and the red block is the nonlinear activation operators. Each parts are simple, but when we compose it together, many layers, it can represent complicated nonlinear solution operators. Here, the green block usually is write out as integrations. Here, it is integration with some kernel kappa, maybe add with a bias term W and B. But the point is, each object is simple, but if we compose simple components, many layers, it can increase its representation ability. And we generalize the discrete linear transform to a continuous integration transform, such as we can evaluate continuously at each point. Just like the neural network universal approximation bounds, we can also develop a approximation bound for operators. Basically, for any continuous operators, there exists a two-layer neural operator that can approximate it. For specific cases like fluid mechanics, like Navier-Stokes equations, we can also estimate the number of parameters that we need to use to represent. So there's a bound claiming it's universal approximators. There are many lines of work, like many specific design of neural operators. The early work is usually we're going to use graph methods to discredit the domain. Graph is very flexible objects. When we have any domain or thing, we can always discretize into a graph. If we want to evaluate any point on the domain, we can always add a new nodes of the graph, such as we can get continuous representations. Our more recent line of work is Fourier neural operators. We're going to represent the fields, represent the things by Fourier basis, which is connected to the siren, the sinusoidal representations. When you have a more global or structured representation, usually you get a better accuracy. The Fourier neural operators is a special case of operators. We're going to restrict the integral operators to a convolution operators. Both of them are linear, but the convolution operator is easier to implement because we have the Fourier transform. Basically, given convolution operators, we can use the convolution theorem. So instead of doing pixel-wise convolution or global convolution, we can first do a fast Fourier transform going to the Fourier space, and then just do a linear transform, which is corresponding to the convolution on the spatial domain. This is done by manipulating the Fourier basis. All right, so this is basically the convolution theorem. Previously, we have these integrations, but now it can be done using the Fourier transform. All right, so previously we have this kernel kappa, and now we do a Fourier transform of the input function and the kappa. The Fourier basis becomes the R, which is the weight applied on the Fourier basis. The implementation is extremely simple. We just first do a Fourier transform, and then a linear transform, and then inverse Fourier transform. This operation, according to the convolution theorem, it becomes a global convolutions. Come to convolution neural network, usually we have a local filter like 3x3 or 7x7 filters. Fourier neural network, we're going to have global convolutions, which usually are better in the partial differential equations. Because in partial differential equations, we have the green functions, where the solution function is indeed written out as a convolution of a fundamental solutions. We also did some architecture design. For example, we add a bias term, W term, to make sure it can trailer to non-periodic cases. This W term left is also acting as a bias term. Right, so this is the architecture of operator learnings. As to wrap up, we have input is an image or a scene, output is another image or a scene. We use Fourier coefficient to represent it, such as we can do a continuous evaluations. For any point off grid, we can always evaluate this coefficient by evaluate by sine x or sine y, like sine nx, sine ny. It can be evaluated at any point, any x and y, because we know the basis. This basis can be evaluated at any point. This method can be used to do a lot of scientific computing problem. For example, the weather forecast. In this case, we have a field, which is the weather of the globe. We have the field at every 6 hours. So given the velocity, given the temperature, given the wind at different heights, at this time, we can forecast what happened in 6 hours. We train this by using Fourier neural operators. Compared to the traditional methods like convolutional neural network, which usually tend to blend things up, you will lose the detail immediately using convolutional neural network. But if you use neural operator settings, which is continuous representation, you will preserve more details of the weathers. You can predict the weather, forecast the weather up to 100 hours ahead. This is a video where we can predict the hurricanes. This is weather of the fields. It's a collaboration between the NVIDIA and Caltech. Here, the red line is ground truth, and the purple is the prediction of the neural network. As you can see, it's quite aligned. This hurricane is quite aligned with the ground truth. You can use these methods to accurately predict the weather. And most importantly, using deep learning methods is 1,000 or 10,000 times faster than traditional traditional ensembling methods, because evaluating in a neural network is extremely fast. Similarly, it can be used to evaluate the carbon dioxide injections. So the background is there too much CO2 in the air, in the atmosphere, so the plants can inject atmosphere, restore carbon dioxide under the ground. In this case, we have a plant, and we inject the carbon dioxide under the ground. We want to measure how it diffuses in the reservoir. I want to make sure the simulation is accurate enough, such as the carbon dioxide will not escape back into the atmosphere. Again, this is a collaboration with Stanford and Purdue University. Using Fourier neural operators, it can be used to forecast this simulation 30 years ahead. It's very accurate. It's more accurate compared to convolutional network. Right, so I guess we don't have time for the extensions, but just a little bit idea here. Similar to the physics-informed neural network, the neural operators can be used to do the optimization to be solved for the equations. Because we have the continuous evaluations, we have the Fourier representations, we can try to estimate the gradient and use it as a loss. So even if we don't have data sets, we can do the physics-informed learning. Given a representation, we can compute the physics laws and optimize with respect to physics laws. Usually this converges a lot faster compared to physics-informed neural network. But in this case, it still converges not as fast as numerical solver. Another part is just like neural fields, this operator learning is continuous representation, can be used to solve equation on more complicated solution, like complicated domain physics or more 3D or detailed physical objects. For example, we can use it to solve for pipes or air fluids. And we can use it to deform the mesh, to use adaptive mesh methods. Yeah, thank you. So that's the end of the talk. Maybe we should go to the questions now.
Right. Thank you very much, Zongyi, for that great talk. It was really nice to see the connections between neural fields and your physics-informed neural networks, especially for problems like predicting the weather and so on. So we have time for a couple of questions. I think we have one question over here. And Zongyi, let us know if you, I probably have to repeat the question, or let us know if you can't hear it.
Thanks for a wonderful talk. I have a question with this. Using the neural operators, would it be possible to unroll a physical simulation stuff to do physically based updates of the neural?
Did you get the question, Zongyi?
Sorry, could you repeat the question?
Yeah, so the question is, could you use neural operators to do physically based updates for things like physics simulation and so on?
Yeah, I think the question is yes. So by physically updates, I think what you mean is, can we use equations and update respect to the equations? So the answer is yes. If we know the physics, if we know the equations, we can compute the physics laws. So basically, we can make sure the output that satisfies the equations. So like at each iteration, we are going to predict the solution, and we're going to estimate if the output satisfies the physics. If it's not, we can correct it respect to the physics. I guess does that answer your question?
Yeah, thanks. Could I ask a follow-up question? This is for the wonderful demo of the atmosphere temporal evolution for the Earth. But that demo, do you use a large training data set, or is it purely based on the physical equations?
So the question for the Zoom audience is the example that you showed with the weather prediction. I guess you're asking for more details on how you use your neural operators to do that.
So for the physics updates, we have a dataset called REA5 dataset, composed of like 40 years of physics observations, like every 6 hours. So we use this as a standard supervised learning task. Basically, we use first, for example, like 40 years to train, and then the rest 5 years to test. Given this trained map, we can roll out. So given time t, we predict t+1 and then t+2 to predict the futures.
Thanks. Would you think it is possible to only use the physical equations to do this?
I see. So the question is, if we don't have the data sets, can we also use that? The answer is yes. So in the physics informed neural operators, if we don't have data sets, it's totally fine. We can use as a pin settings, only use the equation, no data sets. For example, we can use it to solve Navier-Stokes equations in camera flow cavities problem, but maybe not in the weather forecast, which is a little bit too complicated.
Thank you very much.
Thank you for the presentation. I have one question about the Navier-Stokes equation. It is very interesting to map the functions to some network. But the main question is that the Navier-Stokes equation itself is estimation function, so it cannot be generalized to the like turbulence, or it has too many constraints. So why it need to use solve the Navier-Stokes? Because if you need the NLP network, we can just fit the flow itself, like as just don't depend on the Navier-Stokes equations. Because we use the neural network, we can fit the flow itself, not relying on the Navier-Stokes. That is my question. Why it is needed for fitting on the Navier-Stokes method? Because we can fit the neural network to the flow itself, not relying on that. Is it possible?
So your question is, Navier-Stokes is estimation of the physics, and maybe it's not exactly as the physics.
Yes, yes, yes.
Right. So I guess this is still an unknown problem. Like there are certainly more than Navier-Stokes equations, but Navier-Stokes is a simplified model of the physics. If we cannot even even simulate Navier-Stokes equations, how could we simulate more challenging turbulence problem? I guess we're trying to simulate less turbulent problem, which does kind of satisfy the Navier-Stokes equations. But for the more challenging, higher real number turbulence, I guess it's still just too hard to do the simulation. We just do what we can do now. Does that answer your questions?
Yeah, yes, thank you.
All right, thank you, Zongyi. Let's give our speaker another round of applause.
Thank you.
And apologies again for all the technical difficulties. I wish someone would actually do neural fields for all these audio issues. All right, so I'd like to hand it over now to Vincent to introduce our next invited speaker.
Graduated from MIT with her PhD, and she's incoming faculty at Princeton, where she's going to be in the where she's going to continue to do research on computational biology and structural biology. And yeah, she's going to tell you all about how neural fields might be useful for scientific discovery and solving actual problems in biology. Thank you so much.
Yes. I don't know if I set everything up yet. It looks good. It's sharing, right? Excellent. Okay. Sorry about that. Well, thank you to the organizers for putting on this tutorial. I'm very excited to be here, very excited for the opportunity to talk about my work, which is very related to a lot of the things that have been discussed today in neural fields, but in a completely seemingly parallel application space, which is structural biology. A type of imaging microscopy called microscopy or cryo-EM. So I'll start a little about me. I recently defended my PhD from MIT working with Bonnie Berger. And I'll be starting a group at Princeton in approximately 2 weeks, so this summer, and definitely reach out if you're interested in chatting about computer vision, neural field, to computational biology and structural biology problems. Previously to MIT, I worked other research areas on physics-based simulations for understanding protein dynamics, so molecular dynamics simulations at DHL Research, both for understanding kind of the dynamics of these molecules as well as for drug discovery. Worked with the DeepMind AlphaFold team for a summer, which is very exciting since that has also transformed this particular application area of structural biology and various simulation-based approaches for protein folding. So this is the outline of the talk for today. So I'm going to start out with the motivation for this work, a brief primer on what are proteins and why you should care about them. Next, I'll give a quick introduction to cryo-EM and cryo-EM reconstruction. Then the bulk of this seminar will talk about applications of neural fields, in particular our method CryoDragon. And I'll end on some thoughts on what's next for this particular space and share a future vision for machine learning and structural biology. So I think it might be slightly covered up, but why do we care about proteins? So proteins are a fundamental class of biomolecules that carry out all central processes responsible for life. So there are large protein complexes that take care of DNA replication, producing other proteins, degradation. And so one major area of biology is to understand the function of these proteins in order to better understand fundamentally how life's processes work. And so there's obviously lots of implications for medicine and health, as well as really new exciting biotechnology and nanology applications. So this is the protein data bank molecule of the month, either last month, so not for this month, but just as an example, this is human epidermal growth factor receptor 2, so HER2, which is implicated. Mutations in this protein are implicated in various cancers. And so what's shown here is an antibody drug, trastuzumab, bound to HER2, which prevents proliferation of this receptor. So hopefully proteins are this very important class of molecules. The goal of structural biology is to understand the function of proteins via their three-dimensional shape or structure. Tenets of structural biology is that the three-dimensional shape forms the function of the protein. And so what really inspires me is that this bottom-up way of understanding, of visualizing proteins gives us this really nice bottom-up way of understanding how these molecular machines function. Proteins at its very core consists of a linear sequence of amino acids. There's 20 possible amino acids. They have a well-defined kind of chemical connectivity. And then this biomolecule self-interacts to fold into a three-dimensional structure or a three-dimensional shape. So this is the protein folding process. There's an asterisk here because this is a very complex process that, and there's lots of caveats to this. And unlike this kind of visualization shown here, proteins are inherently dynamic. So in order to do all these processes like DNA replication, it's not just a single static structure. One really interesting area of scientific discovery is to understand the dynamics and the conformations of these proteins and be able to relate that to how they work. Wait, I'm going to try to close this live transcription thing for 5 seconds. If I can't get it, then that's fine. Okay, never mind. So one last piece of background on proteins. There's different 3D representations of protein structure. And just to disambiguate two of them, we have an atomic model representation. So this is the Cartesian coordinates of all the atoms in our actual protein biomolecule, where they are in space, and then the kind of graph, the kind of chemical connectivity. And there's a full atom representation where you can see the location of all atoms. This is kind of hard to interpret because it's a little messy. And so one thing you can do is just visualize the backbone of this linear chain. And then there's various ribbon type visualizations that help with interpretations. That's in the center. Kind of what's central to what I work on are electron scattering potentials or densities. And so this representation on the right is a density volume representation of 3D structure, and it's visualized here as an isosurface. And given a sufficiently high resolution density volume, you can really easily place the nuclei of your atoms, or based on the geometric kind of constraints of these amino acids, fit in your atomic models. So structural biology is a major kind of area in biological discovery or biological research. And one major technique for visualizing or solving these structures is with cryo-electron microscopy, or cryo-EM. Cryo-EM, which has been under development over the last few decades, has really undergone transformative improvements over the last 10 years. That's referred to as the resolution revolution. And it's really opened up new areas of structural biology. So these huge protein-protein complexes, these dynamic protein complexes that have been really, really exciting to see. And this has been driven by mainly two parallel developments. The first being better hardware, so direct electron detectors, which fundamentally increase the amount of signal in the underlying images, as well as new software, new probabilistic, new gradient-based learning algorithms that are typically implemented on GPUs. So reconstruction algorithms that typically took weeks or even months on a supercomputer cluster now take hours on a single GPU workstation. There's also been significant automation and democratization of access to the actual cryo-electron microscopes. And so now with this deluge of data, I think it's really exciting time because we have a lot of new computational challenges, but opportunities for really kind of unlocking new areas of structural biology. So I'll start with a brief overview of some of the image processing steps in single particle cryo-EM. So obviously I won't go into any of the biochemistry, but you biochemically purify your protein of interest and then send it to your cryo-electron microscope. There's obviously a lot of challenges here, which I won't go into. Then once you have your pictures, you have a picture of your solution. There's various pre-processing steps of the resulting micrograph. So for example, motion correction, which is shown here on the top, and then particle picking, which is where you identify the individual molecules within your micrograph, draw bounding boxes, and extract them for 3D reconstruction. So that's the focus of my work, which is this 2D to 3D reconstruction task. We have a data set of unlabeled images, and we want to reconstruct the 3D structure of the protein of interest. So shown here is the SARS-CoV-2 spike protein, which was done in approximately a month or 2 months after the beginning of COVID-19. And then finally, given a sufficiently high resolution density map, you can fit in the atomic model. If you're interested in learning more about cryo-EM, I wanted to point out a couple of relevant reviews. I highly recommend this one by Amit Singer at Princeton and Fred Sigworth at Yale, Computational Methods for Single Particle Cryo-EM. The second one goes into single particle reconstruction in a little bit more detail. And then I'm helping out with this new review on deep generative models for volume reconstruction in cryo-EM, and I'm preparing a new review on deep learning for cryo-EM analysis. So getting more into the specific details of single particle cryo-EM image formation. In this technique, which a schematic here shown on the right, we have a purified solution of our molecule of interest that's flash frozen in a very thin layer of ice, and then imaged with our transmission electron microscope. So each cryo-EM image contains a tomographic projection, or this integral projection of a single instance of our molecule or our molecular volume along the imaging axis. And because these molecules are tumbling randomly in solution before being flash frozen, they're captured in some unknown orientation or unknown pose. And so that's given by this 3D rotation. Okay, I don't have a mouse, so I can't point to anything. This 3D rotation, which is this rotation matrix in SO3. And then the image, then there's an in-plane shift corresponding to imperfect centering of our molecule within this 2D image. The image is also convolved by the microscope's point spread function, and then we have a large amount of additive noise. So that's the forward model for single particle cryo-EM. The goal of reconstruction is to solve the inverse problem. So we have an experimentally derived data set of images, typically consisting of hundreds of thousands or millions of images, each containing a unique molecule. And then we want to reconstruct the 3D cryo-EM density, or this volume captured by these images. So there's a number of challenges associated with this task. First, the unknown pose, or this unknown orientation that I just mentioned. Cryo-EM images have very low signal to noise ratios. You have to take into account image grading filters, discretization of the measurements. And then the one that we're putting in is the heterogeneity problem. And so this is where we break the assumption that each volume, each molecule is an identical static structure. And I'll go into that in a little bit more detail, but before I do that, there is one additional piece of background information, which is the Fourier slice theorem. And this helps us relate two-dimensional projections to the 3D volume. So the Fourier slice theorem states that the Fourier transform of a 2D projection of a volume is a central slice out of the 3D Fourier transform of the volume perpendicular to the projection direction. And so if we had a data set of cryo-EM images and you knew their poses, you could take the FFT of the images and then insert these FFTs as slices into our 3D representation or our 3D Fourier space, build up our 3D representation of our molecule or our volume, take the inverse FFT and get back the real space volume. So this kind of suggests a method for reconstruction, which is this iterative process based on expectation maximization, where we give an initial kind of volume, estimate all the poses, then given all those poses, we can re-estimate the volume and repeat until convergence. So that's for the homogeneous case, where we assume everything is the same volume and just via averaging, everything is combined together. In reality, because each image contains a unique molecule and the proteins themselves, remember, are dynamic and they might be in a different conformation, we can actually try to reconstruct a distribution of their conformations. And so this is actually a major opportunity for cryo-EM and for structural biology in general, since the other dominant techniques in structural biology, which is crystallography, crystallizes or rigidifies all copies of the molecule into the same conformation. So here we have an opportunity, a scientific opportunity to study the dynamics of these protein molecules. Unfortunately, you can see how that complicates this reconstruction process. And so the standard approach for dealing with heterogeneous data includes discarding heterogeneous data, which is obviously suboptimal. And then kind of the next most standard, or the workhorse for dealing with heterogeneity, is called multi-class reconstruction, which models image formation as originating from a discrete mixture model of K independent structures, or K independent voxel arrays. So that works okay, especially if your protein of interest maybe only has 2 or a small number of relevant kind of structures, but you don't know this information a priori, and it also fails for more complex forms of heterogeneity like continuous motions. And so in practice, this becomes a very slow, laborious, and also not a very expressive model for the types of motions that you might see. So just as an example, this is a typical cryo-EM processing workflow that you'll find in the supplement of every science paper touting a new kind of structure from cryo-EM. You don't have to look at the details, but the idea is that at the top, we have 3.7 million images collected from the microscope. But through many rounds of user-driven kind of filtering and clustering with this classification or multi-class reconstruction approach, at the end, we have 2 structures, and we've thrown away over 3 million images. And so the identification analysis of the structural heterogeneity, especially kind of continuous forms, is an open problem in cryo-EM reconstruction that I was interested in at the beginning of my PhD. And one of the main research kind of questions was, can we adapt deep learning techniques that are capable of modeling complex continuous distributions to this particular task? So our method is called CryoDragon, which stands for Deep Reconstructing Generative Networks. It tackles this heterogeneous reconstruction problem where we're reconstructing a continuous distribution of structures. And so our contributions include framing heterogeneous reconstruction as unsupervised learning of a deep generative model of 3D structures trained from 2D images. We address this open problem of reconstructing continuous heterogeneity with a model that's relatively expressive and doesn't really impose too many assumptions on the types of motions that we see. And in this work, we also, that's relevant to this particular audience, we introduced a neural field representation of 3D structure that has shown, very excitingly, that has shown broad applicability in computer vision, which is these coordinate-based neural networks with a positional encoding function to featurize the input coordinates. So the CryoDragon method at a glance I've summarized into these 3 points. The first is we develop coordinate-based neural networks, now called neural fields, to directly approximate this 3D density volume. The second is an overall Fourier domain image encoder volume decoder architecture that's based on the VAE. And then finally, we do inference of this model using exact inference for unknown pose variables and variational inference for heterogeneity. So going into this neural fields, and here I think this is maybe the first audience where I won't really have to describe this in that much detail. But instead of, the main idea is that instead of representing the structure as discrete points on a 3-dimensional lattice or this voxel array-based representation shown here on the left, we instead use an MLP to directly approximate a parametric function that maps from our 3D Cartesian coordinates to the cryo-EM density at that location. So cryo-EM structures are parameterized using this neural representation instead of a voxel array. And then in order to learn kind of high resolution structures, which is what we cared about in this cryo-EM setting, we introduced a positional encoding function to featurize the input coordinates using sinusoids of varying frequency. And this you'll be very familiar with since it's very similar to the neural radiance fields architectures. So why do we choose this representation? The main reason is to model continuous heterogeneity. So in the kind of traditional approaches, multi-class reconstruction, we have k-separate voxel arrays. And so the goal of reconstruction during kind of optimization, we need to do inference of the poses as well as kind of class assignment probabilities to these k-separate classes. Whereas in CryoDragon, we simply extend the input dimension of our MLP to condition on a latent variable vector, which can be used to parameterize kind of additional degrees of freedom for our protein molecule. And again, in the multi-class refinement approach or multi-class reconstruction approach, it's ad hoc selection of K and the initialization for these K volumes, and typically K is less than 10. So we like this very expressive neural representation. We extend this continuous latent variable model, encodes this n-dimensional distribution over structures. And this is the generative model for CryoDragon. Now the task for reconstruction is how do we learn this model from data, from our single particle cryo image data, which looks like this. We can barely even see the molecule. Our overall architecture is this image encoder volume decoder architecture. So the volume decoder is this coordinate-based representation that I just described. Given an input image, the encoder kind of maps this to latent space. So we have this latent code or latent embedding representation of our image. And then remember the Fourier slice theorem. So that relates our images to the 3D as slices out of our 3D volume. And so unlike the schematic shown here, which is in real space, the model is actually specified in the Fourier domain. But if we knew the pose, or if we knew kind of the view direction of the particular image, Then we can rotate. We can explicitly model the geometric operation and rotate a coordinate lattice that's originally on the imaging plane by that rotation. Then we have these pixel coordinates, these like Cartesian coordinates for each pixel. We can broadcast our latent embedding to all of our pixel coordinates and reconstruct or decode the slice of the volume pixel by pixel. And then we have a reconstructed slice, compare that to the input image, compute the loss, and use that to update the neural network weights. And so this coordinate-based architecture really nicely enforces this geometric consistency between the different views. So given sufficient views from all these different viewing directions, we can learn a consistent three-dimensional reconstruction of our protein. That's assuming we know the poses, but we don't know the poses and what worked well for us. So there's lots of different paradigms you can use for pose estimation. I'm very curious to kind of see the parallels between this domain and other domains in computer vision and robotics. But what worked best, at least initially, is an explicit search via branch and bound global optimization procedure. So this is inspired from the traditional literature that also does this explicit pose search procedure over a discretization of our 5-dimensional space of poses. So that's a little bit on how do we train the model. So at test time, we have these 2 trained neural networks. How do we actually use that? We saying being the structural biologist or the practitioner. So we can take the encoder neural network and encode our data set of images into latent space. And we have this latent space representation of our entire data set, and we can view this data distribution. Maybe this already tells us something really interesting about our protein. Perhaps these different clusters correspond to different kind of conformations or structural states of our protein complex. We can also use the decoder neural network to generate volumes at different values of our latent variable. And so we can generate representative samples, and the kind of expert practitioner will know what to do with this. And since this is a continuous model, maybe given 2 endpoints of interest, we can do a continuous like interpolation in latent space and reconstruct the trajectory connecting those 2 end states. In practice, a lot of structural biologists are not comfortable with deep learning. And so what you can do is validate these structures using traditional tools by kind of segmenting your latent space and then taking the underlying images and doing a traditional homogeneous reconstruction. And in practice, there's a lot of junk in real data, and so it's also been particularly useful for data set filtering. So just to summarize the training regimes, given an imaging data set, 2 neural networks are jointly optimized to learn this encoding and decoding of some n-dimensional continuous latent space describing the data set's heterogeneity. So like the single C nerf optimization, this is trained per data set. And we try to learn kind of the conformations of that particular protein. The objective of our loss function seeks to maximize a lower bound on the likelihood of the data. So this is just a standard VA loss. There's 2 training regimes, the ab initio case, where we're jointly optimizing poses and our latent space, as well as our volume representation. And then there's heterogeneous reconstruction with previously estimated poses. So this is significantly faster and can work in cases where your heterogeneity, like your protein motions aren't dominant, and you can still run a homogeneous reconstruction prior to training this model to get the poses. And follow-up work explores improvements to pose estimations. So we have Cryo2, which was done in collaboration with Claire and my advisors, Joby Davis and Bonnie Berger, and Cryo5, recent collaboration with Gordon Wetstein and Axel Levy over at Stanford. So that's a little bit about how CryoDragon, how the method works. One thing that's been particularly rewarding is developing a software package for practitioners so that people can use this in real application settings. And so I'll share 2 vignettes on applying CryoDragon to discover new structures in previously published data sets. So these were structures that were missed in the original analysis of the data, as well as visualizing continuous dynamics. So in this first case, and I won't go into too many details on the biology, but what they were interested in is studying the assembly process of this particular protein complex or protein machine. The data set has 130,000 cryo-EM images containing a mixture of these different proteins in the different states. And then through the traditional approaches, the authors were able to identify 4 major classes of this particular complex, B, C, D, and E. And then within those classes, some minor assembly states. They're studying the assembly process of this particular ribosome. So we train a CryoDragon model on this particular data set, and this is kind of the latent space representation of the data set. And we can see that there are already lots of clusters. Our latent variable dimension is 10, and so it's visualized in two ways, with PCA on the left and with UMAP on the right. And then because we have this published class assignment, we can compare the latent embeddings from CryoDragon to the class labels. And you can see that the different clusters in our latent representation align with the different classes from the previously published analysis. And if we generate the structures from these assembly classes B, C, D, and E, we get the expected structures of this ribosomal complex. So just showing a couple more examples from the latent space, this cluster out here in blue is actually an impurity in the experimental sample preparation, and this came out automatically from training the CryoDragon model. And then on the bottom, I'm showing some additional samples from the purple group, showing that these minor assembly states were also correctly modeled. We were able to discover a new assembly state from this region of latent space that was kind of misclassified in the original approach. And so what kind of was interesting here was that the structure that we reconstructed looks like the class C, which is the green structures, but has this additional helix dock that was previously only associated with this other group, the purple group of structures. And so we were able to kind of orthogonally validate the presence of the structure. The second example that I wanted to show is this data set that has significant continuous heterogeneity. So in the original publication appearing in 2017 by Plashka, Lin, and Nagai, they were able to resolve the different regions of this large precatalytic spliceosome through many separate rounds, masking. It was very complicated because of the heterogeneity. There are other approaches for modeling heterogeneity. Another one is multi-body refinement, where the user draws, where the structure is assumed to be composed of a couple of rigid bodies that are user-defined. And then from this approach, they were able to see this kind of large-scale motion of one part of it. But because of the rigid body assumption, there are artifacts at the interfaces, like helices completely breaking. So maybe there are kind of analogous things like human pose estimation and things like that. So this is what we get when we train a CryoDragon model. Here, this is a kind of interpolation in latent space in the corresponding trajectory. We see the large scale motion of the top subcomplexes of this precatalytic spliceosome coming down along the PC2 axes of the latent embeddings. We see that these two pieces move in parallel. And so this is really exciting. This is on real data, being able to see these motions of these these spliceosome complexes. But we're not just limited. So how do we actually explore the full distribution? I think this is an open problem in the space. What we do and what's available in the software right now is this graph traversal algorithm where we build a KNN graph of all of our latent embeddings and just do either a random walk or a directed walk on this graph, generate structures of the visited nodes. And I think this gives a really nice way of just exploring and visualizing the learned distribution and maybe generating a plausible trajectory of how this molecule is actually behaving in our cells. And so in summary, I've described CryoDragon, which is unsupervised learning of this continuous distribution of 3D structures from 2D cryo-EM image data. We introduced this new neural representation for modeling high resolution cryo-density maps. I think what's really powerful about this approach is that this deep generative model or this kind of neural network-based formulation provides a very flexible framework for modeling heterogeneity. So we've been able to use this in practice to discover new structures, visualize continuous dynamics, and through our open source software release, it's been used, quote, in the wild to actually help in real applications, which has been super exciting. And so the last part of this talk, I wanted to end on some future outlook. So this is maybe veering away from neural fields directly, but I think is really exciting for machine learning approaches for structural biology. And so one kind of area, so CryoDragon has done kind of heterogeneous reconstruction, but there are a lot of so it's really approaches. Kind of in the today. How do you do your representation for your structure? Kind of based model. How and what I'm showing here is taking advantage of the underlying atomic model. So we have a workshop paper doing that. maybe how you do inference, maybe like instead of this autoencoder framework, you can think of other ways of optimizing this.
All right, we have a couple of questions in the chat. So the question is, for
They are multi-view in that they are capturing images of the same protein, but the protein itself might be in different locations. So there's kind of an interesting identifiability problem of like, okay, when do you say that when do you enforce that the thing is the same view of different views of the same protein or not? The specific kind of phrase slice theorem in our image formation model, I think really nicely enforces multi-view consistency if you have only a single structure, because that's just completely kind of characterized by our coordinate-based representation. But for the kind of heterogeneous case, it becomes less clear. Cool. Awesome. Oh, you have a question. Okay, sorry.
Let's get here. Has there been any work that combines the object detection for picking particles with the reconstruction sort of in an end-to-end manner as opposed to separately?
Yeah, so that is really interesting, a really great question. And I think people are definitely working in this direction. I don't think anything is done in practice at this point, but I think people are really interested in doing kind of live processing where while you're collecting the images, you can like automatically do 3D reconstruction. And I think that is just like really useful in that you can do getting distracted. Yeah, yes, so that is definitely really interesting. Yeah.
This nice presentation. My question is why would neural fields considered as a good representation of solving protein images? Because as we know, protein image is as simple as a linear equation, and there's a lot of linear solvers. And if we want to solve it in frequency domain, there's also like central slice theorem. So given neural fields is so is not as efficient as some grid-based representations.
Yeah.
Why would we consider as a good presentation? Is there any practical improvements, something in resolution or something?
Yeah, so when I started, no one thought it was a good idea, but I was convinced because I think it's really useful for modeling the dynamics specifically. So we want to be able to model kind of nonlinear dynamics and nonlinear motions of the protein, and it's not clear how you would do that. And so this implicit neural representation is what we did for modeling kind of protein conformational changes. For a single structure, I think a voxel-based representation makes a lot more sense. You can just like take the memory hit, have like a really large voxel grid and just like learn a high resolution, learn all the high resolution details. But when you want to be able to model dynamics, then it's just a research question of what representation do you use? And so this kind of coordinate-based MLP was our first, was kind of what was very exciting and worked well. But I think there's lots of other approaches and a lot of new ways of doing it that people are exploring.
Yeah. Follow-up question is, since we are using neural fields, so everything is in continuous domain.
Yeah.
We will think that will improve the resolution of the proteins we will reconstruct.
We wanted to do, we use this neural fields representation because we wanted to model continuous motions.
Yes.
So I guess that's more answering your first question. For the resolution, it's interesting. So you definitely can maybe share data better. So with this discrete voxel representation, you're assuming that they're completely independent.
Yes.
And so, yeah, exactly. I think I agree with what you're saying.
Yeah, thank you. That answers my question.
Yeah.
All right, if there are no more questions, let's thank Alan again.
So yeah, thanks everyone for staying with us throughout this whole conference. We're on to the last talk now. It is my great honor to introduce our guest speaker for this last session, Alex Evans. Alex is a veteran game developer and a superstar in the graphics community who currently works at NVIDIA as a principal research scientist. Alex started his career in games at Bullfrog and eventually Lionhead, before co-founding Media Molecule, which is a game studio known for incredibly creative titles like Little Big Planet and Dreams. Alex is an expert on content creation and alternative geometry representations like implicit surfaces and sign distance functions, and has shipped absolutely amazing content creation games, which use things like signed distance functions entirely as its primary representation. Today, he works in research on many exciting topics, including but not limited to neural fields. And I personally grew up playing many of Alex's works as a kid. So it's super exciting for me to have Alex with us today. And please give Alex a warm welcome. Thank you, everyone.
Thank you so much. Thank you, Tawaki, and thank you all the organizers for inviting me. I'm relatively new to research, as Tawaki said, and recently my first published work was Instant NGP, which has been mentioned a few times today, which was enormously rewarding for me. So I appreciate this whole community. Right, let's get started. Let's go as quick as we can. So digital sculpting, which is a subject that I'm going to talk about mostly today, already uses implicit fields. It's and actually Tawaki said at the beginning of this course that we shouldn't call them implicit fields, but I'm going to call them implicit fields, so apologies, Tawaki. But neural fields are not commonly used in their content creation context, and I want to talk about some of the reasons it isn't. A lot of what I'm going to talk about today is the non-neural fields, but I think that I want you to draw connections to everything you've seen today, effectively some of the things that Orr talked about earlier, for example, and see how neural fields perspective might breathe new light into these kind of creative processes. And there are some downsides too. So yeah, if we look at the process of digital creation, 3D sculpting, modeling as it's known, before sculpting came along, it was typically a very sort of low-level process where the artist had to spend some large amount of their brain power thinking about edge loops, vertices, polygons, faces, and those sorts of things. And basically, it was a big burden on their brain. Although they were thinking in terms of, I want to make a camera, I want to make a character, I want to make a human, they were probably thinking in terms of, where am I going to place the edge loops around the face? How will this animate? How many vertices do I have? What's my budget? And that was quite an unpleasant experience. And then there was a sort of revolution when these kind of sculpting programs came along, and these are just a few examples. There are many, in fact, ZBrush on the right, 3D Codes on the top left, but there are others. But the point is that these programs, even the ones that began as explicit representations like ZBrush, which actually uses a mesh, a highly tessellated mesh, the key point was they presented to the artist a kind of continuous lump of clay, and you no longer thought about the vertices and the triangles. And as far as I know, 3D Coat was one of the first programs which had a true volumetric representation, what we would call a signed distance field today, or perhaps a level set method. But regardless, it was again giving you that metaphor of clay sculpting. And at the bottom here, we have two other examples which take a slightly different approach. Magica CSG is a very nice program which permits kind of parametric signed distance fields. So for example, functions such as spheres, rectangles, rounded boxes, toruses, and you compose them together in a scene graph to create more complicated shapes. So I call that parametric SDF. And then Substance Modeler represents a kind of middle ground. It's a new product in beta from Adobe, which allows you to layer up a scene graph, but each element in the scene graph is itself a grid, a densely sampled grid. But none of these yet use neural fields. And so I think it's interesting to look at the reasons why. And in my background, I worked on a game called Dreams, and the thesis of Dreams is, can you create all of a game and hand it to the users? So anyone with a PlayStation can do all of the content creation for a game, and can they do everything with nothing other than these primitives, which are represented by parametric signed distance functions? So few instructions are executed on the GPU, and literally everything in the game is created from these 10 or so shapes. And one of the most beautiful things about signed distance fields, which I think is underappreciated, and we've talked about SDFs a few times today, but we've not really talked about the properties of SDFs that make them so useful creatively. And I'm going to come back to this and illustrate it in 2D later. But one of the beautiful things is that because you have what I think of as action at a distance, at any point in space, the distance field is actually affected by surfaces quite far away from it. At any given point, you know the distance, signed distance to the nearest point on the surface, which in some cases can be quite far away. And as a result of that, very simple applications of pointwise, functions such as this soft min operation here, which just takes in two scalar values a and b in a radius. You can actually get these kind of global blending effects, even though it's a function which is applied locally. And the question is, how many of these sort of parametric edits does it take to do creatively interesting things? And the answer is, or can you do creatively interesting things at all with such simple building blocks? And it turns out that yes, you can. So this is an example of someone sculpting on the PlayStation entirely using signed distance field. There are no triangles here. This is entirely an implicit function being directly visualized by ray marching. And what they're doing is subtracting away thousands and thousands of ellipses from a single sphere. And here you can see it in a debug view. And in fact, you can see that there are 21,625 operations. And the reason this is interesting is think back to Orr's talk about how we might want to compose together implicit fields. And in this example, they're parametric fields, spheres and cylinders, but they could very well be in a neural field. The only problem is that we're composing 21,000 of them to create this shape, excuse me, and never underestimate the power of artists to kind of do the same thing over and over again in very creative ways. And so this is one of the problems that we have to tackle if we're going to start building composable neural representations. So I'm going to talk more about that. And I just want to highlight that one of the reasons that these kind of parametric SDF representations are so powerful is that even with 20,000 operations, each one only has a few parameters. And so the overall storage on the wire, on the network, on the cloud, however you want to think about it, is probably only of the order of 800 kilobytes. Whereas if you run a march in cubes or you extract a mesh in some other method, from the resulting field, you'll get something like 12 million triangles, depending on the resolution that you dice at, and have many megabytes. And this delicious English breakfast here is entirely an implicit function of the sorts that we've been talking about today. Again, it's not neural, but it is a function from a position in space to a color, a roughness of the surface, and an albedo. And that's it. And there are no triangles, there's no texturing, and everything here was built from those 10 or so primitives. Okay, I'm not going to talk about that anymore, but I want to talk about the sort of creative workflows that lead to those kind of 3D models, because it's amazing to me that you can compose such simple pieces into such rich artwork. Okay, so I think that the great thing is that all of the artwork basically comes down to collage and manipulation. And to some extent, this is a recap of Orr's talk, but this is the fluffier, end of the day, everyone can relax a little bit kind of version. So I think the first part of collage, and it's literally equivalent to doing real collage with bits of paper or bits of clay or Lego, is that you generally take pieces that are pre-made and then you want to mask them, you want to crop them. And actually one of the things I think neural fields can add is the ability to semantically select things. Here you can see me very awkwardly using in instant NGP finding a bounding box. But fundamentally the masking operation, whether it's crude like this with a bounding box or whether it's fancy with some kind of semantic network that's able to bring out the gargoyle automatically. The first step of creativity is very often masking out the piece that you want. The second step is arrangement. So here I have Aphrodite, a scanned model as an SDF, and here I have Napoleon. And okay, I've got those two sign distance fields in this case, and I want to combine them together. So I mask them against each other. I maybe rotate them. As Orr said, that's a very simple operation. You're just rotating the relative position of the two fields. And because they're sign distance fields, I can even blend them. And I'll come back to this blending in a moment because I think it's a superpower of SDFs that's particularly useful in a creative context. Hi, Napoleon, nice to meet you. Okay, and of course, the other key ingredient when you're creating is repetition. So you don't want one Lego brick, you want many Lego bricks, and this is something that both Dreams and Substance Modeler are particularly strong at. So the idea of Substance Modeler is that each of these individual pieces is represented as a 3D grid. What you can imagine a 3D tensor in PyTorch of density values or distance values. But that you combine with that traditional scene graph, which allows you to repeat and clone and copy these things cheaply. So that's collage. And then the next part is, if you're arranging these pieces, how do you manipulate them so that they can fit together better? So, it's all very well if I have a blade of a windmill here, but how do I make sure that the blade is the right shape? And so really that's about deformation. We've already heard about kind of different forms of domain deformation, but it's a really powerful technique. We've seen already that the deformation fields, as in NeRFs and hyperNeRF and BANMO and other NeRF-like works, can itself be a neural field. Or it can be, parametric fields, such as this great tweet from Simon Green, where he hacked together some sort of Inception-esque, I don't know if it's Inception, but you know what I mean, movie-esque domain deformations. And equally, you can do simple twists. And these are extremely powerful. And the other thing I mentioned before was blending. Now, we've heard a little bit about the inductive biases that MLPs and neural fields bring to the table, and I think that's a very important superpower that they have. However, even a simple, dumb SDF grid has an enormously powerful shape kind of prior to it all. If I take this field of Napoleon again, and all I'm going to do is crossfade it, that is linearly blend between the field of Napoleon and the field of was it Aphrodite? I think it was. So what I'm doing here is I'm blending between the two, and you actually get this kind of really interesting shape morph effectively between the two. And I just want to illustrate a little bit more why this is happening and why these kind of naturalistic priors or biases in your model are so important, and they actually apply in the case of STFs even when you don't have an MLP in the mix. Okay, so let's look at that in. Before I go into blending, I'm just going to point out the glory of implicit representations. It's that all these operations that I just showed you, as Orr showed as well, are extremely simple. So cutting and masking is just a question of evaluating your function in a smaller domain, cropping to a box in my case. Arrangement is as simple as taking the maximum value of two SDFs or the maximum density from two NeRF light fields. Repetition is a special case of domain deformation. You simply stick a modulo operator into your argument, into X, you scale it by a factor S perhaps, and then you modulo every B units, and that allows you to repeat things. Likewise, the generalization of that is that you can have some time-varying function G, which itself could be a neural field, which allows you to then do the inception folding of space and the bending, or perhaps in a human scenario, taking from a canonical T pose into an animated pose. So domain deformation is extremely powerful, as we've already seen today. And then blending is that thing that I just showed you between the two models. It's literally just the linear blend between two fields. Okay, so let's go into a little bit more about that, because let's say we're having occupancy grids. The neural fields don't have to be sign distance fields or NeRF light fields. They can also just be simple occupancy, the probability that something is solid at a given point in space. And so I mocked this up in Photoshop to just show you how that works when you blend between two occupancy grids. So I have a 2D grid of an A and I have a 2D grid of a G. And when I change the occupancy of those two fields, you get a crossfade. It's not that interesting. But what I think is interesting is when you replace those occupancy grids with a sign distance field. So here I have the sign distance field of the same G and the sign distance field of the same A, and I'm going to crossfade between those two, again, just using a linear blend. And because the function is smooth, and because the function has this kind of spooky action at a distance in the sense that the shape of the letter actually propagates into the entire field, if I now threshold that so that you see the sign of the distance field, as I crossfade between the two, I actually get this really creatively interesting deformation between the shapes. And I just wanted to emphasize that these kind of natural priors or more image-like priors are really powerful. And things like siren networks and even ReLU networks for MLPs for neural fields take this even further. But I think it's interesting to illustrate it in such a simple setting as a 2D grid in Photoshop. Okay. Let me see, is this the video I already played? I forgot my own slides. Yes, we've seen that. Great. Okay, having sung the praises of SDFs and the iconal constraint, there is one slightly irritating thing about them, which you have to think about when you're using this composition of creative operations. So typically we only visualize the zero level set. We only see where the zero surface is, and we don't really think about what the field is doing away from the zero set, the zero level set. And there's an interesting paper from, I think it's at CVPR this year, where they actually regularize the interpolation between two fields to make sure that the iconal constraint is enforced. And the reason that's so important is that when you do almost any operation to an SDF, whether it's interpolating in the latent space, whether it's the sort of blends I just showed you, or whether it's just simple union operations and subtractions and additions, it turns out that the field you get is no longer truly a distance field. So here you can see me kind of sculpting in 2D and adding these little scribbles. Now, if you look at the iso contours of this shape, superficially they look like a distance, but actually they're not. And you have to then run a kind of a numerical relaxation to try to redistance this into an actual distance field. And if you don't do that, as you compose more and more of these operators together, you get more and more unusual behavior, more floaters, more strange things happening. So this is one of the irritating things about sign distance fields, to give a bit of balance. Okay, so how do we keep things interactive when we have an unbounded number of operations that are being mashed together by an artist. So imagine that you have a neural implicit field, whether it's an SDF or a NERF or something else, and you combine it with 50 others. Some of the papers that have shown these kind of operations coyly have 4 or 5. And as someone who's been in the games industry, I can tell you that no artist is going to put down 4 Lego diggers. They're going to want to put down 5,000 Lego diggers, and then they're going to want to make each one individually unique. And for each of those, they're probably going to want to deform it. They're going to want to reskin it. They're going to want to lift the bucket. They're going to want to change the color of the plastic. And then they're going to blend it with 300 more, and then they're going to clone that and repeat the entire thing again. And I can't emphasize enough that that will just go on forever. And so the question is, what representation can we use to represent the scene in aggregate? And actually, Vincent talked about the need to maybe parameterize networks when you're generalizing them, not by a global latent code, but by some spatially varying code. And there are some interesting works as well on trying to actually have full scene graphs represented in a neural fashion. But fundamentally, I think that simpler approaches are going to win. And here's why. If you look at, it'd be very nice to be able to store the full list of thousands of operations, but fundamentally evaluating 5,000 MLPs at each point in space is probably going to be too expensive, even for the next gen GPUs. And so the funny thing is that baking it onto a grid, that is literally just evaluating the MLP everywhere and putting it into a big 3D grid, has shown to be the dominant and winning approach in 2D graphics, right? Everyone is used to layering in Photoshop. Everyone is used to having an underlying resolution that they set high enough and that they're comfortable with the resulting band limiting of the signal. And unfortunately, that is something that it's very high for bang for buck, if you like. But maybe neural fields can offer a better way, both for images and for 3D fields. Perhaps we should be projecting this composed scene back into the latent space, or maybe just re-optimizing a new network. And I think that's a very interesting approach. And this is actually something that all touched upon. I can't remember what he called it, the primal representation, perhaps like he called it. And I think of it as the source of truth format, but it's the same idea, that in any given creative domain, you have some kind of source of truth, which the designer will jealously hold on to, the camera raw of a photographer, or the Illustrator file of an illustrator, or PDF. And then you have a transport format, which use what you send out over the internet. And that's fine, because the transport format is typically more compact, more easy to, more widely supported, more easy to display. The problem with it is that it's a one-way ticket. It's a lossy process going to the transport format. And if we're thinking about a creative process, we're going back and forth. If neural fields become the source of truth format, but then we're having to do this reprojection or this rebaking after too many operations, there's a risk that we might sort of start losing fidelity. And actually, you can see this in JPEG, right? The reason that designers hold on to their PNG jealously is that, if you repeatedly re-JPEG the same image, so you're bouncing back and forth between a PNG file and a JPEG file, after a few hundred bounces, and if you did that after every brushstroke, you would lose your image entirely. And I thought for fun, I would actually do this in with a small ReLU network, and it immediately shows you the spectral bias that we've heard about today, that after 100 generations or so, the clouds have become blurry. And this is with a fairly large number of frequency bands in the positional encoding. And there's another problem, actually, that these kind of positional encodings, especially the ones that are global, have. So frequency encoding, if you remember, takes that position, feeds it through sine waves, which are effectively across the whole image, and then go through an NLP, which likewise is global, in the sense that if you change any of the weights in the network, then the entire image will change. You change one number in your matrix, the whole image will change to some degree. So here I've taken Albert, and I've put him into a ReLU network with, I think, 4 layers, 128 neurons each, with a frequency encoding. And if I flip back and forth here, as soon as I add the light bulb, you'll see that the entire image changes. It's not just the area around the light bulb that's changing, it's all of the sort of undulations of those sine waves. And that's really undesirable in a sort of iterative baking process. You don't want edits over here to be affecting something you're maybe not even looking at as an artist. So this is one of the big challenges for neural fields, I think. And just to lean into it to make it more visible, perhaps over the Zoom compression, here it is with fewer octaves in the frequency encoding. So you can just really see that when I add the light bulb, the artifacts across the image change globally, and that's a problem. Future work to be solved, I hope. Okay, So now I've been so glass half empty about neural fields. You know, they're globally, they change a lot. We can't use them as a source of truth format, perhaps. What do they have to offer? And well, I think what the best thing to do is to look at all of this through the lens of the framework that we've learned about today. So to recap some of the slides from the other speakers today, fundamentally, we have this sort of methodology which starts with some parameters, feeds it through some function, which is typically an MLP, has a forward map and makes pictures. And as we've also discovered from the literature, you know, planoxels, direct voxgo, NGLOD, there are lots, and dreams in my earlier beginning of my talk where we had these parametric SDFs. The function that you evaluate, the implicit function f of x, can be actually parameterized by many different things. But actually, as Ellen said recently, if you only had a single molecule in the last talk, she was saying, you know, if you only had a single shape, then maybe a big voxel grid would be sufficient. And it's only when you start generalizing to a kind of class of shapes or a continuous movement of shapes that you actually start wanting to have these scene parameters, a latent code perhaps, or a general, you know, a way of parameterizing the network that allows you to have a whole class of shapes rather than just a single shape. And I think that's where the superpowers come in of the neural fields. So superpower number one is that we can do inverse rendering. And all of those 3D sculpting programs I showed you, all of them use implicit fields, and not one of them, to my knowledge, thought about this idea that we could backpropagate through our representation, whether it's an MLP or not. We could have been doing optimization for years in the graphics community, but we didn't. And I think that this framework, even when you don't have the neural part, is still interesting. And so in fact, the neural fields course for me is about, I don't know, differentiable fields, backpropagatable fields. I think that's an interesting sort of superset of neural fields. And the superpower number two is that we've always had these different representations like grids, sparse grids, trees, and even these parametric representations. We've never had a way of converting between them. I mean, we could evaluate the parametric SDFs, for example, into grids, but there was no way of going back. But now we have the ability to kind of define a loss, whether it's a photometric loss on images or a 3D loss on you know, across the whole volume. And now we can actually propagate and use this machinery to move between different representations. And I think that's very exciting. And then superpower 3 is this generalization, this idea that a single network or a single representation could be a whole class of shapes, could be all of the cars in a shape net, or could be all of the aeroplanes, whatever it is you want to have. Okay. And of course, as soon as you have generalization, you have generation, and that gives us the sort of we're just beginning to see the beginnings of it, where you know you feed a frozen text encoder and a vision encoder, you render random views, and now you can run algorithms like CLIP in order to basically end-to-end optimize a NERF field directly for from text. So, you know, render me an avocado chair, and now you get a NERF fully out of it. And I think this is just beginning to kind of emerge. What's lovely about it is that, to me, this is about taking the mind-boggling power of pre-trained language models and applying it to the framework that we've just learned about today. This very actually fundamentally quite simple framework for neural fields. And we can now hot glue it to all sorts of other interesting things. And just 2 years ago, when I was working on neural fields, I had no idea any of this was possible. And so let's just recap, and that is my final slide. I think that within the narrow domain of 3D shape creation, it's too limiting to just say that we get a nice compact representation, right? A NERF is nice and small and compact. And Tawaki's work in SIGGRAPH this year about making them even more compact is very exciting. But they have problems when you insert them into the loop, and then you have this lossy process each time you bake down. But they bring these unbelievable superpowers to the table, which for me are a lot about understanding. So using backpropagation and differentiability to understand the scene, so that I don't have to put an awkward bounding box around the gargoyle, but I can just click on the gargoyle. You know, there's works like iLabel where you can just click on a point in a neural field, and the network seems pretty good at understanding what it's captured. But then also this idea of generalization and generation across a whole class of shapes is something that I think that the non-neural methods just simply couldn't even hope to do. And so when we combine these kind of areas together, I think we're going to get some really fun new workflows that augment the existing ones, the existing non-neural workflows. And that's everything. I look forward to seeing what you do next year.
All right, thanks so much, Alex, for the super inspiring talk. I guess now we can open up the discussion to the audience if anyone has any questions.
To get us started, a very simple practical question. Prashant asks, does the public instant NGP code have the operations that you just showed?
So the Albert Einstein image stuff and the decaying image stuff I actually wrote this morning in Python. So yes, that's using the public instant NGP. The SDF morphing stuff is actually not instant NGP. That's actually something that I wrote for this talk. So that's not released, unfortunately. But it's if you have an SDF renderer, it was very simple and it was not neural. So I don't know if it's not relevant to instant NGP. So the SDF stuff not, I'm afraid.
Thank you so much for doing that, just for this talk. I have another question. Have you ever seen so far any production creative tools exploring neural fields? Or are we still too early?
Yeah, I think that they must be happening behind closed doors, but I'm not actually party to any. But I think that a lot of the papers coming out of Adobe Research are very exciting, and NVIDIA has some as well. And I think that it seems to me that they're natural things. So I'm sure that there must be stuff going on behind the scenes. But I think that it's actually a case where the research community are ahead of the curve, right? So what's exciting to me about neural fields is that the sort of the trailblazing part is going on in this community. And there's opportunity still to solve some of these problems that have been raised across this whole course today. And I'm not sure that that it's going to flip immediately. I think there's opportunity to do creative work purely in the research domain and then see it trickle into production fairly soon. I think a lot of people are excited by stylization, sort of one click, go to like, oil painting style. And I was always very dismissive of those things. But then when you start seeing the expressiveness of language models, which is something that just totally blindsided me, for example, that you can get so much through prompt engineering in the 2D domain. I mean, I guarantee that there must be lots of people trying to chew on how that would translate into 3D. And I think that neural fields are probably one of the strongest contenders for a kind of underlying representation to kind of fiddle with in that context.
Thank you very
much. Vague answer, so, yeah, vague answer, sorry.
Oh, that was really good. All right, any more questions from the audience? Okay, in the interest of time, let's thank Alex again for the very energetic and inspiring talk.
Thank you so much, Alex, for that really inspiring talk, and also to our other invited speakers for their great talks. I prepared a few concluding remarks, but then I know it's been a long day and all of you are probably tired, so I'll keep it very short with just two things. So first, some of you mentioned that the URL to join our Slack community wasn't working, the one that we showed this morning. So what you see here is a link that should work now. So if you want to take a picture of the QR code, please go ahead. I'll leave this for about 10 seconds. We look forward to seeing you in the Slack channel and growing this community. Hopefully, as Alex said, for CVPR 2023, we'll grow even stronger. All right, so with that, I'd like to take this opportunity to thank all of you for coming, to our invited speakers for their really great presentations, and finally also to my co-organizers for organizing such an amazing workshop. Thank you so much, and see you soon.